My name is Ala Kamil, and I will be serving as the designated federal official to the United States Environmental Protection Agency Science Advisory Committee on Chemicals, which is referred to as the SACC. For this meeting and in my role, I will be opening this public meeting. I want to thank Dr. George Cobb for serving as chair of the committee and Dr. Robin Ann Gentry for serving as co-lead for this meeting. I also want to thank members of the committee, ad hoc reviewers, and the public for attending this important meeting. We appreciate the time and effort of the committee members in preparing for this meeting, considering their busy schedules. In addition, I want to thank EPA's Office of Pollution Prevention and Toxics, OPPT, and my colleagues at the Science Advisory Committee branch in EPA for their hard work in preparing for the peer review of the draft risk evaluations for 134678 hexahydro, 466788 hexamethylcyclopenta gamma-2 benzopyrene, known as HHCB, and for phthalic anhydride, and the draft hazard assessments for orthodichlorobenzene and para-dichlorobenzene. The SACC is a federal advisory committee that provides independent scientific peer review and advice to EPA on chemical-related issues regarding the impact of proposed regulatory actions on human health and the environment. The SACC provides advice and recommendations to EPA. Decision-making and implementation authority remains with the agency. The SACC for this meeting is comprised of 16 members who are experts in toxicology, environmental risk assessment, exposure assessment, and related sciences. The expertise of these members is augmented by 11 ad hoc reviewers who are special government employees participating in this SACC peer review, providing additional scientific expertise, including transcriptomics, inhalation and respiratory sensitization, exposure to consumer products, cancer and non-cancer human health hazards, and bioaccumulation in aquatic environments. This is in order to assist in the reviews conducted by the SACC committee. Now, as the designated federal official for this meeting, I serve as a liaison between the SACC and the agency. I am responsible for ensuring provisions of the Federal Advisory Committee Act, also known as FACA, are met. The Federal Advisory Committee Act of 1972 established a system that governs the creation, operation, and termination of executive branch advisory committees. SACC meetings are subject to all FACA requirements. These include open meetings, timely public notice of meetings, and document availability to the public. All documents are available to the public in the docket at regulations.gov, and the website is listed in the meeting agenda. As the designated federal official for this meeting, a critical responsibility is to work with appropriate agency officials to ensure that all appropriate ethics regulations are satisfied. In that capacity, committee members received training on provisions of the federal conflict of interest laws and ethics and scientific integrity training. In addition, each participant has filed a standard government financial disclosure report. Our deputy ethics officials of the Office of Mission Operations and their teams, in consultation with the Office of the General Counsel, have reviewed these reports to ensure all ethic requirements are met. The SACC will review challenging scientific issues over the next 5 days. We have a full agenda, so meeting times are approximate. Thus, we may not keep to exact times as noted in the agenda due to discussions and public comments. We strive to ensure adequate time for the agency presentations, public comments, and committee deliberations. For presenters, SACC members, and the public commenters, please identify yourself as you speak into your microphones, since this meeting is being webcasted, transcribed, and recorded. I'd like to note that we have a live video webcast for this meeting through YouTube, and to access it, please go to the link on the meeting webpage listed in the agenda. Copies of all EPA presentation materials, written public comments, and other documents related to this meeting are available in the public docket at regulations.gov. Copies of the presentation materials submitted this week by public commenters will also be available in the public docket within a week. For this meeting, there are so far 53 registered attendees, 16 of which are registered to give oral comments. Registration to attend this meeting is open until the last day of the meeting. Members of the committee and ad hoc reviewers are encouraged to consider all written and oral public comments submitted for this meeting. We dedicated adequate time for the agency presentations, public comments, and peer reviewers to discuss their questions. As we move through the proceedings, if time allows, we may be able to move to the next agenda item if an item takes less than the anticipated time. Now, for press inquiries, for members of the press, EPA Media Relations staff are available to answer your questions about this meeting. Please address all questions to Kathy Milburn at the email press@epa.gov. Now, at the conclusion of the meeting, the SACC will prepare a report as a response to questions posed by the agency. Background materials, presentations, and public comments will also be included in this report. This final report also serves as the meeting minutes. So we anticipate the final report and the meeting minutes will be completed in about 90 days after the meeting is concluded. Again, I wish to thank the committee, ad hoc reviewers, and the public for your participation. And special thanks are due to the EPA teams who participated in the preparation of this peer review. I'm looking forward to both a challenging and interesting discussion over the next 5 days. And now I turn the meeting over to our chair, Dr. George Cobb. Dr. Cobb.
Thank you, Dr. Kamal. And thanks to everyone in the audience. I'll apologize right off the bat. I have a brand new computer system that I'm still getting used to here at Baylor. So that happened, of course, just the last few days. So I would also like to echo Dr. Kamal's thanks to the career staff at EPA, especially those in OPPT who are putting these documents together under very short timelines for the quantity of work that's being done. And also to Dr. Kamal and his colleagues there that are helping us organize and get all of these meetings underway and processed in an appropriate way. And thank you as well to the public for joining us. This is an important aspect of having these meetings in public for everyone to understand what's going on. I'd also like to thank the committee members who are with us today and the ad hoc reviewers. This was a heavy lift to get all of this reviewed. These 5 chemicals is quite a bit. And I really appreciate those efforts. I would now go into a roll call and introductions. On the first day here, folks, if you will give a very brief introduction when I call your name, and then we'll proceed through the roll. Just for completeness, I am George Cobb. I am a professor of environmental science here at Baylor University, and I'm the chair of this committee. And now we'll go to Dr. Apte.
Hi, everybody. My name is Udayan Apte. I'm a professor in the Department of Pharmacology, Toxicology, and Therapeutics at the University of Kansas Medical Center, and my expertise is on liver toxicity, environmental chemical exposure to liver.
And Dr. Fong.
Thank you, Dr. Cobb. Hi, my name's Art Fong, and I am the technical leader for Smart Chemistry at Apple, and my area of expertise and practice is in safe and sustainable chemistry. Thank you.
Thank you. Dr. Baker.
Hi, I'm Marissa Baker. I'm an associate professor of occupational health at the University of Washington in Seattle.
Thank you. Dr. Chasen.
Hello. My name is Dr. Christine Chasen, and I'm retired as director of the Lifeline Group, and my area of expertise is exposure and risk assessment modeling, particularly for aggregate and cumulative assessment.
Thank you. Dr. Fox.
Hello, my name is Mary Fox. I'm an associate practice professor at the Johns Hopkins Bloomberg School of Public Health, and I'm associate director of our Risk Sciences and Public Policy Institute.
Thank you. And now the co-lead for this meeting, Dr. Gentry.
Hello, I'm Robin Ann Gentry. I'm a consultant and principal with Ramble. I'm a PhD and board certified toxicologist with over 35 years in all aspects of human health risk assessment.
Thank you. Ms. Jenkins.
Good morning. I'm Allison Jenkins. I'm a regulatory toxicologist and risk assessor at the Texas Commission on Environmental Quality. Thank you.
Cynthia, thank you. Cynthia, I don't know why I keep missing your name. I do not know. It just happens. I'm sorry. I'm going to go back to Dr. Graham.
That's quite all right, Dr. Cobb. I am Cynthia Graham. I am a toxicologist and I'm an independent toxicology consultant. And my expertise is in respiratory and dermal sensitization and occupational asthma.
Thank you. Dr. Lee.
Dr. Cobb. Hi, everybody. I'm Lee. So I'm associate professor of environmental health at the University of Nevada, Reno. I have a training background of environmental chemistry and environmental exposure science. I develop computational models to simulate how chemicals are moving, changing, and building up in the environment and the human body.
Thank you. Dr. Merced Nieves.
Good morning. I'm an assistant professor at Icahn School of Medicine at Mount Sinai in the departments of Public Health and Environmental Medicine. My expertise are in neurotoxicology and environmental epidemiology.
Great, thank you. Dr. Ottinger.
Good morning, everyone. I'm Mary Ann Ottinger. I'm a professor emeritus and research professor at the University of Houston in the Department of Biology and Biochemistry. I'm an endocrinologist, a neuroendocrinologist, and work in the areas of ecotoxicology and wildlife.
Great, thank you. Dr. Presbilla.
Good morning. My name is Jennifer Prisbilla. I am an environmental health scientist at the Agency for Toxic Substance and Disease Registry. My expertise is in human health risk assessment, environmental epidemiology, and risk exposure. Thank you.
Thank you. Dr. Rubin.
Good morning, I'm Rainbow Rubin. I'm Science Director at Breast Cancer Prevention Partners and affiliated with UC Berkeley Department of Environmental Health Sciences.
Thank you. Dr. Sammel.
Good morning, Dr. Cobb and everybody. I am Dr. Jennifer Sammel. I am a consultant and principal scientist with Insight Exposure and Risk Sciences in Boulder, Colorado. I'm also affiliated with the University of Minnesota School of Public Health, Environmental Health Department. And my expertise is in exposure science and industrial hygiene, as well as risk assessment. And I'm a certified industrial hygienist and certified safety professional.
Thank you. Mr. Wright.
Good morning. My name is Mike Wright. I was the Director of Health, Safety, and Environment for the United Steelworkers Union. I'm now retired. And if you're wondering why the Steelworkers Union knows anything about chemicals, we were also the union which had the largest membership in the chemical industry and in chemical using industries like rubber and paper. My training was in industrial hygiene and in industrial engineering, and my expertise is in the occupational aspects of toxic chemicals.
Thank you very much. And Dr. Kamal, is Dr. Anderson not joining us? Is that what I understand?
Yes, that's correct.
Okay.
Mhm.
Okay, so then we go to Dr. Gadia.
Good morning, everybody. I'm Sanket Gadia. I'm the lead toxicologist at Tesla, and I have expertise in human health hazard assessment with focus on occupational toxicology. Thank you.
Yeah, thank you. Dr. Islas Robles.
Good morning, everybody. My name is Argel Islas Robles. I am toxicologist and study director at the Institute of In Vitro Sciences. I am also a board-certified toxicologist, and my expertise is in the application of new approach methodologies on dermal toxicity with a focus on skin sensitization. Thank you.
Thank you. Dr. Carmos.
Yes, hello, my name is Agnes Carmouse. I'm a senior toxicologist at Syngenta, focusing as what we call a human safety project expert. My expertise is in applying new methods and benchmark dose modeling to risk assessment, and I have a background in transcriptomics. Thank you.
Thank you. Dr. LaRocca.
Hi, everybody. I'm Jessica LaRocca. I'm the Biologicals Pipeline Development Leader for Corteva AgriScience. My background is in toxicology, and my area of expertise is in new approach methodologies and mode of action studies. Thank you.
Thank you. Dr. Lovato.
Okay, hi everybody. My name is Ramon Lavado, and I'm an associate professor at Baylor University, and my expertise is in ecotoxicology and aquatic toxicology.
Thank you. Dr. Pandiri.
Good morning, everyone. I'm Arun Pandiri, and I'm a group leader for the molecular pathology at the Division of Translation Toxicology at NIHS. My background is I'm a veterinary pathologist, and I've been at NTP for more than 15 years.
Excellent. Thank you. Dr. Rager.
Hi, my name is Dr. Julia Rager. I'm an associate professor and associate chair in the Department of Environmental Sciences and Engineering here at UNC's School of Global Public Health. I have expertise in toxicogenomics, bioinformatics, and also inhalation toxicology, and I was a consultant prior to my current job in academia.
Great. Thank you. Dr. Slink, and before he introduces himself, I'll just say he was my predecessor as chair of this committee, so I'm very happy to have Dan back on the committee as an ad hoc reviewer. Dr. Slink.
Thanks, George. My name is Dan Schlenk. I'm a professor of aquatic ecotoxicology, environmental toxicology at University of California, Riverside. Area of expertise is that of fate and effects of legacy and emerging contaminants in aquatic biota. Nice to be with you.
Thank you, Dan. Dr. Sao.
Good morning, everyone. My name is Kan Shah. I'm Associate Professor of Environmental and Occupational Health at Indiana University School of Public Health, Bloomington. My expertise is computational toxicology, especially dose response assessment and benchmark dose modeling. I'm also a board certified toxicologist. Thank you.
Thank you. Dr. Strickland.
Hello, I'm Judy Strickland. I'm a toxicologist specializing in non-animal methods for hazard assessment, especially skin sensitization and acute toxicity. I retired from Enitiv Incorporated, where I supported projects at the National Institute of Environmental Health Sciences.
Thank you. And Dr. Wolf.
Last and least, I'm Doug Wolf, currently independent consultant, formerly was with the US EPA and Syngenta Crop Protection, not at the same time. I'm a veterinary pathologist by training, with expertise in toxicologic pathology, carcinogenesis, and developing and implementing new approach methods for chemical evaluation.
Great. Thank you, Dr. Wolf. And I think that does it for the introductions of the committee. And now I think we can move to the agenda, which would be to have welcoming remarks from Dr. Alyssa Reeves, the Director of the Office of Pollution Prevention and Toxics. So if Dr. Reeves is on the line, I'll turn the floor over.
Great, thank you, and good morning, everyone. I'm happy to join you here today and welcome everyone to our SACC meeting and set the stage for this meeting this week. I'm the Director of Office of Pollution Prevention and Toxics, and I've been with our larger office of OCSPP for over 20 years. And throughout my time here in OCSPP, whether in Office of Pollution and Prevention or over in Office of Pesticide Programs, it's always important for us to produce transparent, predictive, and scientifically sound and robust risk evaluations that are consistent with statutory and scientific obligations. EPA's risk evaluations are the backbone of regulations that impact the public, workers, and hundreds of industries and sectors that rely on these chemistries. And so the transparency and regulations rely on critical information that we receive and consider from our stakeholders via public comment and peer review committee meetings like this one here this week. Next slide. I'd like to first acknowledge all of the stakeholders that we collaborate with. First, I'd like to say sincerely thank you to the SACC members for your commitment of time and expertise to support this effort. And I also want to give a big thank you to our collaborators, including DTT and NIEHS, as well as NICEDM, ICVAM, and a special acknowledgement to our technical experts, Emily Renke, Dory Gurmalak, and Vic Johnson, for their help and expertise with the chemicals this week. Next slide. So I want to set the stage over the next couple of slides here. We've divided the presentations into 3 parts. So part 1 is ortho and para-DCB. The second part is phthalic anhydride or PAD. And next slide. Part 3 is HHCB, as you can see here. Next slide. So for our peer review meetings like this one, gold standard science is a critical component to our risk evaluation process. They ensure that the evaluation is based on sound science and that all relevant data are considered. The SACC plays a virtual role in this process by providing independent expert review of the underlying science that's relied on in our risk evaluations. Like other federal advisory committees, the SACC is an important tool within the EPA for building consensus and providing input and recommendations from the agency's customers, partners, and stakeholders. Therefore, we would be greatly appreciative of this committee striving to reach consensus as much as possible. Your insights and recommendations help enhance the quality and credibility of the final risk evaluation. And notable and exciting with these chemicals this week, and in line with the executive order restoring gold standard science from May of 2025, the risk evaluations also utilize new approach methodologies or NAMs. Next slide. So TSCA section 4H encourages the use of alternative methods or new approach methods, or NAMs, that reduce or replace use of vertebrate animals while providing information of equivalent or better scientific quality and relevance that will support regulatory decisions. In January of this year, Administrator Zeldin announced the agency was getting back on track with reducing mammalian animal testing and recommitting to the ambitious goal laid out during the first Trump administration to eliminate the practice by 2035. This charged OCSPP to prioritize developing and implementing high-quality alternatives to reduce testing on vertebrate mammals to align with regulatory requirements, a high bar of gold standard science. In this SACC, you'll see where our teams integrated and evaluated the data of these NAMs. Next slide. So let me call out a few highlights of the application of the NAMs for the DCBs.
Excuse me, Alyssa, you seem, oh, there you go. The slides were off, but they're back. Yeah, they're back.
Thank you. For the DCBs, the risk evaluation team included data from the 5-day transcriptomic studies, and these transcriptomic based approach is the first quantitative use of transcriptomic data to inform TSCA's risk evaluations. For phthalic anhydride, or PAD, the risk evaluation applied adverse outcome pathways as a framework to organize data from in vitro, and in vivo streams of evidence as part of its characterizations of inhalation and dermal hazards of phthalic anhydride. And for its dermal assessment, a draft point of departure was developed using a computational NAMs-based approach, the Sarah Ice model, or the Skin Allergy Risk Assessment Integrated Chemical Environment model. And this model integrates data across multiple NAMs-based assays to derive a human relevant outcome. And so finally, the last slide, I'd like to just hand off to Steve Dutton, our office director, or our director of Existing Chemicals Risk Assessment Division, to walk us through the meeting. Steve?
Great, thank you, Alyssa. So as mentioned, I'm Steve Dutton. I'm director of the Existing Chemicals Risk Assessment Division, the division that's primarily responsible for much of the material that we'll be discussing this week. So I'll just be kind of continuing this introduction here and echo Alyssa's thanks to everybody who's online and who has been starting to go look through all the materials that the team has pulled together here over many years to get us to this point. We definitely look forward to all the discussions today and happy to be helping kick things off here. I'm going to give just a quick summary of some of the TSCA regulatory context that has us here today. And we'll end with a very quick summary, trying to summarize in a tremendous amount of information in one slide per chemical that we'll be looking at this week. And then, of course, with a longer presentation coming from the team after myself. If we can go to the next slide, please. Thank you. So TSCA Section 6B requires EPA to conduct risk evaluations to determine whether a chemical substance presents an unreasonable risk of injury to human health or the environment without consideration of cost or other non-risk factors, and inclusive of consideration of potentially exposed or susceptible subpopulations identified by EPA as relevant under the conditions of use. Next slide, please. All right, on slide 10, we have kind of a rewording of all this. So under TSCA, EPA is required to evaluate existing chemicals using the best available science and reasonably available information to make decisions based on the weight of scientific evidence. We develop risk-based chemical assessments without consideration of cost or other risk factors and considering the risk to potentially exposed or susceptible populations. And then we address any unreasonable risk that is identified through in the risk evaluation process in the risk management step. So all the chemicals that we are discussing this week are on the TSCA high priority list. And as such, it's already been established that they may present unreasonable risk to human health and the environment. And the objective of the risk evaluation is to determine if they do present unreasonable risk to human health or the environment under the conditions of use. Next slide, please. So this slide shows a kind of a graphical representation of the steps in the process here. So the TSCA risk evaluations inform our risk management steps at the end of this figure here. The final risk evaluations that were the technical documentation we'll be discussing here goes into those final risk evaluations. That collectively serves as the primary scientific support documents that the agency uses to determine if it is necessary to issue regulations or address any unreasonable risk identified as part of this evaluation. Risk evaluations are to be completed in 3 years using reasonably available information. And this is an evolving process with the development of new assessment methods and approaches over time, a lot of which you'll be hearing about here this morning. And this is where we very much value the input from the committee to provide us guidance on our use of these new and emerging approaches. If unreasonable risk is determined, the next step is the risk management, where restrictions are developed to mitigate the unreasonable risks that may be identified. Next slide, please. So just a couple general reminders before I get into a summary of the chemicals that we'll be looking at here. So we're seeking SACC's input on the new methods, approaches, and scientific issues in the technical documents that have been provided for review. And accompanying those are the charge questions, which are sort of honing in on the issues where we really would seeking your advice. We've intentionally left out questions about routine risk characterization calculations or things that we've received clear and sound advice for in the past. The risk evaluation, which contains the unreasonable risk determinations, are provided as accompanying information with some of these chemicals when they've been available. But the focus of this meeting here is on the technical support documents and the technical components that go into those risk evaluations. The full risk evaluation packages for all of the chemicals will be made available for 60-day public comment in a separate process outside of the SACC review. And we'll be doing that as soon as those are all available. Jumping to the next slide, I can start on a very quick summary of the 4 chemicals we have to discuss this week. So we have ortho and para-dichlorobenzene, we have phthalic anhydride, and we have HHCB. So for next slide, for ortho and para-dichlorobenzene, the draft hazard technical support documents for those were provided to the SACC and posted for public access in early April. And that's what our charge questions are focused on, the hazard technical support documents. The draft exposure and risk evaluations for DCBs will be made publicly available as soon as those are completed, hopefully very soon after this meeting. Both ortho and para-dichlorobenzene are produced through chlorination of benzene, but they have quite different chemical properties, uses, and health effects. Ortho-dichlorobenzene is a volatile liquid at room temperature. It is primarily used as a solvent for its solvent properties in paint thinners, glazes, and lubricants. It is also, its exposure is associated with respiratory symptoms, liver, and kidney toxicity. In contrast, para-dichlorobenzene is a crystalline solid at room temperature, and it's primarily used in the manufacture of thermoplastics, and it's also used in solvents and air fresheners. Para-dichlorobenzene exposure is associated with developmental, liver, and respiratory system toxicology. Transcriptomic data, as was described by Alyssa, has been used for both of these chemicals. You'll hear quite a bit more about that shortly in our next presentation. So that was leveraged for both ortho and para-dichlorobenzene, and neither chemical was found in the draft hazard assessment to cause cancer in humans. Environmental hazards were also assessed for aquatic and terrestrial organisms for both ortho and para-dichlorobenzene. Jumping to the next slide, slide 15 has a quick summary for phthalic anhydride. Phthalic anhydride is primarily used as a chemical intermediate in manufacturing products such as plasticizers and resins. It is also found as an ingredient in oil-based consumer products, such as paints and coatings, and a hardener in adhesives and sealants, and is both a skin and a respiratory sensitizer. Although in the draft assessment, we have concluded it does not have genotoxic or carcinogenic effects. Phthalic anhydride is unstable in the environment and is expected to be primarily present as o-phthalic acid, which you'll hear a little bit more about that this afternoon. Next slide is the last chemical I'll be just describing very briefly here. HHCB is primarily used as a fragrance ingredient in perfumes, cosmetics, personal care products, detergents, and household cleaners. And this assessment, we used a fit-for-purpose tiered approach, which you'll be hearing about towards the end of the sessions here this morning or this afternoon. And this tiered approach, we used combining screening level and refined analyses by population, route, and pathway. This assessment also used an integration of monitoring and modeling estimates to strengthen our weight of evidence. The draft HHCB risk evaluation concludes that HHCB presents no dermal hazards based on these robust data sets of human, animal, and in vitro studies. EPA identified no effects suitable for deriving an acute point of departure for any route of exposure, and therefore EPA did not quantitatively evaluate HHCB for acute risk to human health, but the non-cancer point of departure selected for intermediate and chronic oral and inhalation exposures is health protective, including any potential cancer effects. And if we'll jump to the next slide, this is my last slide, just has a quick overview of the timeline of what got us to where we are today. So this timeline shows the progression for these 4 chemicals going from prioritization through the scoping and to the draft risk evaluations, which were released in early April this year and are under discussion here this week. These 4 chemicals were designated as high priority substances in 2019, with final scoping documents released in 2020. And looking forward, we anticipate releasing, as I mentioned, the dichlorobenzene draft exposure and risk evaluations very shortly for a full 60-day public comment, and finalizing all these risk evaluations under discussion this week, this fall and winter, but no later than our February 2027 consent decree deadline. I'd just like to, again, thank everybody for their time and attention, and for the team who's here in the room with me for all the effort to get us to this point. So I think at this point, we can move on with the technical presentations on...
Excuse me,
I'd like to hand it back to you.
I'd like to turn this back to the committee for a second before we get into the technical presentations to see if there's any questions or comments from the committee. If there are none from the rest of the committee, I'd like to, again, I'd like to thank you for making this presentation. I appreciate it. A couple of things that really do need to be pointed out. First of all, in the phthalic acid or phthalic anhydride, you've done a good job with the use of phthalate as a transformation product that would probably be the toxicant of most concern. But when we were doing the phthalic ester combined assessments or reviews, that was not done. The data that is feeding this assessment was not included there, and very easily could have been to more completely evaluate that assessment, and that's not good for that particular assessment. So we'll circle back to that. I'd also like to say that several aspects of this risk assessment process are not being evaluated by the committee, which may mean that we're not fully fulfilling the statutory requirements of the committee to review the assessment. That's not for us to decide, but it needs to be considered by EPA as you're moving forward. And the risk characterization that you've omitted in the questions you've stated that we gave you clear advice, but we've given you clear advice and you have not addressed the matters that we suggested that you address. Specifically, the exposure to pests, communities that was mentioned heavily. If we're not evaluating how the exposure assessment is done, there's no way to evaluate how that important subgroup and the rest of the population, human populations, are being affected. So those are my comments regarding what has been said so far. And again, I'd like to thank you for making your presentation and make sure that we get my comments on the record before they get lost in all of the things we have to do this week. So I'll turn it back to you for either response or to turn it over to your next presenter.
Yeah, thank you, Dr. Cobb. I appreciate the comments there. So yeah, I think some of those things we can discuss with the experts as we continue on with the technical presentations here. So I will go ahead and hand it then to my colleagues in Research Triangle Park, starting with Dr. Thomas Jackson, who's giving us our overview of the ortho and paradichlorobenzenes human health hazard assessments and the transcriptomics work that's went into those. Over to you.
Good morning, and thank you, Drs. Dutton, Reeves, Kamel, and Cobb. My name is Thomas Jackson, and I'm a member of the Risk Assessment Support Division that was newly created in the 2025 HHCB reorganization to provide research support to the Office of Chemical Safety and Pollution Prevention. Today, our focused discussion will be on the draft human health assessments for ortho and paradichlorobenzenes, as well as the transcriptomic analyses that are supporting both chemicals. I would like to thank the members of the SACC for their participation and the feedback that we'll receive throughout our meeting. And I also want to thank the public commenters that we'll be hearing from as well. Next slide. I would like to start off today's technical dichlorobenzenes presentation with this first slide emphasizing the incredible teamwork, collaboration, and contributing authors that brought us to this published draft hazard assessment. We are especially appreciative of efforts from Drs. Scott Auerbach and Georgia Roberts and the Division of Translational Toxicology at the National Institutes of Environmental Health Sciences for developing and performing the 5-day transcriptomic study exposures and data generation. Next slide. This table provides an overview of our presentation outline. I'm going to start us off with a description of the transcriptomic methods and analyses which support both ortho and paradichlorobenzene hazard assessments. My colleague, Dr. Keith Jacobs, will follow with our presentation of the non-cancer hazard assessment, and then Drs. Sasidaran and Haggard will present the cancer assessment for both ortho and paradichlorobenzenes. The relevant charge questions for each section of the presentation are also shown in the table and will be shown on the slides as we present. Next slide. Our document map here reminds the committee that only the hazard technical support documents and supporting transcriptomic technical support documents shown here as TSDs 2 and 3 in this figure for both ortho and paradichlorobenzene have been submitted to date for the SACC for peer review. The focus of our dichlorobenzene charge questions is human health hazard, and the remainder of the risk evaluation package is still pending publication. Next slide. We will begin here with the technical portion of the presentations, and I would like to thank you for the opportunity to share the draft transcriptomic assessment for ortho and paradichlorobenzene with the technical support document for the draft risk evaluations supporting the hazard characterization of orthodichlorobenzene and paradichlorobenzene using 5-day in vivo transcriptomic studies. This describes EPA's proposed approach for analyzing and interpreting these transcriptomic data in the draft human health hazard assessment technical support documents and the draft risk evaluations for both ortho and paradichlorobenzene. In this presentation, we will give an overview of the technical details of the transcriptomic analysis and its associated methods. The full integration of these results with the apical health effect data can be found in the human health hazard technical support documents for each chemical and will be covered in later presentations by Dr. Keith Jacobs and Dr. Adi Sasidaran. Next slide. A literature review for para and orthodichlorobenzene found that para had relatively complete animal hazard data, but would benefit from support for the proposed mode of action for rodent liver tumors, whereas ortho had incomplete animal hazard data. In 2023, EPA's Office of Pollution Prevention and Toxics requested that the National Institutes of Environmental Health Sciences conduct 5-day inhalation studies with targeted transcriptomics for both ortho and para-dichlorobenzene for use in the forthcoming TSCA draft risk evaluations. We again want to reiterate that we appreciate Scott Auerbach, his team, and the productive collaboration we have enjoyed with NIEHS. Next slide. Here we present the rationale for short-term transcriptomic studies to indicate chronic points of departure. Short-term studies reduce and refine animal usage and toxicity testing while serving as a necessary refinement bridge to validate in vitro approaches. These are a cost and time effective way to detect gene expression changes that may be linked with adverse apical health effects. These can be conducted on a much faster scale than traditional toxicity studies and chronic bioassays. EPA conducted a value of information case study on the EPA transcriptomic assessment product known as the ETAP, and the results indicate that reducing the time to decision, realized by using the shorter duration process, has significant public health and economic benefits when compared with the longer traditional toxicity testing and human health assessment process. One consideration for quantifying a transcriptomic point of departure from short-term in vivo studies is to determine the duration of exposure needed to inform adverse health effects that may develop in longer duration, the classic chronic toxicity studies. Studies conducted across several organizations, including the EPA, Hamner Institutes, Health Canada, NTP, Corteva, and others, have experimented with different time points ranging from 1 to 90 days, with the goal of comparing dose concordance between gene set-based transcriptomic points of departure and the apical effect-based points of departure from traditional toxicity test designs and exposure durations. One of the aims of these investigations has been to identify an optimal repeated dosing duration for the transcriptomic assessment. Next slide. Here you can see the concordance between the lowest gene set from short-term, defined as less than 7-day, 15 to 21-day, 28 to 31-day, and 90-day studies against chronic 2-year apical benchmark doses or benchmark dose lower bounds. The solid black line indicates a perfect concordance at 1, with the dashed red lines representing a 10-fold difference between the benchmark dose or benchmark dose lower bound values. Overall, it's clear that there is a high degree of concordance, and these results have been used to build confidence in and justify the use of transcriptomic points of departure as predictive of apical points of departure. While these previous efforts have examined short-term exposures of varied durations, for the 5-day duration in particular, the results suggest that the error associated with the concordance between the transcriptomic benchmark dose or benchmark dose lower bound value versus the non-cancer and cancer apical benchmark dose or benchmark dose lower bound value is approximately equivalent to the inter-study variability in the repeated dose toxicity study itself. Additionally, the 5-day exposure duration has been recommended by the National Toxicology Program. Next slide. As a result, transcriptomic analyses from 5-day animal exposure studies have been proposed as a means to improve the risk assessment process and enhance testing paradigms for several reasons, including that it allows for a more rapid assessment of chemicals compared to traditional chronic toxicity testing. It offers increased, highly sensitive detection of gene expression changes, which underpin the observable apical health effects. It reduces and refines animal usage through shorter duration assays, while serving as a necessary refinement bridge to validate in vitro approaches. It provides characterization of critical cellular and molecular events to support the development of biologically plausible modes of action through identifying specific causal gene sets and or pathways that may be linked with adverse apical effects, and it can help prioritize chemicals for further assessment or assist in identifying critical data gaps in a cost and time-effective manner. Next slide. Because repeated dose studies related to respiratory toxicity were identified by the literature review as the most important data gap, the study requested by OPPT and conducted by NIEHS was conducted via inhalation exposure. In the study, healthy adult female mice and rats were exposed to either the ortho or para isomer of dichlorobenzene consecutively once per day for 5 days for a duration of 6 hours plus the time taken to reach 90% of the target concentration. On the 6th day, animals were necropsied and 5 putative target tissues of liver, heart, ovary, kidney, and lungs were collected. RNA was isolated and submitted for targeted RNA sequencing using the TempoSeq S1500 Plus assay to measure changes in gene expression. The goals of this study were to provide more information on the effects of inhalation exposure to ortho and para-dichlorobenzene, provide support for the proposed mode of action for para-dichlorobenzene, which my colleague Dr. Derek Haggard will present on later in this presentation, and to help explain species differences in rodent liver tumors. Finally, we wanted to develop transcriptomic points of departure for orthodichlorobenzene. I do want to mention that the transcriptomic data were generated using TimpoSeq's S1500 Plus platform. This platform has previously been demonstrated that extrapolation from the S1500 Plus panels show concordance with more than 90% of the biological pathway and gene set space represented in the publicly available, well-annotated, and comprehensive gene set database, the Molecular Signatures database. There are myriad ways that we can analyze transcriptomic data to understand biology, support mode of action, or derive points of departure. But the limited coverage of transcripts that are actually measured in the S1500 Plus assay, over 2,600 probes for rats and over 3,000 for mice, does limit some of the methods of transcriptomic analyses that could be used if we had whole genome coverage that can be used to inform mechanism and derive points of departure. However, EPA has devised an approach that we present here that is robust despite that coverage limitation, and that's what we are going to cover in the subsequent sections. Next slide. Sequenced reads were quality controlled following our standard processes, aligned to a reference genome, and prepared for analyses. Individual gene level analyses were performed, including benchmark dose analyses of each gene to curate dose responsive changes in gene expression, and those changes were subsequently summarized into gene sets that were used to derive points of departure. Grouping individual genes into predefined collections or gene sets based on specific biological pathways, processes, or molecular functions is a common method used to interpret and provide biological context to the observed changes in transcriptomic studies. Next slide. Before we dig into our interpretation of the results, I just want to spend a couple minutes showing the accumulation plots and how we're going to be presenting many of these results. Next slide. Here you can see the benchmark dose lower bound median along the x-axis, shown as BMDL median, with each point representing a distinct gene set, where the average benchmark dose lower bound median of the constitutive genes found within that gene set occur at that point along the x-axis. So each of those gray dots is a distinct gene set. Next slide. The y-axis shows where each gene set falls along the ranking of gene sets from 0 to 100% of all of the gene sets identified and included. The furthest left gene set is the single lowest BMDL median of a gene set, and this provides the first indication that any biological activity may be happening. Over to the right, where you see the inflection point highlighted, this indicates a burst of biological activity that continues to increase as cells respond to chemical exposure. This is the tipping point where coordinated activity typically begins to scale up. Next slide. As I mentioned, there are lots of ways that we can summarize these data, and there are lots of databases available for gene set collections. EPA has selected 2 of these gene set databases to aggregate and summarize the gene level dose response modeling results. The first gene set database is the gene ontology biological process that is used in the gene ontology category analysis module within Benchmark Dose Express 2.3, which follows the standard methods for the development of the EPA transcriptomic assessment products. Gene ontology biological process gene sets are derived directly from the gene ontology, or GO terms, that are developed by the expert-driven GO consortium as a structured, controlled vocabulary to link biological data across species using 3 functional categories based on hierarchical relationships. The GO-BP is a large database of well-annotated gene sets that provides comprehensive coverage of diverse biological functions. The GO-BP collection does suffer from a high degree of functional redundancy, which often occurs due to the hierarchical structure of GO-BP. When I say hierarchical structure, what we're talking about are the child terms, for example, microtubule-based process, which share nearly identical terms with its parent set, microtubule cytoskeleton organization, and would therefore result in 2 gene sets comprised of nearly identical membership or many times completely identical membership. Additionally, the GO-BP terms are large and include lots of probes with strong internal gene correlations. This, in conjunction with that hierarchical structure, can lead to a high rate of false positives. The next collection that we utilized was the Molecular Signatures Database, or MSIG-DB, which consists of gene sets that are reviewed, curated, and annotated manually. MSIG-DB gene sets are inclusive of hallmark, human chromosome cytogenic band positional gene sets, curated gene sets including canonical pathways, biocarta, wiki pathways, KEGG, and reactome, regulatory target gene sets, including those related to microRNAs and transcription factors, computational gene sets, including those linked to cancer, the gene ontology gene sets I described previously, oncogenic gene sets, and immunologic gene sets. So as you can see, this is another large collection of well-annotated gene sets with comprehensive biological function. The MSigDB has coverage over an extremely diverse landscape of biological mechanisms with over 50,000 total unique accession numbers for gene sets in the version used for this analysis. This broad representation of potential toxicities creates a valuable background for untargeted examination of potential chemical-induced transcriptomic effects. I want to emphasize that the MSigDB gene sets for mouse were mouse-native gene sets, meaning that those databases were curated specifically for pathways relating to mouse-specific cell and molecular functions, whereas the rat-specific gene sets required additional functional orthology mapping to the human gene set equivalents, because there are no rat-native gene sets available in the MSigDB. An additional strength of MSigDB is that its curators try to reduce the functional redundancy of Go terms, as domain experts reviewed the clusters of gene sets to merge and collapse similar overlapping categories and assign precise biological themes. Because of the broad coverage, MSigDB does still have redundancy and heterogeneity, but that collapsing of terms has reduced much of that redundancy. Next slide. We do want to emphasize that gene expression changes are not inherently adverse. Enrichment of gene sets alone does not necessarily result in an adverse apical outcome. For example, you can see changes in gene expression in a tissue that are adaptive and resolve back into a normal functioning tissue. However, changes in gene sets are often experimentally and computationally linked to cellular level responses that, when combined with mechanistic data, can relate to and inform apical effects. Next slide. So we found mechanistic key events that were identified following exposure to orthodichlorobenzene. Systematic review identified several of these key events, and for respiratory toxicity, these cellular pathways are supported by in vitro data, which found that apoptosis and oxidative stress response signaling were upregulated in a human lung epithelial cell line that was exposed to orthodichlorobenzene. Targeted investigations suggest that liver toxicity from orthodichlorobenzene in rats involves reactive oxygen species and is associated with activation of inflammatory signaling cascades through liver macrophage Kupffer cells. Orthodichlorobenzene-induced Kupffer cell activation appears to promote lipid peroxidation and protein adduct formation, which correlates with apical indicators of liver injury. Specific mechanistic data were not available for kidney, but it is likely that similar mechanisms underlie the observed apical effects. Therefore, we curated what we are calling supersets for each of the following 5 mechanism-informed terms: apoptosis, cytotoxicity, inflammation, oxidative stress, and necrosis, or a combination of all 5 terms. Here on the right, you can see a heat map that is showing the effects of orthodichlorobenzene on the gene expression in the liver of mice at each dose for each gene included in one of those supersets. Next slide. There's varying overlap between genes within each superset, owing to functional connections and overlap observed across many of these discrete cellular processes. This overlap is inherent to any and all enrichment analyses, but we do want to emphasize this point here. So you can see that these terms are not entirely distinct, with many of the genes that are included in gene sets relevant for apoptosis also in gene sets relevant for inflammation, for example. So you can see the apoptosis gene sets shown in the vertical green bar of this upset plot, with that next gray bar being the overlap of apoptosis and inflammation, and there is a high degree of that overlap. Next slide. Before converging on including only the combined MSigDB superset with all gene sets including any of the relevant terms of interest, we evaluated an additional transcriptomic point of departure values for each of the individual superset terms for apoptosis, cytotoxicity, inflammation, oxidative stress, and necrosis in each species, using both the lowest and 5th percentile value approaches. The combination of genes within any of the 5 superset terms relating to the plausible mode of actions described was determined by EPA to be the most appropriate to use to get a sense of the large-scale biological impacts of orthodichlorobenzene exposure. And this determination was informed by a recognition that individual superset terms were often too limited in scope to be informative, and that the combined set of superset terms exhibited better performance than any individual superset at aligning with the full MSigDB curve and representing the full landscape of transcriptomic changes. And in this figure here, you can see some of that with that first panel showing teal dots with the combined superset terms, and the second panel showing the sparse coverage that the cytotoxicity term alone would have provided. Next slide. Here you can see those supersets I just described highlighted in teal against that full landscape of all MSIG-DB terms in gray. So each gray dot on this plot is an individual MSIG-DB gene set term, and each teal dot is a superset term. Next slide. For orthodichlorobenzene, we are proposing 6 distinct analyses using these 3 libraries of gene sets. For completeness, a similar analysis was performed for para-dichlorobenzene, but the results of this presentation are going to focus on orthodichlorobenzene. The full description for both ortho and para can be found in our transcriptomic technical support document. Using the Go biological process, molecular signatures database, and the MSIG-DB superset curated libraries, we examined the gene set with the single lowest benchmark dose lower bound value, and we also proposed a 5th percentile of the distribution of benchmark dose lower bound values that I'm going to show more on in the next few slides. Next slide. This slide is now putting everything together and using the mouse liver as an example. So here you're going to see where those 6 transcriptomic points of departure that I described in those previous slides fall along the MSIG-DB curve. The purple vertical dashed 1 line shows the Go biological process lowest benchmark dose lower bound median. The gray 2 dashed line shows the MSIG-DB lowest BMDL median, and the teal 3 dashed line shows the MSIG-DB mechanism informed combined superset lowest BMDL median. Next slide. The purple in 4, gray 5, and teal 6 vertical dashed lines here show the 5th percentile of the distribution of benchmark dose lower bound medians for all gene sets identified in those libraries. And so you can see that where these vertical dashed lines fall is the 5th percentile of all of the included gene sets in the relevant database. Next slide. I'd like to briefly touch on how we are interpreting the MSIG-DB supersets with respect to the full MSIG-DB landscape. When these supersets fall along the full length of the background MSIG-DB accumulation plot and show representation from the highest BMDL median all the way to the lowest BMDL median, it suggests that the selected mechanism-informed supersets are representative of the full landscape of changes induced by all concentrations of orthodichlorobenzene exposure. Next slide. When there is a left shift of the MSIG-DB superset accumulation plot, this suggests that the selected mechanism-informed supersets are linked to only the lowest concentrations of chemical exposure and may reflect only the most sensitive toxicities. Next slide. Conversely, when there's a right shift of the MSIG-DB supersets, this suggests that the selected mechanism-informed supersets are linked to only the highest concentrations of chemical exposure, and those terms may not reflect more sensitive toxicities. Next slide. Now I'm going to show where the various transcriptomic point of departure values that were derived fall relative to each other for the liver and lung in both mouse and rat following the 5-day inhaled exposure to orthodichlorobenzene. There were quality issues in the kidney with potential pancreatic contamination, so those data were deemed unreliable and are not presented here. For the mouse liver, the combined MSIG-DB supersets fall along the accumulation plot curve and are representative of the full distribution of gene sets in MSIG-DB displayed in gray. You can see that the 3 lowest values, dashed lines 1, 2, and 3, for the 3 databases, all fall similarly along the accumulation plot curve, indicating that there's consistency amongst these 3 database collections. Similarly, the 3/5 percentile of the distribution of gene set values, shown by dashed lines 4, 5, and 6, also align. Strikingly, the 5th percentile values fall just below the inflection point of the accumulation plot curve, suggesting that the 5th percentile of the distribution is tracking with coordinated biological activity across the mouse liver. Next slide. Here we're showing the same thing, but for the rat liver. The rat liver shows even greater consistency amongst the 3 database collections with nearly overlapping values for the lowest and 5th percentile. Again, the 5th percentile, dashed lines 4, 5, and 6, falls just below the inflection point for rat liver. Next slide. This is the same thing, but for mouse lung, and we are similarly showing that the combined MSIG-DB supersets are well represented along the length of the accumulation plot curve, with relatively similar values for all 3 database collections. Again, the 5th percentile of each database collection falls just below the inflection point for mouse lung. Next slide. Finally, for rat lung, we see the weakest performance of the combined MSIG-DB supersets along the accumulation plot curve. However, it still generally tracks with and is representative of the full landscape of MSIG-DB gene sets. And additionally, the single lowest gene set values, shown by dashed lines 1, 2, and 3, are fairly similar. And the 5th percentile of the distributions, shown by lines 4 through 6, are also fairly similar, and again fall just below the inflection point of the accumulation plot curve for lung. Next slide. In this table, you can see the overall summary of results for the liver and lung, and the performance of all 6 transcriptomic point of departure derivation methods. This table is summarizing those previous 4 graphs I showed, and a very similar table is going to be shown by my colleague, Dr. Keith Jacobs, and he's going to contextualize that more in the context of the human health hazard assessment. Next slide. I'd like to conclude by presenting the 4 decisions that EPA presents for using the transcriptomic point of departure in the human health hazard assessment for orthodichlorobenzene. The first decision was to use the mechanism-informed supersets, which anchored the gene expression changes to mechanistic insights derived from the systematic literature review. Next, the combined MSIG-DB superset collection was determined to be more appropriate because it is unbiased to any individual mechanism and is less prone to spurious findings than any individual term. Third, the 5th percentile of the distribution of gene sets was selected. It can be challenging to interpret mechanism from a single lowest value, especially if the resultant term is not relevant for the biology or phenotype. The 5th percentile of the distribution is consistent with the threshold of toxicological concern and species sensitivity distribution approaches, which have been used historically by regulatory agencies, and it aligns with recommendations for in vitro screening approaches for bioactivity-based points of departure. Additionally, that 5th percentile transcriptomic point of departure consistently fell near the inflection point on accumulation plots for each tissue and species, demonstrating representation of early sensitivity for biological effects before maximal gene expression changes are induced. Given the sensitivity of this novel approach for identifying early transcriptional signatures of toxicity, merely applying the most sensitive or lowest gene set or superset, which could be an outlier, could be representative of transient effects, could be adaptive, and/or could be not solely driving the observed toxicities, would be less reliable as an indicator of adverse response data compared to the 5th percentile of the combined supersets, which were informed by mechanistic data. Finally, we present the inclusion of a transcriptomic point of departure, which has previously been demonstrated to show high concordance with apical points of departure derived from traditional toxicity studies. Aggregation of gene sets and deriving a transcriptomic point of departure provide a more biologically relevant term than any individual gene level analysis and provide broad coverage of potential toxicities across the MSIG-DB landscape. The changes observed from a transcriptomic point of departure are not inherently adverse, but we have attempted to overcome this limitation by presenting novel analyses that tether the transcriptomic point of departure to apical phenotypes. Additionally, certain modes of action may not be represented by transcriptomic changes if the mode of action is not regulated at the transcriptional level. Next slide. I briefly want to show where these transcriptomic points of departure fall relative to apical points of departure. So using the formulas in the hazard technical support documents to account for the duration of exposure and species, EPA calculated human equivalent doses and are highlighting here where our selected 5th percentile combined MSIG-DB superset transcriptomic point of departure for liver compares with the apical points of departure. You can see that the transcriptomic point of departure in the teal dashed line of 8.26 milligrams per kilogram per day is 25% below the apical points of departure shown in the black lines of 11 and 12 milligrams per kilogram per day, demonstrating that this was a successful application of transcriptomics to derive a point of departure consistent with apical values, but able to detect those molecular changes earlier than phenotypic outcomes. Dr. Keith Jacobs, who will present next, will contextualize this plot a bit more in the hazard portion of the presentation, but I do want to highlight that the selected transcriptomic point of departure, the 5th percentile of the distribution of combined MSIG-DB supersets that falls just below the inflection point, also falls just below the apical PODs that were determined from other studies. Next slide. Similarly, in the lung, the 5th percentile of the distribution of combined MSIG-DB superset BMDL medians, again the teal line shown here, of 0.015 parts per million, when converted to a human equivalent concentration, falls just below the inflection point and is consistent with apical POD values shown in the black lines of 0.014 and 0.02 parts per million, despite those being derived from nasal epithelium and the transcriptomic point of departure being from a different part of the respiratory system in the lung. Next slide. That concludes my technical presentation. I'd like to thank you for your attention and take any clarifying questions.
Thank you very much for that really nice presentation. Now we'll turn it to the committee for questions. And I see Dr. Ottinger has her hand first.
Yeah, this may be jumping ahead, and so if so, I'm fine with waiting. But I was curious about, first of all, I think this approach is great, and I agree with the super gene consolidations that you've come up with. Is there any way to predict long-term effects, given that maybe some of those genes may be slower in response or not quite as robust? And also conversely, some of these acute tests might, in a physiological sense, a whole animal kind of approach, be more transient. So how do you integrate those kinds of effects into this model?
Thank you for those questions. For the first question, you asked if there is the hope of being able to predict long-term effects from these exposures. So that is an active area of research, both in the agency and lots of external bodies. It's something we hope to build more confidence in, but I do not think there is confidence in the current presented results for how that would work. That is something that is a very active, ongoing area of research.
Absolutely fair, and I suspected that, but I appreciate your response.
Can you repeat the second question?
So in some of the other charge questions that I reviewed, there were some examples of acute tests in whole organisms, and some of the inflammatory responses and other kinds of responses turned out to be somewhat transient. And so I'm just basically asking for acknowledgement or validation that this is intended as a short-term acute responsive kind of screen.
Yes, that is correct. Okay. There is evidence that these transcriptomic points of departure can be predictive of those longer-term effects, but it would have to be demonstrated. And
exactly, so, part of the validation.
That's not what we are stating. We are instead stating that we are picking up those early signatures using transcriptomics.
Which I think is great. I just wanted to clarify. Thank you.
Thank you.
Dr. Wolf.
Yeah, two things. One, I just want to respond to Dr. Ottinger on the goal of these activities is protection, not prediction. The rodents don't predict humans, and so we're using rodents here as well. So I think identifying protection goals is very laudable.
No controversy there, Doug. That wasn't my intent.
Yeah. So the other question I have, and we'll get more into detail when we deal with charge question 1, but I'm curious about your decision to use the chamber concentrations for your x-axis. NIHS did a wonderful job of determining blood concentrations and tissue concentrations. And it seemed to me you had a great opportunity, particularly in the liver, where there's quite a bit of difference in the tissue concentration between the rat and the mouse, to really lay that out better and explain those based on, the true toxicodynamics, how the chemical acts on in this case, the organ. And since you had tissue concentrations, did you look at that and decide that wouldn't work, or have you not actually done that analysis that way?
Thank you for that question. Yes, when we received these data, we did not yet have the internal dosimetry, and so all of these analyses were performed prior to receiving those data. We are interested in how the dosimetry would affect these outcomes, and that is something we are continuing to explore. But at this time, the analyses presented are with the nominal concentration. That's correct.
Okay, yeah, we'll go into more discussion about that when we get to Q1 and others. So thanks.
Thank you. Dr. Shao.
Thank you. Could you go back to slide 32?
Can you repeat the slide number?
32, yes.
Oh, perfect.
So when you explain the each dot, so I want to understand. So one dot is a gene set, and then in this gene set there are multiple genes, and for each gene you calculate the BMD or the BMDL.
This is the BMDL of each gene.
So you calculate the gene of the BMDL of each gene, and then so if there are multiple genes in that gene set, then you calculate the median of those BMDL.
That is correct, and I just want to say there have to be at least 3 genes for us to include that gene set in the analysis.
Okay. So that's just want to clarify. And then there's I think 2 slides. I don't remember the exact number, but it should be between 40 and 50. So you considered 2 different scenarios, and you mentioned like a right and the left. So can you go to that 2 slides and explain that a little bit?
Yes, that should be a few slides forward from here. I think it's the next slide after a couple more. There. This would be the left and right shift, yes. Would you just like me to explain these again?
Yeah, so what is those 2 scenarios you demonstrate here?
So the mechanism-informed terms are selected based on the literature review for these chemicals. And so this is assessing how well that selection represented the full landscape of toxicities across the distribution of responses. And so if these superset terms fall along the full landscape perfectly, we are saying that our selected superset terms represented the full landscape of toxicities from lowest, most sensitive to highest, least sensitive outcomes. When there's a left shift, we would interpret that as it only detected some of the most sensitive toxicities and not those terms that would be occurring at higher exposure concentrations. And if there were a right shift, we would interpret that to be the opposite, that it is only picking up on the toxicities that happen at higher exposure concentrations, that the terms we have selected were not representative of the full landscape.
Okay, all right. Thank you.
So this is George Cobb. I have a follow-up on that. Why do you need to know that if you're looking for health protective responses? I mean, if it's only responding at the lowest concentrations and it's maxed out at the concentrations that are observed in the environment, then it's maxed out at the concentrations observed in the environment. Are you looking to get multiple different endpoints to evaluate?
I was saying that I consider this as more of a quality assessment metric, that we are seeing how well our superset terms performed against the full landscape of effects, and it is informative to know rather than it being an exclusion criteria. If it doesn't fit along the curve perfectly, that would still need to be taken into account by the risk assessment team. So I was instead saying this is more of a metric of, do we capture the full landscape of effects, yes or no?
Okay. Thank you very much, and I'm sorry for interrupting, but I thought that was a flow of conversation. Dr. Rager.
Thank you, and thank you, Thomas. I have 2 questions. The first of which, could you please comment on the decision to use whole body inhalation exposures as opposed to nose only inhalation? And then secondly, can you please comment on the decision to use S1500 gene sets that include approximately 2,000 genes? Can you comment on their degree of coverage across the gene sets in the superset? And in terms of the superset gene set identifications, these are reliant upon you thinking you know the chemical mode of action. Can you comment on the degree of confidence you have in capturing all pathways involved in this chemical toxicity?
There's a camera on. Don't turn the camera. Yeah. So I would sit down.
Okay. Yeah. So, and one of the things I would say is there's another expert online here, Georgia Roberts, who actually leads the actual contractual capabilities that design these studies. Oh, I apologize. My name is Scott Auerbach. I am from NIEHS, Division of Translational Toxicology. So typically and historically, NTP has carried out, or DTT has carried out exposures from an inhalation standpoint to whole body exposure as opposed to nose only inhalation. These are, again, related to the engineering of the systems that we have available to us through the contractual capabilities at Patel. I would like to defer if Georgia is online to further clarify additional reasons why there's a preference for whole body exposure. Georgia?
Hi, this is Georgia Roberts. I'm also with the Division of Translational Toxicology. Scott, I don't have much to add other than, historically speaking, the whole body exposure route has been, I don't want to say default, but more of our standard, while the nose only was used for exceptions, whether it be an exposure scenario, high human potential toxicity, or selected particulate exposures. So in general, whole body is the route that we would select over nose only.
Right. Thank you for the response. Dr. Gotti.
I think it's on the S1500.
Sorry, can we return to the S1500 question? Sorry, I had two. Can you comment on the coverage of the S1500 across the superset gene sets that you created?
Thank you. This is Thomas Jackson from EPA again. So for the first question you asked about the S1500, was the degree of coverage across genes in the supersets, was that correct?
Correct.
Yes, so there was a high degree of coverage across genes in the superset, and some of that is reported in the transcriptomic support document where we specifically created plots and did analyses to determine how much coverage there was there. I do want to reiterate that the S1500 Plus does have a high degree of concordance with the full transcriptome when it comes to MSigDB coverage. That has been determined to cover more than 90% of gene sets. It's just with fewer probes in each of those terms. But yes, there was a high degree of coverage. The specific numbers are reported in the document, but I don't remember them off the top of my head.
Thank you. Now, Dr. Gotti.
Thank you. And Thomas, this is really interesting. And I'm going to go back to the basics of drug discovery because they've always struggled with a classical problem of translation of these effects. And studying transcriptomics at an acute level can be overly conservative from a risk assessment, hazard assessment standpoint. Could you comment on both the correlation of this into proteomics and application into risk assessment and hazard assessment overall?
Thank you for that question. Yes, so our decision to include transcriptomics in these assessments was an important one for how we decided to determine that these were not picking up just overly sensitive changes. And for those reasons, we wanted to come up with these mechanism-informed ways of tethering the transcriptomics back to apical phenotypes. So that was the superset terms were created to do that. And what we saw that was quite striking here was that those results actually aligned very nicely with some of the more sensitive outcomes, but also with the apical effects. And so we do not expect that it would always come out that way, but in this fit for purpose analysis, we found that the tethered analysis to mechanism-informed terms were aligned with those outcomes.
Excellent. Thank you. Dr. Gentry.
There were a couple of slides where you talked about the justification of the 5th percentile and using it. You're comparing both the rat and the mouse. You use the term just below the inflection point. And I think in those two slides, I mean, the placement on the curve is very different. So can you talk a little bit more about that and kind of what you mean by just below, because they seem to be in very different spots along the curve?
Thank you for that. Yes, so that term is not an incredibly specific term, and I apologize for that vagueness of saying just below. The point I was trying to make is that we were seeing relative consistency across these databases, although there is always different performance of the different databases and of the different techniques. And so I was highlighting that those were relatively consistent and that they were coming up generally below the inflection point on the curve. But you are correct, they were not always within that small portion of the curve. And we did see that typically the combined superset term was actually the most consistently at the closest point to the inflection point, which was also part of our reasoning for selecting the combined superset term of the 5th percentile of the distribution.
Which slide number was that? Which slide was that? Which slide number?
It was near the end. I think your answer is related to within species. What I was speaking to was the pretty big difference across species that you could see in the 5th percentile.
You're saying in mouse versus rat?
Yes.
Yes, okay. So there is a large difference. And actually, if you pull up the table, it would be one of my final few slides of that presentation. You can see that there is a wide difference between mouse and rat. And I do want to reiterate a point that was made previously, that we do use nominal concentrations. And so we cannot speak to whether these differences between mouse and rat are due to the nominal exposure concentrations or due to a true potency difference within the tissues. But it could be either of those that is causing this difference between species. But here you can see that across methods, mouse was always more sensitive than rat in all tissues.
Right, but again, you're using support for the 5th percentile within a species. You're using that term near the inflection point. But if you look at that in the mouse versus the rat, where you are on that curve is very different compared to the inflection point.
That is a fair point. Thank you for that.
Okay, Dr. Ottinger.
I promise very quickly, following up on that and following up on the earlier comment that Doug made, I wondered if your next steps may be to consider conserved mechanisms in response and even take advantage of the receptor screens that Earl Grey and others have done over the years that would give you insights into where there may be commonalities across species and even classes of organisms to generate these superset genes to be able to then get at least an overview of what might be responsive.
Thank you for those suggestions.
Other questions from the committee? I actually have
Dr. Cubby, you're muted.
Yeah, you
I
muted
clicked
yourself.
twice. I'm sorry. So I was asking if the committee had questions, and then I have a question if there are no more for the committee. And my question is on slide 49, and it's very minor question, I think. Yeah, there was a discussion that values 1, 2, and 3 are in close proximity, and that's not the case in my book. But what is that value number 2? I mean, what's the numerical value for that guy? Or
So,
approximate numerical value for that guy?
I would need to go back and reference those specific data. But I will say this is an example of where choosing the single lowest point could result in something that may or may not be relevant. And so this was part of our justification for moving towards a 5th percentile approach, was to try and avoid some of these potentially spurious further shifted points that would not have occurred if we had selected a different database.
Yeah, I'm simply trying to figure out what you guys are saying are in close proximity or reasonably close doses, because that looks like to me it might be a couple of orders of magnitude difference.
Yes,
between
this is a
2
fairly
and 3.
meaningful difference. This is a fairly meaningful difference, and I was more trying to emphasize that there is consistency more in the 5th percentile versus in the lowest on this slide specifically.
Okay.
Thank you.
Fair enough. All right. So if there are no other questions from the committee, first of all, thank you for this presentation and for answering our questions. And we can continue on to the non-cancer with Dr. Pepperell. No, it's Dr. Jacobs again.
Hello, my name is Keith Jacobs, and I will present the non-cancer assessment for ortho or O and para or P dichlorobenzene. Next slide. Here is an outline of the non-cancer assessment that I will present for both chemicals. I will begin with o-dichlorobenzene. I will first lay out the evidence for the 2 key endpoints of respiratory toxicity and liver toxicity. The next slides will describe how EPA selected transcriptional PODs and selected hazard values from among co-critical POD options. P-dichlorobenzene will then be presented following the o-dichlorobenzene summary. Next slide. The human health non-cancer assessment for o-dichlorobenzene is relevant to charge question number 3. Next slide. EPA organized the human health assessment by administration route. For inhalation, the most consistently observed and relevant effect was respiratory toxicity, specifically damage to the nasal olfactory epithelium. Adverse effects were generally not reported in lung or other respiratory tissues. In one study, ZISU 1995, mice were exposed to 64 or 163 ppm o-dichlorobenzene for 4, 9, or 14 days. This study was limited because it only qualitatively reported the presence of histopathology with associated severity scores, without any incidence data on how many mice were affected. Regardless, very severe epithelial damage was reported at 4 days, with severity decreasing at 9 and 14 days, suggesting recovery or adaptation over time. In a more recent OECD 413 study identified after the initial 2019 literature search, Cho et al. 2023 exposed mice to 30, 60, or 120 ppm o-dichlorobenzene and reported multiple signs of nasal histopathology with effects seen at all doses without a noticeable dose-response trend. At all concentrations, severity was less severe than reported in Zissou 1995. In considering the data from these two studies together, EPA concluded that there is a consistent inverse duration response, and repeated exposure does not lead to an accumulation of effects. Therefore, a single POD for respiratory toxicity is applicable to all exposure durations. Next slide. Liver effects were consistently observed across less than chronic durations, species, and routes. These most commonly included increased serum ALT, increased liver weight, and necrosis, with other histopathological indications also reported. Liver effects were considered for assessment of oral and dermal exposures because respiratory toxicity is the most appropriate endpoint for inhalation exposures. Beginning with the oral data, Umamara et al. 1996 exposed rats to a single oral dose of 120, 200, or 300 mg per kg o-dichlorobenzene with increased serum ALT, observed at or above 200 mg per kg, and necrosis at 300 mg per kg. Interestingly, this same study also tested the P isomer and did not observe any indication of liver toxicity from acute exposure. Robinson et al. 1991 observed increased serum ALT and liver weight following either 10 or 90 days of oral exposure. Histopathology was also observed at the only dose it was measured. NTP 1985 had 13-week and 2-year studies in the publication. Liver effects, including histopathology and increased liver weight, were reported at 13 weeks in both species and sexes. The 2-year study did not observe any histopathology, while liver weight was not tested at lower maximal doses. The 2025 NIEHS study that was used for transcriptional analysis also reported apical data following 5 days of inhalation exposure, with similar responses as other studies seen from serum ALT and liver weight. Overall, there is generally a flat duration response with similar outcomes and hazard values reported across durations. Next slide. The previous presentation laid out each of the 6 different options for TPOD derivation. I am showing them again here. Next slide. For application to the risk evaluation, EPA decided to focus on the TPOD options from the MSIG-DB combined supersets. These supersets are associated with cellular damage processes and are more likely to represent transcriptional markers of adverse outcomes. They are further supported by mechanistic data indicating a role for oxidative stress and inflammation in liver toxicity, with apoptosis and oxidative stress markers activated in lung tissue. Using the combined superset avoided bias towards any individual mechanism and increased the statistical power. Next slide. EPA also determined that TPODs for mice were most relevant to align with available data from acute and short-term apical studies on respiratory and liver toxicity. Finally, the 5th percentile result was selected to reduce the influence of potential outlier gene responses and for consistency with other EPA statistical approaches. Next slide. These TPODs were then duration and dosimetrically adjusted in the same manner as the apical PODs. Specifically, the original hazard values were converted to human equivalent concentrations, or HECs, by adjusting to continuous exposure and accounting for dosimetric differences between animals and humans. The NIEHS study did not examine nasal tissue, so for comparison with apical respiratory toxicity PODs, the same dosimetry based on the extrathoracic region was also applied to lung TPODs. It would be expected that nasal TPODs would be even more sensitive, given that adverse effects were not seen in lung. This was not an issue for liver TPODs, which were from the same organ as the apical outcomes. However, route-to-route extrapolation was required for comparison with the PODs from oral studies. When deriving to continuous HECs and daily human equivalent doses, or HEDs, the respiratory TPOD HEC is 0.45 ppm, and the liver TPOD extrapolated to an oral and dermal HED is 8.26 mg per kg day. Next slide. This is the same graph shown in the previous presentation, copied here to visualize where the three co-critical hazard values for respiratory toxicity fall along the curve of gene set activation. These values fall on the lower end of the curve, suggesting that nasal tissue necrosis corresponds with the relatively more sensitive, but not the most sensitive, range of gene set activation. The next slide will describe how these co-critical PODs were derived. Next slide. For assessing inhalation risk, EPA compared 3 potential HECs among the lung TPOD, the ZISU, lowest observed adverse effect concentration, known as LOAC, and the CHO, LOAC. When accounting for differences in uncertainty factors, the resulting hazard values differ by less than 50% across the 3 options. EPA does note a clarification in these hazard values from the draft hazard assessment. The updated values are shown in the table above. However, the relative ratio is unchanged from the values that were shown in the draft assessment. While the lung TPOD represents a different part of the respiratory tract, the lung TPOD HEC of 0.45 ppm with a UF of 30 was selected for use in risk estimation because it has the additional precision of being derived from a BMDL and reduced statistical uncertainty because an additional UFL was not required. This value will be applied to all exposure durations. EPA has robust confidence in this value based on the co-critical values from the other studies. Next slide. For liver effects, multiple apical endpoints were successfully BMD modeled from across the 4 relevant studies, covering various measures of increased liver weight and serum ALT. The table here only shows endpoints with adequate modeling fit. However, EPA attempted to model additional endpoints as well. Next slide. Like before, the gene set rank graph here shows all 3 co-critical liver PODs. All 3 values fall just below the inflection point of the graph, above which significant toxicity would be expected as numerous gene sets are activated. Next slide. Similar to the inhalation route, the 2 apical BMDLs together with the NIEHS TPOD HED were considered co-critical for liver toxicity. As visualized on the previous slide, the 3 POD options vary by only 25 to 30% among them, despite covering different routes, durations, and species. Among these options, the HED of 11.0 mg/kg/day from Umamara in 1996 was selected for use in risk estimation for all durations because it represents clear adverse outcomes from a single exposure and is a refined hazard value resulting from BMD modeling. As with the inhalation POD, EPA has robust confidence in this value because it is supported by co-critical PODs from 2 other studies. Next slide. I will now present the non-cancer assessment for p-dichlorobenzene. These slides are pertinent to charge questions 7, 8, and 9. Next slide. For the outline of p-dichlorobenzene, the slides will begin describing acute POD selection and BMD modeling, followed by options for intermediate exposures, and finally, discussion of potential dermal assessment approaches. We also have a slide on chronic inhalation POD value. Next slide. P-dichlorobenzene has been previously assessed by multiple governmental entities across the US and internationally. Generally, key endpoints are very consistent across assessments, especially for repeated exposures. EPA notes that the draft EPA IRIS and ATSDR assessments covered both O and p-dichlorobenzene, but as just presented, the o-dichlorobenzene assessment utilizes much newer studies. For OPPT's p-dichlorobenzene human health hazard assessment, EPA prioritized the use of guideline or guideline-like studies submitted to EPA and used as part of the 2018 Office of Pesticide Programs risk assessment. The 2006 ATSDR toxicological profile was also important for identification of key studies and for providing supporting information. These key studies were supplemented through a broad literature search, along with the 2025 NIEHS 5-day inhalation study. EPA concluded that the resulting non-cancer database was complete because it included studies covering all exposure routes over 4 animal species and a diversity of study designs. Updated literature searches were targeted to cancer information to support the mode of action and human relevance analysis for cancer to be discussed in the next presentation. Next slide. This slide summarizes the non-cancer PODs for p-dichlorobenzene. Across durations and routes, EPA utilized PODs covering neurotoxicity, developmental toxicity, respiratory toxicity, and liver toxicity. The key hazard outcomes in studies are largely consistent with conclusions from the prior governmental assessments, aside from the acute oral POD obtained from a translated German study and the additional consideration of intermediate and dermal scenarios. These differences are the primary subjects of the 3 charge questions relevant to p-dichlorobenzene non-cancer toxicity. Next slide. Beginning with the topic for charge question 7, Bornadowitz et al. In 1994 is an OECD 416 2-generation study. However, only the peer-reviewed academic publication with summary data is currently available. The study presented various fetal outcomes, including postnatal mortality, reduced pup weight, delayed developmental benchmarks, and diminished neuromuscular reflexes. Postnatal mortality and delayed eye opening were identified as the most reliable and representative endpoints for POD derivation. Postnatal mortality was not reported on a per liter basis, which is recommended by EPA guidelines for developmental toxicity risk assessment. As a result, the study was rated high for other endpoints, but only medium for postnatal mortality. Next slide. As part of EPA's BMDS benchmark dose modeling suite of tools, the agency has used an approach known as the Rao-Scott transformation that can account for litter effects in the absence of individual animal or litter summary data. The Rao-Scott transformation is a validated statistical method that simulates a nested dataset as would be obtained if individual pup data were available. The transformation approximates the expected intralitter correlation associated with developmental toxicity study design. Postnatal mortality is an irreversible binary outcome that is considered applicable to acute exposures, consistent with EPA guidelines for developmental toxicity risk assessment. EPA determined that both F1 and F2 outcomes were relevant to acute exposures because p-dichlorobenzene is not bioaccumulative and does not show evidence in other studies of increased sensitivity across generations. Next slide. 3 PODs were successfully modeled from the Bornadowitz dataset, F1 delayed eye opening, and day 4 dead pups from each generation. Other options included route extrapolation of the acute inhalation POD for neurotoxicity from Monsanto in 1994, similar postnatal mortality outcomes from Chemical Manufacturers Association, or CMA, 1989, and sensory irritation in humans from Hollingsworth, 1956. Each of these options were considered either less reliable for acute exposure or were insufficiently supported by the weight of scientific evidence. Therefore, EPA selected the BMDL of 17.6 mg/kg/day for F2 dead pups as the acute oral POD because it's the most appropriate representative value of an irreversible severe adverse outcome relevant to acute exposure. Next slide. Charge question 8 considered the approach EPA took for intermediate inhalation exposures. EPA considered 4 high-quality studies for intermediate inhalation PODs. The 13-week study, ACE of 2005A, was not selected because the observed liver effects in rats suggest adaptation instead of adversity, consistent with the database overall, which did not show strong evidence of non-cancer liver toxicity via any exposure routes in rodents. The 3 remaining high-quality studies of Bushy Run 1992, Biodynamics 1991, and CMA 1989 were all selected for dose response analysis. Each of these studies are high quality. However, there are significant uncertainties associated with the dose response results that preclude selecting a single representative value. The 2-generation reproductive toxicity study in rats, CMA 1989, had uncertainty in analytic quantification of the air concentration, which may have biased the POD higher than it should have been. Additionally, it is unknown whether dead pups at 4 days post-birth are due to exposure or if they were cannibalized for other reasons. EPA assumed the most conservative option that all deaths were associated with exposure when selecting a putative POD. The 10-day developmental study in rats, Bushy Run 1992, has a no observed adverse effect level, or NOEL, for reduced maternal weight lower than the BMDLs from the CMA study, even though CMA 1989 had stronger evidence of maternal toxicity. This indicates that the NOEL from Bushy Run may not be representative. Biodynamics 1991, a 28-day study in dogs, used only an N of 2 animals per sex, and while the outcomes and PODs are very consistent with the other dog studies, there is still substantial quantitative uncertainty in a POD based on 2 animals. Overall, EPA has moderate confidence that these options represent the upper and lower bounds of intermediate hazard values for risk screening purposes, but only slight confidence for any specific value. Therefore, the range of 10.4 to 46.8 ppm was proposed for use in risk screening, if needed, in the risk evaluation. Next slide. Olfactory epithelial lesions in rats, specifically increased eosinophilic globules, were identified as the most sensitive inhalation endpoint and the basis of the chronic HEC. Selection of this endpoint is consistent with prior assessments by ATSDR, the EPA Office of Pesticides, and Cal EPA. The endpoint is corroborated by adverse respiratory effects reported across the database, including in a cross-sectional human study and for the isomer o-dichlorobenzene, as previously discussed. EPA assigned moderate to robust confidence for the selection of this endpoint and the resulting POD value. There are some uncertainties, however, in applying this POD to humans, as human and rodent nasal architecture differ significantly. In using default human dosimetric adjustments, the resulting HEC assumes that humans receive a higher dose in the extrathoracic region per surface area. But rodent nasal passages are convoluted with branched turbinates that are more complex than humans and may result in a more complex deposition pattern than a simple breathing rate to surface area ratio would suggest. Additionally, the rat olfactory nasal epithelium is thinner and is larger relative to the size of the nose. The HEC for this endpoint is approximately 100-fold more sensitive than the acute inhalation POD, and over an order of magnitude more sensitive than the intermediate POD options. For these reasons, EPA is seeking SACC comment on EPA's characterization of the endpoint and the POD derivation for this endpoint. Next slide. EPA considered 2 approaches for deriving dermal PODs, the subject of charge question 9. In the draft hazard assessment, EPA ultimately decided to extrapolate across routes from the robust oral POD from Monsanto in 1996. For risk estimation, this POD will be compared to dermal exposure estimates that incorporate either fractional absorption or maximum flux rate obtained from empirical data. Alternatively, Appendix M of the hazard assessment presents an approach for certain exposure scenarios using a 21-day dermal study in rats, referred to as Biodynamics 1990, that did not observe any effects at the highest dose of 300 mg per kg day. Benefits of this approach would be that using a dermal study avoids the need for extrapolation across routes or for adjusting exposure values for absorption, and it would result in risk estimates within a few fold of the default approach. For context, based on this study and other considerations such as expected absorption and use scenarios, EPA's Office of Pesticide Programs qualitatively ruled out dermal risk in their risk assessment. This approach was ultimately not selected because it would require risk estimation using a POD based on the absence of any effects. It is also questionable whether a 21-day exposure in rats, which did not demonstrate organ-level toxicity via any route, are representative of the effects seen in dogs. Additionally, it would not account for acute developmental toxicity and could not be applied to flux-based exposure scenarios. So additional dermal PODs adapted from other studies would be required. For these reasons, EPA decided to utilize the oral data from Monsanto 1996 for all dermal exposure scenarios. Next slide. Thank you. I can now answer any clarifying questions on the non-cancer assessment for O and p-dichlorobenzene. Following questions, we will move to the cancer assessment presented by Dr. Abhilash Sasidharan.
Excellent. Thank you for that presentation. So are there questions from the committee? Dr. Gentry.
I just want to make one comment and make sure I understood this, but it looks like you're linking to apical endpoints for orthodichlorobenzene that aren't typically considered adverse, like changes in liver weight, changes in serum ALT, where for para-dichlorobenzene, you're clearly linking to apical endpoints that are considered adverse.
Keith Jacobs, EPA. We are using the same endpoints for both ortho and para. At EPA and OCSBP, we consider liver effects adverse when we see multiple signs of potential adversity. So it would have to be liver weight combined with serum ALT or combined with histopathology. So as I mentioned, that's why we did not use the value from the ASO 2005A study, because we only saw liver weight. However, in all of the studies that we are using, there's multiple indications. Usually we have all three. We might have specifically used the modeled number that came from liver weight or the modeled number that came from ALT. But in the actual study, we see those effects at the same doses.
Okay, thank you.
Good conversation there. Dr. Ottinger.
Just a quick question. With the Scott transformation and the expression of mortality per individual versus per litter, is there any concern about gender or consideration of that? Gender differences?
Keith Jacobs, EPA. Gender differences are not a part of the modeling, but the male, I believe the study did not separate in the summary data we have, did not separate.
That's what I read, but I just didn't know if that was any cause for concern.
Right. It is an uncertainty that we only have summary data, which includes summary of pups overall and summary across litters, across genders.
Right. Thank you.
Excellent. So I do have one question. This is George Cobb. On slide 58, and I don't know that you necessarily need to go back to it, you were describing severe tissue effects, and that was pretty clear. Are you then the information on slide 77, is that what you're calling the tissue lesions, severe tissue lesions, or is it something else on slide 58?
So if 58 is for ortho-dichlorobenzene, we're primarily using the necrosis and atrophy for ortho. In para, we're using inflammatory lesions like eosinophilic globules, but we do also see eosinophilic globules in the same CHO 2023 study.
Yeah.
They're less sensitive, and that's not what we're using for the actual value, but you see the same inflammatory lesions in both, which is why we cross-referenced that it's consistent.
Excellent. Yeah, thank you for that clarification, and I do appreciate that. So if there are no other comments from the committee, I think we should probably take like a quick 10-minute break, and then we'll come right back for the closeout of this session and questions before lunch. Okay, welcome back. If EPA is ready, we can continue to our next presentation. You can proceed whenever you are ready.
Thank you, Dr. Gob. My name is Abhilash Shashidharan, and I will present the cancer hazard assessment for p-dichlorobenzene and o-dichlorobenzene. Next slide, please. Here is an outline of the presentation. For p-dichlorobenzene, I'll review the existing agency classifications, the human and animal evidence, the genotoxicity profile, and the constitutive androstenedione receptor or CAR-mediated mode of action. My colleague Derek Haggett will present the transcriptome support for key event 1, and I will then discuss the remaining key events and EPA's proposed cancer classification. Following that, I'll present the cancer hazard evaluation for o-dichlorobenzene using the recap framework. I'll begin the p-dichlorobenzene assessment by reviewing why different agencies have historically disagreed on its cancer classifications. Next slide, please. As you can see, agencies reached divergent cancer classifications despite evaluating the same mouse liver tumor data. IARC, ECCA, NTP, and a draft iris assessment all identified p-dichlorobenzene as a potential carcinogen based on rodent tumor findings. In contrast, Australia's NICNAS concluded the mouse tumors were not human relevant because of species differences in metabolism. EPA's Office of Pesticide Programs classified it as a not likely to be carcinogenic based on a mitogenic MOA, though it considered carcinogenic effects plausible in humans above a threshold dose. TCEQ concluded the existing database was inadequate. The fundamental disagreement is not about the tumor data itself, it is about whether a mode of action has been established for these tumors, and if so, whether it is relevant in humans. Resolving this uncertainty was the central objective of this assessment. The bottom row shows preliminary conclusion from this assessment. P-dichlorobenzene is not likely to be carcinogenic to humans. This is based on a non-genotoxic car-mediated mode of action that is not relevant in humans. In the following slides, I'll present the scientific evidence supporting this conclusion, specifically how EPA applied new mechanistic data to address the long-standing cancer classification uncertainties for p-dichlorobenzene. I'll begin with the existing human and animal evidence for p-dichlorobenzene. Next slide, please. Regarding human data, we reviewed 22 epidemiology studies, including 6 focused specifically on cancer outcomes such as non-Hodgkin lymphoma, retinoblastoma, brain tumors, and endocrine-related cancers. None of these studies established a causal relationship with any specific cancer type. Overall, the human evidence does not support a causal association with cancer. Moving to the animal data, 2 chronic biopsies demonstrated dose-related hepatocellular adenomas and carcinomas in mice across both sexes and routes. Notably, these liver tumors were entirely absent in rats at any dose or route. We also evaluated other tumor findings, including lung, thyroid, and adrenal tumors. However, we determined they are not treatment-related because they lack a dose-response relationship and fall within historical control range. Therefore, only the mouse liver tumors are considered treatment-related. We will examine these mouse liver tumor findings in greater detail on the next slide. Next slide, please. Hepatocellular adenomas and carcinomas were consistently observed in both sexes of mice following inhalation and oral exposure. At the highest doses, liver tumor incidences ranged from 70 to 90% across routes. However, no liver tumors were observed in rats at any dose or route. To determine whether these mouse-specific tumors are relevant to humans, we must evaluate the underlying mode of action. We begin by evaluating genotoxicity because ruling out direct DNA damage is an essential step in establishing non-genotoxic mode of action. Next slide, please. As mentioned, to determine whether the mouse liver tumors are driven by direct DNA damage, we reviewed the genotoxicity evidence from existing assessments. As the table shows, standard guideline compliant assays do not indicate genotoxic potential for p-dichlorobenzene or its primary metabolite. Bacterial reverse mutation, mammalian gene mutation, chromosomal aberration, and micronucleus tests are all negative. While there are a few isolated positive findings from non-standard assays, they have not been consistently reproduced. Importantly, transcriptomic data at the oral tumorigenic dose clustered with non-genotoxic hepatocarcinogens rather than DNA reactive agents. Therefore, the overall weight of evidence consistently rules out a genotoxic mode of action, pointing instead to a receptor-mediated pathway. We will examine that mechanism on the next slide. Next slide, please. This slide outlines our proposed CAR-mediated mode of action. New mechanistic and transcriptomic data have identified CAR activation as the molecular initiating event. CAR is a nuclear receptor that regulates hepatic gene expression. As shown in the pathway diagram, we used the OECD Adverse Outcome Pathway 107 framework to map out the sequence. In mice, CAR activation leads to CAR-dependent gene expression, sustained hepatocyte proliferation, pre-neoplastic changes, and ultimately tumor formation. We evaluated this pathway under EPA's 2005 cancer guidelines and the IPCS human relevance framework. In the following slides, I'll present the evidence supporting each of these key events, starting with CAR activation. Next slide, please. As mentioned, new mechanistic evidence confirms that p-dichlorobenzene acts as a CAR activator across mouse strains following oral exposure. This CAR specificity is supported by two independent lines of evidence. First, through knockout validation. Mice lacking both CAR and PXR, the pregnein X receptor, showed no CYP2B10 induction, whereas both wild-type and humanized mice showed strong activation. Second, through receptor selectivity. We observed robust induction of CAR marker CYP2B10 alongside negligible induction of PXR marker CYP3A11. This confirms CAR-specific activation with minimal PXR contribution. In rats, however, this CAR activation is substantially weaker, less consistent, and occurs only at higher concentrations. To further characterize these CAR-linked gene expression changes, a 5-day inhalation transcriptomic study was conducted. I'll now turn it over to Derek Haggard, who will present the transcriptomic evidence.
Thank you, Abhi. My name is Derek Haggard from the Risk Assessment Support Division that provides research support to OCSPP. I will be presenting a brief summary of the 5-day NIAHS transcriptomic study supporting the proposed mode of action for para-dichlorobenzene. As a reminder, OPPT requested the NIAHS perform a 5-day inhalation transcriptomic study in healthy adult female mice and rats exposed to either ortho or para-dichlorobenzene. 5 putative target tissues of liver, heart, ovary, kidney, and lungs were collected, and changes in gene expression were measured using targeted RNA sequencing with the TempoSeq S1500 Plus assay. As highlighted previously by my colleague, Dr. Thomas Jackson, there are many ways to analyze transcriptomic data depending on research goals or specific use cases. Now, given the results of mechanistic studies which demonstrate that canonical CAR-responsive genes are induced in mouse liver following oral exposure to para-dichlorobenzene, EPA wanted to examine whether a similar CAR gene expression response was observed in the 5-day NIAHS inhalation study, which would provide additional support for the proposed molecular initiating event of CAR activation within the livers of mice and rats. To this end, EPA leveraged existing data from mechanistic studies and published biomarker sets and investigated whether there were concerted changes in the expression of a small representative set of CAR biomarker genes to confirm CAR activation in the 5-day inhalation study and to determine whether species differences exist between mice and rats. Next slide, please. EPA identified 3 genes known to be responsive to CAR agonists in mice: CYP2B10, CYP2C55, and CDC20. The gene CYP2B10 in mice is a highly inducible liver cytochrome P450 that serves as the primary biomarker for activation of CAR. In humans, the functional analog for this gene is CYP2B6, and both mouse and human analogs are strongly induced by phenobarbital and other CAR agonists. Furthermore, mechanistic studies have found that oral exposure to para-dichlorobenzene strongly activates this gene in mice. CYP2C55 is predominantly expressed in colonic epithelium, but also acts as a marker for hepatic CAR activation and was shown to be upregulated in response to oral exposure to para-dichlorobenzene in mice. And although there's not a clear functional analog to this gene in humans, members of the human CYP2C cluster are critical for drug metabolism and are known to be induced by CAR. And lastly, CDC20 is a well-conserved gene across species that plays an important role in cellular proliferation. Activation of CDC20 by CAR has been hypothesized to play a role in later key events of CAR-mediated liver tumor agenesis and is thought to be involved in key event 2 of sustained hepatocyte proliferation. Next slide, please. Analyses of these 3 CAR biomarker genes showed that para-dichlorobenzene exposure causes a dose-dependent increase in expression in both mouse and rat, which suggests that this chemical does activate CAR and results in altered gene expression. When EPA compared the overall response between mice and rats, para-dichlorobenzene was more potent and resulted in a larger magnitude in expression changes in mouse compared to rat. Next slide. We further explored this potential species difference by directly comparing the fold changes between mice and rats exposed to the same nominal concentrations as highlighted here. This analysis showed that the magnitude of expression was much larger in the cytochrome P415 genes, even up to 27 times higher, and all genes were much more potent in mice compared to rats. This species difference in expression may explain the difference in tumor outcomes observed in apical studies following para-dichlorobenzene exposure. Next slide, please. As described earlier, multiple mouse liver transcriptomic studies demonstrate that para-dichlorobenzene consistently induces canonical CAR-responsive genes after oral exposure that is CAR-dependent, as highlighted by Abi. EPA's focused analysis of the 5-day NIHS inhalation transcriptomic study presented here corroborates these studies by demonstrating that genes responsive to CAR activation were indeed disrupted after inhalation exposure in mice and to a lesser degree in rats, which potentially accounts for the observed species-specific difference in liver tumor outcomes from apical studies. Additionally, the observed changes in CDC20 provides a link between CAR activation, key event 1, and downstream hepatocellular proliferation, key event 2. However, much more research is needed to determine whether long-term dysregulation of CDC20, along with other cell proliferation genes, co-occurs alongside apical endpoints from studies of longer exposure durations. And with that, I would like to thank you for your attention, and I will give the floor back to Abi, who will continue the remaining discussion on the para-dichlorobenzene cancer assessment, and I will ask to hold any clarifying questions regarding the transcriptomic analysis until the end of his discussion. Thank you.
Thank you, Derek. With CAR activation established through both molecular and transcriptomic evidence, we can now examine the downstream liver responses. Hepatocellular hypertrophy and increased liver weights are adaptive responses to increased functional demand. This is driven by CAR-mediated CYP450 enzyme induction and the expansion of smooth endoplasmic reticulum. In mice, this strong response was observed consistently across strains and study durations. At 300 ppm in the 2-year inhalation study, relative liver weights increased by 100% to 260% above controls. In rats, by contrast, these effects were substantially weaker and occurred only at higher doses, which is consistent with their reduced CAR activation. Importantly, hypertrophy itself is considered an adaptive rather than tumorogenic response. Whether the pathway progresses further depends critically on the next key event, sustained hepatocyte proliferation. Next slide, please. Sustained hepatocyte proliferation is the critical driver that separates an adaptive response from a tumorogenic one. Multiple studies demonstrate that p-dichlorobenzene significantly increases hepatocyte DNA synthesis, but without any accompanying liver toxicity. This points to a mitogenic response rather than a regenerative one. In mice, this proliferative activity remained elevated through at least 4 weeks at the oral tumorogenic dose of 600 mg per kilogram per day. Additionally, p-dichlorobenzene appears to suppress apoptosis. This combination of elevated cell division and reduced cell death creates a condition that favors the development of pre-neoplastic foci. In rats, however, the response is strictly transient, returning to the baseline by week 4 and failing to drive downstream tumorigenic events. Next slide, please. Pre-neoplastic foci are early clonal outgrowths of altered hepatocytes that bridge sustained proliferation and tumor formation. Direct evidence for classic altered foci in mice is limited, as p-dichlorobenzene has not been evaluated in promotional studies designed to capture this stage. Instead, we rely on indirect evidence from the NTP 2-year bioassay. In that study, dose-related increases in cytomegaly and karyomegaly occurred alongside liver tumors, serving as clear indicators of phenotypically altered populations. This pattern is highly consistent with observations for several well-characterized CAR activators, which also operate through this pathway even when altered foci are not directly reported. In rats, by contrast, a medium-term assay showed no statistically significant increase in GSTP positive foci. This indicates that sequence in rats is interrupted before clonal expansion. In mice, however, the pathway proceeds directly to the adverse outcome. Next slide, please. Hepatocellular adenomas and carcinomas are the adverse outcomes of chronic p-dichlorobenzene exposure in mice, observed consistently across 2 chronic bioassays. In the NTP 2-year oral gavage study, significant increases occurred at 300 and 600 milligram per kilogram per day in both sexes. Similarly, the 2-year inhalation bioassay showed clear positive trends at 300 ppm. Critically, rats do not develop liver tumors following either oral or inhalation exposure. The complete absence of tumors is consistent with their reduced CAR signaling, which is insufficient to sustain hepatocyte proliferation required for tumor formation. With the mode of action established in rodents, we next applied Bradford considerations to evaluate the overall strength of evidence. Next slide, please. The Bradford-Hill considerations provide strong support for CAR-mediated pathway. Dose-response concordance is clear, with molecular changes occurring at or below doses associated with tumor formation. Temporality is supported by logical progression from early molecular events to tumor development. Specificity is demonstrated in carnal mice, where the response is essentially abolished. Strength and consistency are evident across multiple independent studies, and the overall pattern is highly coherent with other well-characterized CAR activators. We also evaluated alternative mode of action, including genotoxicity, cytotoxicity-driven regeneration, and alternative receptor pathways such as AHR, PPR alpha, and PXR. None are well supported by the available evidence. With the mode of action established in animals, we next evaluated whether this pathway is relevant to humans. Next slide, please. We evaluated the human relevance of this pathway using IPCS human relevance framework, which asks 2 key questions. First, is the weight of evidence sufficient to establish the mode of action in animals? EPA concluded yes. Second, can human relevance be reasonably excluded based on qualitative difference in key events? EPA concluded that human relevance can be reasonably excluded based on 4 independent lines of evidence. First, receptor biology. Human CAR differs from mouse CAR in ligand responsiveness and downstream transcriptional networks. Second, human hepatocytes in vitro. CAR activators induce CYP enzymes but do not trigger sustained proliferation. Third, humanized liver models. CAR activation occurs without proliferation or pre-neoplastic lesions. And fourth, epidemiological evidence. Decades of clinical use of phenobarbital, a prototypical car activator, have shown no consistent increase in liver cancer risk. Taken together, these findings support the conclusion that CAR-mediated pathway driving liver tumors in mice is not expected to operate in humans. These species differences are shown in the next slide. Next slide, please. This cross-species comparison summarizes why the CAR-mediated pathway is specific to mice. In mice, CAR activation is strong and sustained. This drives robust gene expression changes, sustained proliferation, pre-neoplastic changes, and ultimately tumors. In rats, by contrast, CAR activation is weaker and less consistent, leading to significantly reduced gene expression changes. Most importantly, their proliferation is transient, returning to baseline by 4 weeks, which prevents any progression to pre-neoplastic changes or tumors. Finally, in humans, while CAR is present, it responds fundamentally differently. SIP and same induction occurs, but mitogenic genes are not engaged, sustained proliferation is absent, and humanized models show no pre-neoplastic lesions. Because the pathway proceeds to completion only in mice, this cross-species comparison directly informs our overall weight of evidence conclusion for p-dichlorobenzene. Next slide, please. In conclusion, the available data demonstrate that p-dichlorobenzene induces liver tumors in mice through a well-characterized, non-genotoxic, CAR-mediated mode of action. The absence of liver tumors in rats is consistent with a threshold-based pathway where rats do not achieve the level of CAR signaling required to sustain hepatocyte proliferation. Furthermore, this CAR-mediated pathway is not considered relevant to humans. The rodent proliferative sequence is not reproduced in human systems, and decades of clinical phenobarbital use show no consistent liver cancer association. Based on this overall weight of evidence, EPA preliminarily concludes that p-dichlorobenzene is not likely to be carcinogenic to humans under the 2005 cancer guidelines. This concludes the p-dichlorobenzene assessment. I will now transition to the cancer hazard evaluation for o-dichlorobenzene. Next slide, please. While the para and ortho isomers are structurally similar, the cancer database for ortho-dichlorobenzene is substantially more limited. Given this data limitation, EPA applied recap framework to systematically evaluate the available evidence. Next slide, please. For the o-dichlorobenzene cancer assessment, I will present the application of the recap framework, the existing cancer evidence, read across and mechanistic evidence, and EPA's evidence integration and conclusion. I'll begin by identifying the specific data gap that makes this framework necessary. Next slide, please. For o-dichlorobenzene, that data gap is substantial. There is no chronic inhalation bioassay, and existing oral bioassay did not reach the maximum tolerated dose. To address these limitations, EPA applied the recap framework, the Rethinking Chronic Toxicity and Carcinogenicity Assessment for Agrochemicals project, a scientifically robust, step-by-step weight of evidence framework that helps minimize new animal testing while still delivering a protective human health assessment. By integrating existing epidemiology, animal bioassays, mechanistic data, and structurally related analogs, this assessment addresses two key questions. First, is a quantitative cancer risk assessment warranted? And second, would additional bioassays be likely to change that conclusion? We began by examining the direct cancer evidence currently available for ortho-dichlorobenzene. Next slide, please. The available human epidemiology studies are inadequate for assessing carcinogenicity, primarily due to significant uncertainties in exposure assessment. In the animal bioassays, the chronic oral toxicity showed no treatment-related tumors in rats or mice. Notably, liver adenomas decreased significantly at the highest dose in mice. While earlier assessments questioned whether a maximum tolerated dose was achieved, EPA's reevaluation confirms the MTD was reached in rats based on decreased survival and body weights. Additionally, the non-neoplastic nasal and lung lesions observed in the bioassays are not considered pre-neoplastic, as no nasal tumors were reported. Historical agency classifications remain consistent with this limited database. US EPA IRIS found the data inadequate. IR classified it as Group 3, and Health Canada concluded it is probably not carcinogenic. Overall, the available data do not demonstrate carcinogenicity by oral exposure. As I mentioned on the previous slide, the lack of chronic inhalation bioassay remains a critical gap. Specifically, since the respiratory system is the most sensitive target for non-cancer toxicity. To address this specific uncertainty, we conducted a read-across analysis using structurally related analogs. Next slide, please. The read-across analysis began with a systematic screening of 1,654 candidate analogs across 19 search strategies. This list was then refined using professional chemistry expertise to identify 22 preferred analogs. We prioritized structurally matched compounds, those with a monoaromatic ring, stable carbon halogen bonds, and matching physical chemical properties such as water solubility and low curve. Critically, these analogs share the same metabolic pathways as o-dichlorobenzene, specifically CYP-mediated ring hydroxylation, and show the same rapid urinary excretion without bioaccumulation. From the 22 preferred analogs, 6 had non-cancer inhalation toxicity values and were carried forward for the read-across. Of those 6, only 3 also had the carcinogenicity data, and these 3 are the basis of our cancer comparison: p-dichlorobenzene, chlorobenzene, and 1,2,4-trichlorobenzene. With the analogs established, the next question is whether any of them show evidence of genotoxicity or a human relevant carcinogenic mechanism. Next slide, please. Both the direct evidence and read-across data strongly indicate a non-genotoxic profile for orthodichlorobenzene, with the standard mutagenicity assays generally testing negative. Regarding unlocked tumor findings, p-dichlorobenzene induces liver tumors in mice through CAR activation and kidney tumors in mice through alpha-2 globulin nephropathy. Both are well-established rodent-specific mechanisms not considered relevant to humans. 1,2,4-trichlorobenzene produced liver tumors in mice via oral exposure through an unknown mode of action. However, o-dichlorobenzene itself did not induce liver tumors in the oral bioassay. For chlorobenzene, hepatic neoplastic nodules were observed in male rats but did not progress to liver tumors. Finally, NIH's transcriptomic data show a pattern consistent with acute non-cancer toxicity for orthodichlorobenzene. These data also indicate significant CAR activation in the liver, which is consistent with a non-genotoxic mode of action. Therefore, EPA concludes the overall weight of evidence does not support a genotoxic or human-relevant carcinogenic mechanism for o-dichlorobenzene. Next slide, please. This slide summarizes how EPA integrated these multiple lines of evidence using the recap framework. First, The direct evidence for o-dichlorobenzene does not indicate human carcinogenic potential. The chronic bioassay was negative for treatment-related tumors. The available epidemiology is inadequate, and an in vitro cell transformation assay was negative. Importantly, the respiratory lesions observed in the bioassays were non-neoplastic and did not show progression to cancer. Second, the tumors observed in or read across analogs, such as the liver tumors in mice and kidney tumors in male rats, occur through well-characterized rodent-specific mechanisms that are not human relevant. Additionally, our mechanistic and transcriptomic data for o-dichlorobenzene are consistent with a pattern of acute toxicity rather than signal for chronic toxicity or cancer. Finally, regarding our non-cancer PODs, these are considered protective of potential cancer effects. No tumors were observed in the NTP 2-year bioassays at doses similar to or higher than non-cancer PODs, suggesting that tumor induction is unlikely at doses relevant to non-cancer risk. Taken together, this integrated weight of evidence allows us to bridge the inhalation data gap and conclude that no human relevant cancer hazard was identified. Next slide, please. In conclusion, EPA preliminarily concludes that the available cancer bioassay evidence is insufficient to support a quantitative cancer risk assessment under EPA's 2005 guidelines. By applying the recap weight of evidence framework, EPA did not identify a human relevant cancer hazard for o-dichlorobenzene and therefore did not derive a quantitative cancer value. We further conclude that additional chronic rodent bioassays would be unlikely to alter this determination. Finally, the proposed non-cancer points of departure are expected to be protective of potential cancer effects. This concludes the cancer assessment for o-dichlorobenzene. Next slide, please. Thank you for your attention. We will now take any clarifying questions.
Thank you for that presentation. And now we can turn to the committee for clarifying questions. Dr. Apte.
Yeah, hi. My question's about p-dichlorobenzene CAR-MOA analyses. And both in the document and in your presentation, you did mention that the alternative MOAs were looked at and were removed from the consideration. And I was wondering if there is any detailed analysis that was provided in any appendix or anything where, how the decision was reached to remove things like NRF2 especially in this process.
Thanks for that question. This is Derek Haggard from EPA. So we had initially attempted to apply analysis for kind of a set of 6 molecular initiating event biomarkers that have been published previously and run by EPA colleagues such as Dr. Chris Corton. Unfortunately, due to the limitations of the S1500 Plus platform, we didn't have sufficient coverage in terms of genes that are represented within the S1500 Plus assay for the biomarkers themselves, as well as having a large enough of a reference background set to apply the typical analysis that is done for whole transcriptome type studies. So the running Fisher's test that's used for that type of analysis wasn't performed. So we were really limited by the technology that was used in this case. And so in terms of confirming the CAR mode of action, our next best option was to take the approach we did here, which is selectively identifying more sentinel-like type genes to confirm whether or not what was observed in the published oral studies were also observed in the inhalation study that we have here.
Okay.
Yeah.
Okay, thank you.
Okay, so this is Chris Corton, and let me go ahead and add to that. So in your materials, there is an appendix that we prepared where we took advantage of the available genomic data sets that were out there from a number of studies, both in mice and rats, that actually looked at the gene expression patterns in the livers of the treated rodents using full genome arrays. So we had this opportunity then to look at the full complement of all the genes that we know are linked to the different modes of action of liver cancer. And so we applied a technique that we've been using for the last couple of years, where we could assess the activation of the different modes of action, including CAR, PPAR alpha, HR, oxidative stress, et cetera, the ones that are typically involved in liver tumorigenesis. So that is there. So we were able to observe CAR activation and also rule out these other modes of action.
And I think that's appendix, this is an update. Is this appendix D, gene expression biomarker analysis of existing rodent liver studies with p-dichlorobenzene? I think that's the one you're referring to, right, Dr. Gordon?
Yes. Say yes. Say yes.
I'm sorry, I can't.
Yes.
This is George Cobb. I can't hear the conversation.
All right, thank you. I found it, thank you.
Okay, thanks for that conversation. Dr. Wolf.
Yeah, I wondered if I could get some clarification on your adverse outcome pathway. I'm a little confused because as I look at the AOP wiki, the Alcom paper and the PEFR paper, and my understanding of nuclear receptor agonists, you don't see sustained hepatocyte proliferation. It's a mitogenic burst over a short period of time, sometimes up to a month, but it subsides. And where you do see sustained proliferation is persistent cytotoxicity. And I'm wondering, and we'll talk about it more when we get to those charge questions, but I just wanted to get some clarification of where you came up with that description of the key event. Because as I say, if you look at the papers you reference and you go back to the AOP wiki, that's not how it's described for this specific MIE and mode of action.
Yeah, while the labeling index, the percentage of dividing cells at any moment normalizes, the liver weight and the total cell numbers significantly elevated for animals' life. I know that this is a big issue because the labeling index actually normalized around 13 weeks. But because the liver is permanently larger and the absolute number of cell replications per animal stays above control for the lifetime and continually increasing the opportunity for spontaneous genetic errors, even if the replication go back or the DNA labeling go back by 13 weeks, the liver is still larger, and that can actually lead to the spontaneous genetic errors. And here you have to look at, this is actually a different, multiple mechanisms are involved due to CAR activation. CAR activation leads to CYP2B induction. This will accelerate the overall chemical metabolism, and the metabolites can induce oxidative stress that works as a tumor promotion agent. And even if as I mentioned earlier, even if the replication index normalizes by 13 weeks, but since the liver is permanently larger, it can actually lead to spontaneous genetic errors, leads to tumor.
Okay. Yeah, so I agree with that. And that's what needs to be clarified in the document. And that is not sustained hepatocyte proliferation as we typically think about it, because that is an increase in labeling index. And what you describe is scientifically accurate, but not that. And so I think that was a bit confusing to me when I saw it in the document and I saw it in this, but when I go back to the papers that you reference and then the AOP wiki, it describes it as with the typical nuclear receptor agonist. And what you described is exactly what is described in those papers, which obviously you read thoroughly. So I think that's a place of clarification, and it'll need to be clarified. And I think the way it's presented in the presentation resulted in my confusion on that. So thank you for clarifying.
Thank you. We will clarify that in our final evaluation. Thank you.
Okay, let's move on to Dr. Fox.
Hi, Mary Fox. I don't know if Dr. Pandiri was ahead of me though in the order. Okay, we'll go. Okay, so I was interested in a little bit more information about the epidemiological literature. So, and I think there's a very brief mention of it on slide 83, and this is for paradichlorobenzene. Were any of the epidemiological studies showing association to cancer outcomes?
Hi, everyone. I'm Anne Huang. I'm the epidemiologist. Yes, there are association between the paradichlorobenzene exposure with cancer, but there are some inefficient exposure assessment of the paradichlorobenzene. So the conclusion for the paradichlorobenzene to cause cancer is not conclusive.
Well, so I guess my question is, if there isn't a strong exposure assessment, that may mean we can't do, we can't do dose response analysis, but I think there's potential for a signal on hazard identification. But thank you.
Thank you for that question, Dr. Fox. I actually had the same question, even though that's outside of my area of expertise. That I had the same question. So thank you for getting that on the topic. Dr. Says, do you have a response?
Yeah, just want to clarify that there are no direct evidence for epidemiology, and because of the exposure assessment issues, the human epidemiology data is not associated with any causal cancer, specifically liver. Yeah.
So just to follow up on that, then what was the dichlorobenzene exposure in these studies then? What was the source of the exposure? I'm sorry, you're on mute.
Can you repeat the question one more time? Sorry.
So you said there are no causal relations. What was the source of dichlorobenzene exposures in these epidemiology studies that showed some link to cancer but are considered non-causal? What were the sources of exposure?
The air pollution.
Anna Lowett, Senior Science Advisor, Toxic Program. We weren't necessarily prepared to talk about the epidemiology data because we don't find it to be robust or very strong. But we will provide in the next few minutes the section of the technical support document where all those studies are described. And if there are additional clarification questions on any specific of those studies, we can follow up on those tomorrow.
Yeah, and I think this is a problem because really what you're asking this question is really what IRIS does in multi-day meetings to figure out whether things are carcinogenic or not embedded in a meeting like this. So that puts stressors on both sides, on the agency to try to figure out what the right answer is, and us to try to figure out the science behind that, as well as all the other things we're being asked to do. So got some work to do here. I think we can leave that for now and go to Dr. Pandiri.
Thank you. Thank you, Dr. Sasidaran, for your presentation. I have a similar question as Dr. Udayan Apte has indicated. In the alternate MOAs, I believe the oxidative stress NRF2 pathway has not been adequately addressed. I'm saying this mainly based on the information that you have provided within the document, where you have shown NRF2 activation was observed even in CAR-PXR null mice. So NRF2 activation was very high. And more importantly, there is a wonderful reference that you have cited, which is Henderson et al., where they used the hemoxygenase reporter system. And they showed that 1,4-dichlorobenzene is the strongest inducers of hepatic oxidative stress, whereas phenobarbital was also tested in the same study, which is a classic CAR activator, showed very little oxidative stress. So these both lines of evidence suggest that NRF2 oxidative stress is a significant alternative mode of action that need to be considered. And also, when you look at your own 5-day toxicogenomics data, several oxidative response genes were updated or upregulated. So maybe that is a discussion further.
Oh, you're on mute again. You're still on mute.
What are we saying?
Dr. Sasidaran, you are muted.
I think they're having audio problems in that venue. While we're waiting for that, I'd like to George Cobb, I'd like to say thank you for that question, because that's very good points you're making, and hope we can get a response from EPA here.
If the room in the conference has an audio problem, maybe you can use your computer speaker.
So this is Chris Gordon from the EPA. I'd like to address Arun's comments. There is a fair amount of genomic data which indicates that there is oxidative stress after exposure to DCB. And we show that, and you may have referenced that study that we did with the gene expression biomarkers. So we had a gene expression biomarker that's indicative of NRF2 activation, and that one indicated that there was strong oxidative stress, which was coincident with CAR activation. And you also mentioned the HO reporter system, and that also indicated that there was activation of oxidative stress with exposure. We've also done another study that I think was referenced, where we looked at the coincidence between CAR activation and NRF2 activation, and across as many chemicals as we could find in the mouse compendium that we had. And we could see very clear activation of NRF2, which occurred at doses that were a bit higher and a bit later than the CAR activation. So you get CAR activation, and then you get this increase in oxidative stress, and so there's a strong correlation there. So I guess the one of the questions that you addressed was whether or not this oxidative stress is mechanistically linked to the tumors or not. And I think that the assumption is that in the CAR mode of action, just like with for instance, other modes of action, such as PPAR alpha, that the oxidative stress is occurring, and that it is then linked to the potential for oxidative DNA damage. And hopefully that addresses your questions.
Yeah, but the issue here is we have seen increased NRF2 signaling, oxidative stress, even in the CAR-PX or null mice. So you have, in this particular case, it is a clear indication you have decoupling from your CAR activation to the oxidative stress. So I do agree with all the papers you have cited. It seems like that, but these two lines of evidence clearly shows that just because something is a CAR activator doesn't mean it has a strong oxidative stress response. Like in the Henderson paper, they showed phenobarb has a very weak oxidative stress response compared to dichlorobenzene, which is a CAR activator, but it has an overwhelming oxidative stress response.
This is Abhilash Shidharan, again, EPA. Okay, just want to clarify that there is oxidative stress reported, but that is not the primary tumor driver, because the CAR activation, as I explained earlier, CAR activation leads to CYP2B10 induction. CYP2B10 induction leads to increased oxidative metabolism. That way, there are reactive metabolites generation reported. But if oxidative stress is the primary driver, you will have to see any cytotoxicity or necrosis in the animal studies. Even after 13 weeks, we do not see any liver damage, AST, ALT, or liver enzymes in any of the animal studies. That means that the CAR is the primary driver and oxidative stress is the secondary effect. And it can actually go together and work as like a tumor promoter. The p-dichlorobenzene case, you will have to consider the metabolism as well, compared to phenobarbital or any other chemicals. Here, that is one of the most important factor.
Chris Gordon from the EPA. So to address Arun's comments about the uncoupling between the phenobarb exposure and CAR activation and oxidative stress, that did occur in the HO reporter gene mouse. But in our studies, where we extensively looked at multiple concentrations of phenobarbital at multiple time points, we could see a very tight coupling of phenobarb exposure, CAR activation, and activation of NRF2.
This is George Cobb. I appreciate the discussion. Perhaps, unless Dr. Pandiri disagrees, I'd like to maybe move this discussion to the actual charge questions. Would that be acceptable, Dr. Pandiri? Because
Yeah, absolutely.
that just in the interest of time. And then Dr. Wolf had a question.
Just a clarifying question on that, and we'll discuss it more in the charge questions on this oxidative stress. But is it tied closely with the dose response? And I think that's besides the time course, it's all 5 days on the transcriptomics, but you have very nice dose response characterization, particularly in the liver with the internal concentration measures. And so Dr. Corton, was that tied closely with dose response? Just for clarification of the relevance of that.
To be succinct, but yet, so there was a study, a 90-day study that was performed over at Hamner in mice with para, and they did multiple doses, and the appendix that I mentioned shows the sort of parallel increase in the oxidative stress along with the CAR activation, which was dose dependent.
Thanks.
Thanks, everybody. And I don't see any additional comments or questions from the committee. So I think at this point, it's time for a lunch break, and I'll ask Dr. Kamal if we should go to the top of the hour or how we should handle that, and if there are any closeout items we need this morning before we adjourn for the morning.
Thank you, Dr. Cobb. Yeah, we can take an hour, 60 minutes. So we'll meet at 2:06. Is that okay?
Excellent.
All right.
That's good. And then we'll see everybody back then.
Thank you.
Welcome back. I think we've been gone for an hour now. This is George Cobb, returning us to the afternoon session of Science Advisory Committee for Chemicals. Before we get started, I think we need to take the roll to make sure we know who is here. And so I'll just go down the list and you can just say if you're here or not. Dr. Apte? Is Dr. Apte here? Dr. Fong?
Yes, present.
Dr. Baker?
Here.
I see Dr. Chason.
Yes, here.
Dr. Fox.
Here.
Dr. Gentry.
Here.
Dr. Graham.
I'm here.
Ms. Jenkins.
Here.
Dr. Lee.
I'm here.
Dr. Merced Nieves.
Here.
Thank you. Dr. Ottinger.
Here.
Dr. Prisbilla.
Present.
Dr. Rubin.
Here.
Dr. Samuel.
I'm here.
Dr. Wright.
I'm here.
Dr. Gadia.
Here.
Dr. Islas Robles.
Here.
Dr. Carmouse.
I'm here.
Dr. Rocca. Hello, Rocca, I'm sorry. Okay. Dr. Lovato,
Here.
Dr. Pandiri,
Present, sir.
all right, Dr. Rager,
I'm here.
Dr. Schlink. Okay, Dr. Shao,
I'm here.
Dr. Strickland,
Here.
Dr. Wolf.
Present.
All right, let's go back to some that were not here. Dr. Apte,
I'm here.
great. And then Dr. Loraka.
Yep, here.
All right, and then Dr. Slink. All right, so I think we have quorum so that we can continue. And we can, before we proceed to additional topics from EPA, were there anything the committee needed to clarify from the morning session? Okay, and this, for those of you who are ad hoc members, we normally do this. We circle back at the end of every half day just to make sure we haven't missed something from earlier, so that we don't lose things too long on the time scale. All right, well, let's move on in our agenda now, and we can go to the EPA for our afternoon session, and we're going to hear about phthalic anhydride from Dr. Sayer.
Thank you for joining us today. I am Andrew Sayer, an environmental toxicologist with the US EPA. I'm happy to present an overview of the 2026 draft risk evaluation for phthalic anhydride. Next slide, please. Before we get too far, I want to start by acknowledging the many people that make this possible. We wouldn't be here today without your support, dedication, and hard work. Thank you. Next slide, please. Today's presentation on phthalic anhydride is broken into 7 sections, some with multiple speakers covering the parts of our risk evaluation. Each section is set up to help guide the audience through the technical aspects of information for a particular charge question. Next slide, please. I will start with a very brief introduction to phthalic anhydride. Phthalic anhydride is primarily used as a chemical intermediate in the manufacturing of various products such as plasticizers and resins. It is also found as an ingredient in consumer products like paints and coatings. Annual production volumes were reported to be between 250 and 500 million pounds per year. Importantly, phthalic anhydride undergoes hydrolysis to ortho or o-phthalic acid in the environment with a half-life of approximately 30 seconds in an aqueous solution. Therefore, phthalic anhydride is expected to be primarily present in environmental media in the form of orthophthalic acid. Next slide, please. The table on this slide demonstrates a key concept to understand for the phthalic anhydride risk evaluation. In environments where phthalic anhydride is expected to rapidly hydrolyze to orthophthalic acid, I think you have to go back a slide, please. In environments where phthalic anhydride is expected to rapidly hydrolyze to orthophthalic acid, exposures to orthophthalic acid rather than phthalic anhydride were evaluated. The environmental hazard and general population risk characterizations focused on orthophthalic acid. For the consumer and occupational risk assessments, EPA evaluated risk from exposure to phthalic anhydride and not orthophthalic acid. This is because phthalic anhydride is included in consumer products as an intentionally added ingredient and is expected to remain in the consumer products without hydrolyzing due to the low water content of these oil-based products. Additionally, workplace monitoring studies measured phthalic anhydride in air. Next slide, please. This diagram shows how all the documents and parts of a risk evaluation fit together to support the assessment, including the technical support documents or TSDs. The risk evaluation is represented by the gray box. This is our document map that you will see used throughout these presentations. We hope that it will help orient the audience to the different parts of our technical presentations. You may notice the green outline around the environmental hazard assessment and the green box that says charge queue number. These are keys to the remainder of the presentation. At each transition, we will use this format along with the green box to highlight the relevant TSD along with the related charge question. Next slide, please. This concludes the introductory remarks. I'll pause here for any clarifying questions before moving on to the next section of the presentation. Dr. Cobb?
Yeah, thank you for that presentation. From the committee, are there clarifying questions about any of this? If not, we can proceed.
Good afternoon. Oh, next slide, please. Good afternoon. Again, my name is Andrew Sayer, and I'm an environmental toxicologist with EPA. I will be presenting an overview of information pertaining to the environmental hazard charge question. Next slide, please. Charge question 10 pertains to the environmental hazard assessment, the environmental risk characterization, and the associated technical support documents for environmental hazard as highlighted on the slide. Next slide, please. This slide introduces charge question 10, which asks for comment on the usability of the aquatic hazard dataset for quantitative assessment. The dataset contains 4 aquatic hazard studies with 6 endpoints that include acute, subacute, and chronic values, as well as 2 aquatic plant and algae endpoints. Low and uninformative studies were also evaluated and considered qualitatively for supporting information. As a reminder, although EPA considered hazard studies from phthalic anhydride, the relevant exposure EPA assumed for the environmental risk assessment is orthophthalic acid due to the near instantaneous conversion of phthalic anhydride to orthophthalic acid in an aqueous environment. Next slide, please. 2 acute studies evaluated effects of orthophthalic acid on aquatic taxa. The first study with an aquatic invertebrate, Daphnia magna, consisted of 5 to 8 test concentrations in accordance with ISO standard determination of the inhibition of the mobility of Daphnia magna. This study was conducted with multiple other chemicals in addition to orthophthalic acid. The second study with the rainbow trout, an aquatic vertebrate, consisted of 5 concentrations and a control in accordance with OECD Guideline 203, fish acute toxicity test. Both studies reported endpoints at 100 milligrams per liter or greater. Next slide, please. One study evaluated effects of orthophthalic acid on 2 fish species, a 7-day subacute study with the zebrafish and a 60-day chronic study with the rainbow trout. In the zebrafish study, although exact test concentrations were not reported, 5 to 7 concentrations were used. Because of variability with the LC50 being less than the LOAC, EPA did not consider this study for quantitative assessment. In the rainbow trout study, an LC50 was determined at 44.2 milligrams per liter, with the LOAC reported at 32 milligrams per liter based on mortality, total embryo toxicity, length, and weight. A NOAC was not reported. Mortality generally occurred in the egg stage during late gastrulation. Significant differences were also reported in length and weight compared to controls, but it was not reported whether the differences were an increase or decrease. Next slide, please. 2 algal studies evaluated effects of orthophthalic acid on aquatic plants and algae. In the first study, the green algae Pseudocurchinella was assessed after exposure to orthophthalic acid over a 72-hour period, resulting in an estimated EC50 of 2,270 milligrams per liter based on an inhibition of growth. In the second study, the freshwater algae Desmodemus was assessed after exposure to a limit test of orthophthalic acid. The resulting EC50 was greater than 100 milligrams per liter based on an absence of effects. Next slide, please. Although available data were limited to a few species and of high or medium study quality, EPA chose to use the information presented here to derive concentrations of concern. Studies with unbounded endpoints were not considered, and an assessment factor was included to account for uncertainty with the limited data set. Please review and comment on the strengths and uncertainties of the methodology and data used to derive acute and chronic COCs for aquatic thresholds, and whether the data supports the quantitative approach used by EPA. Next slide, please. Thank you for your time. This concludes the environmental hazard section of the presentation. I'll pause here for any questions before we move on.
Thank you for getting us through that, and turn to the committee to see if there are any clarifying questions, comments. I see Dr. Ottinger.
I just wanted to ask if there was, since this is a ring structure compound, if there was any measurement of other endpoints that could involve interacting with as an endocrine disruptor or other kinds of effects.
Andrew Sayer with EPA. These studies really focus on those apical endpoints that we were looking for. As far as endocrine disruption, we didn't see any of that, those measurements or metrics in these studies.
Thank you.
Oh, Dr. Slink.
Yeah, thanks for that presentation. Going through some of the documents, I believe for the Daphnia and algal study that were sort of combined, that was a published article. I went through that and it said that the concentrations of the acid were measured in the algae, but I couldn't find a confirmation if they were actually measured in the Daphnia. What's your take on that? Would you, is that consistent with what you saw, or would you assume that they both were measured since it's the same publication?
Andrew Sayer with EPA. So I think for some of these studies, they measured multiple chemicals in sort of like a high throughput fashion. And we couldn't find some of the analytical verification either, or if it was done, it was not reported in text. So that's consistent with what we saw as well.
Okay, so the assumption is that it was in the algae, it was measured in the algae, but not the Daphnia. That's kind of consistent, right?
That's accurate.
Yeah. Okay. Thank you.
Okay. Dr. Chasen.
Sorry, thank you very much. I'm out of my wheelhouse by a lot here, but I was wondering if there was information about bivalves or other types of sort of bottom dwelling, the crustaceans or anything like that, that would be relevant to, surface waters and that kind of toxicity, or at least whether those kinds of water animals are considered when looking at the environmental hazard.
Andrew Sayer, EPA. There was one, I appreciate your comment. There was one study that didn't make it past our systematic review criteria. It got ranked uninformative, but we did take a look at it. It was an acute study with the chironomid, not exactly a bivalve, but like a benthic dwelling organism. And it didn't, there was no toxicity. It was a EC50 or I'm sorry, an LC50, but there was no effect seen after 48 hours. The endpoint was greater than 27 milligrams per liter.
Thank you.
Thank you for that response and all the questions. Are there other questions from the committee? If not, I have two. Well, maybe one's kind of a comment and maybe a question. But let's go back to Dr. Ottinger's question about the endocrine endpoints. Were there studies that were not the focus of the couple that you selected that had those types of endpoints that are not reported here in the presentation or in the written report from EPA?
Andrew Sayer with EPA. We had very limited data for this, and most of the studies were a little older, which was sort of irrelevant. But we didn't find any endocrine disrupting endpoints in these studies. Unless
I'm on mute. So did you look at any of the phthalate or phthalic acid endpoints, or just for the phthalic anhydride data set?
Andrew Sayer, EPA again. We assumed for this, because it's an aqueous environment, that the phthalic anhydride was almost exclusively orthophthalic acid. So to get at your question, like the studies that we had are the ones that were received through our systematic review protocol. And we didn't have much data to begin with.
So you're saying there's not much data for the orthophthalic acid?
That is correct.
Okay, I'll have to go back and look at that. I may be misremembering that data set. So Dr. Ottinger.
Marianne Ottinger. Yeah, no, the reason for my question was because in a number of the bivalves and other species, they use signaling compounds or signaling hormones for them that have ring structures. And so if there's any chance of even the aqueous form of the compound interacting with those systems, it could interfere. And, broadly termed as an endocrine disruptor sort of function. So that was the basis of my question.
Thank you. And I'd like to kind of make a point, and other committee members can chime in if they'd like, or EPA can as well. You mentioned that one or some of the studies didn't designate whether growth was affected upward or downward. It's my understanding it doesn't matter, because if you're too big, you may be more visible to predators and can't escape. You're too small, maybe you can't effectively forage. So there's potential risk on both sides of that, but that is not my area of expertise. I've just picked that up over the years, working with some really good folks like those on this committee. So I don't know if EPA has a response to that, or if that's just a comment just for the record.
Andrew Sayer, EPA, thank you for your comment. We acknowledge it. We welcome any other literature studies that the committee would like to submit.
Thank you. Okay, if we don't have additional comments, then I think we go to the non-cancer human health, if I'm reading this right, and Dr. Peperiel will be our presenter.
Can everybody hear me?
Yes.
Thank you, Dr. Cobb, for that introduction. Good afternoon, everyone. My name is Ashley Peperiel, and I'm a toxicologist in EPA's existing Chemicals Risk Assessment Division. I will be covering background information pertaining to the non-cancer human health hazards of phthalic anhydride. Next slide, please. This slide shows that there will be 3 subsections within the human health hazard portion of this presentation. Each of the 3 subsections is related to the indicated charge question. Reference documents and docket are shown. Next slide, please. This slide provides the general document map for the phthalic anhydride risk evaluation. For this portion of the charge, the primary technical support documents providing background information include the human health hazard assessment and the human health risk characterization, which is section 4 of the risk evaluation. Next slide, please. The first section of the phthalic anhydride presentation will focus on the POD derived for use in the general population screening level assessment. This section is relevant for charge question 11. Next slide, please. The general population is expected to primarily be exposed to orthophthalic acid from TSCA releases of phthalic anhydride. Therefore, EPA evaluated hazards associated with oral exposure to o-phthalic acid in addition to phthalic anhydride. The evidence base consisted of 11 studies of phthalic anhydride or o-phthalic acid, 9 of which were in rats and 2 of which were in mice. The evidence base included 2-year carcinogenicity studies in rats and mice by NCI published in 1979 and 2 developmental studies in rats. Based on the available evidence, EPA preliminarily concluded that phthalic anhydride and o-phthalic acid have low systemic toxicity via the oral route of exposure, as described in section 4.1.3 of the draft Human Health Hazard Assessment. This conclusion is based on the following sub-bullets on the slide. No consistent target organ toxicity was observed. Adverse effects are limited to reductions in body weight gain, and food consumption across studies of rats and mice. No hazards were identified that were relevant for acute durations. There is no evidence of developmental toxicity at non-maternally toxic doses. There is no evidence of carcinogenicity in rats or mice. Consistent with EPA's conclusion, assessments by the OECD in 2005, Australia NICNAS in 2013, and Health Canada in 2019 have also concluded that phthalic anhydride has low systemic toxicity via the oral route of exposure. Next slide, please. Considering the available evidence, EPA's proposed non-cancer oral POD for use in the general population screening assessment is based on no observed adverse effect level, or NOEL, for decreased body weight gain in rats exposed to phthalic anhydride in feed for 2 years. This proposed POD is health protective and is lower than the majority of other candidate oral PODs considered by EPA. EPA used allometric body weight scaling to the 3/4 power to derive human equivalent dose, or HED, of 66 mg per kilogram per day from the NOEL. A total uncertainty factor of 30 was proposed as the benchmark margin of exposure. The uncertainty factors that contribute to that include the interspecies uncertainty factor of 10x and an interspecies uncertainty factor of 3x. The interspecies uncertainty factor was reduced from 10 to 3, consistent with EPA guidance, which indicates that if an animal POD is converted to an HED using allometric body weight scaling, the toxicokinetic portion of the uncertainty due to interspecies differences is sufficiently addressed. Health Canada and NICNAS have also selected this as their POD. And the table on the slide summarizes the proposed POD, including the relevant population in the risk evaluation, exposure scenario, critical effect, HED, and benchmark MOE. A consideration of the key study to derive the POD was that it reported test substance loss from the feed over time. However, the authors of the key study reported sufficient information that allowed EPA to calculate adjusted doses accounting for that loss of test substance. This adjusted value is represented in the NOEL and LOEL column of the table. As indicated in the footnote on the table, NCI reported a 2.59% loss of phthalic anhydride from the feed mix per day over a 14-day period when stored at room temperature. And they also reported that fresh food was prepared every 7 to 10 days. And so assuming the fresh diet was prepared every 10 days with a 2.59% loss per day, EPA estimated the total loss after 10 days to be 25.9% and use that to adjust the doses you see represented in the table and in the draft POD. Next slide, please. All right. So the next section of this presentation will focus on the dermal POD for phthalic anhydride. The draft human health hazard assessment for phthalic anhydride incorporates novel approaches, including the application of adverse outcome pathways as organizing frameworks for the available data. In addition to human and animal data, available data for this assessment include in chemico and in vitro new approach methodologies, or NAMs, for the dermal assessment. NAMs are also incorporated in the respiratory assessment, which I'll address in a later part of this presentation that focuses on inhalation hazards. The novelty of the dermal assessment of phthalic anhydride is the use of a computational NAMs-based model to derive a human relevant point of departure. And this section is relevant for charge question 12. EPA would also quickly like to thank its collaborators for work on this section, including NIHS, NICEDM, and NICVAM. And special acknowledgement is given to Dory Garmalek, Emily Renke, and Vic Johnson. Next slide, please. EPA considered all reasonably available data relevant to dermal hazards of phthalic anhydride, which mostly consisted of evaluations of skin sensitization and related immune effects. EPA preliminarily concluded that the most sensitive hazard for phthalic anhydride via the dermal route of exposure is skin sensitization. This conclusion is consistent with that of other existing assessments by the OECD, Health Canada, Australian NICNAS, the ACGIH, and Europe. In contrast, orthophthalic acid or ophthalic acid is not a skin sensitizer. Information was available on skin irritation as well, but was considered much more limited compared to the vast amount of data on skin sensitization, and it was not as sensitive. Studies investigating other endpoints were not identified. To organize the available data on skin sensitization, EPA applied the framework outlined by the Skin Sensitization Adverse Outcome Pathway, or AOP, described by the OECD in 2014. Next slide, please. The figure on the slide shows the skin sensitization AOP. AOP describes the sequence of events starting from the molecular initiating event and ending with the adverse outcome of sensitization, or inflammation upon challenge with an allergen. Each blue box with red text above it represents a key event. The OECD test guidelines that are relevant for each key event are indicated in the orange shapes adjacent to the blue boxes. For example, test guideline 429, the local lymph node assay, is relevant for key event 4, T-cell proliferation. Next, moving through the figure, in key event 1 in the first box, low molecular weight compounds like phthalic anhydride form haptens via covalent binding of an electrophilic hapten to cysteine or lysine amino acid residues on epidermal proteins. The binding can be quantified by assays included in the OECD test guideline 442C, which include peptide depletion assays like the direct peptide reactivity assay, or DPRA, and kinetic DPRA, or KDPRA. The hapten complex formed during key event 1 can be recognized by immune cells that trigger subsequent key events in the AOP. As shown by the path of the arrows, key event 1 can then proceed either to key event 2 or directly to key event 3. Key event 2 represents events in keratinocytes that occur when the hapten complex reacts with cell surface proteins or endogenous proteins to activate cellular response pathways, such as the NRF2 antioxidant response pathway. OECD test guideline 442D describes assays that quantify this keratinocyte response, including the keratinosense and lucens assays. Key event 3 represents activations of epidermal dendritic cells, known as Langerhans cells. Activation of DCs leads to increased chemokine and cytokine secretion, and changes in expression of chemokine receptors, which can be quantified in various ways as described in OECD test guideline 442E. Relevant assays for this key event include GARD skin, the human cell line activation test, or HCLAT, and USENS. The activated dendritic cells internalize or engulf the hapten complex formed by MHC for subsequent presentation to T cells in the lymph node. This then leads to T cell activation and proliferation, which is reflected by key event 4. A positive response in the local lymph node assay, or LLNA, reflects induction of sensitization. Finally, the adverse outcome is inflammatory response upon challenge with an allergen. Memory T cells reactivated by hapten presentation by activated mature DCs will induce inflammation and allergic contact dermatitis in human or its rodent equivalent contact hypersensitivity. Next slide, please. So a summary of the available data identified by EPA relevant to each key event is shown in this table on this slide. This table was adapted from tables 4.6 to 4.10 of the draft human health hazard assessment. The column headers indicate the key event, the assay, a summary of the result of positive or negative, and whether it was included for dose response analysis. Check marks in blue highlighting on the table indicate a study was rated acceptable and appropriate for quantitative dose response assessment in EPA's data evaluation record. For key event 1, EPA identified 2 DPRA and 1 KDPRA. All were positive. Of these, 1 DPRA and 1 KDPRA were considered acceptable and used for quantitative dose response assessment. For key event 2, EPA identified 2 keratinosense and 1 lucens assay. All assays were negative. Of these, 1 keratinosense assay was considered acceptable for quantitative use in dose response assessment. For key event 3, EPA identified 2 HCLAT and 3 USENS, as well as 1 GARD skin assay. Of these, 4 were negative and 2 were positive, including the GARD skin and 1 of the USENS assays. However, only 1 HCLAT assay was considered acceptable for quantitative use in dose response assessment. For key event 4, EPA identified 5 LNAs, all of which were positive. 3 were considered acceptable for quantitative use in dose response assessment. And for the adverse outcome, EPA identified 1 guinea pig maximalization test, 1 Beeler test, 1 modified Beeler test, and 1 skin prick test. Phthalic anhydride was positive in all assays tested. Additional supporting evidence was identified from case reports and workers manufacturing phthalic anhydride, as well as case reports of contact dermatitis in consumers using nail polish with phthalic anhydride, as described in section 42116 of the draft human health hazard assessment. Across available data, EPA identified consistent evidence that phthalic anhydride is a dermal sensitizer. Supporting data come from studies in humans as well as animal data, including positive responses in the guinea pig maximalization tests, the Beeler tests, and in vivo LLNAs. Positive results in the DPRA and KDPRA assay reinforce the conclusion that phthalic anhydride is a sensitizer. Of note, mixed results were reported for in vitro assays relevant for key event 2 and 3, which involved aqueous cell culture media. EPA identified skin sensitization as the key endpoint for dermal POD derivation. To derive a POD, EPA applied a computational NAMS approach called the Skin Allergy Risk Assessment Integrated Chemical Environment, or SARA-ICE model, which can integrate information from select assays compliant with OECD Test Guideline 497. Next slide, please. EPA applied the SARA-ICE model to derive a POD for skin sensitization consistent with OECD Test Guideline 497, the defined approach for skin sensitization. The model was developed through collaboration with method developers at Unilever and Nicedum. The model, SARA-ICE is a Bayesian statistical model that incorporates uncertainty of the inputs, as well as statistically integrates across all of the key events in the AOP simultaneously where they are available. The model is built using a database of 434 chemicals with skin sensitization data from in vitro and in vivo information sources, namely human predictive patch tests. The most common result in a human predictive patch test used to build the model is that one individual or 1% of individuals is positive for sensitization. Inputs of SARA-ICE model potentially include results from the DPRA, KDPRA, keratinosens, HCLAT, USENS, LNA, and HPPT data information sources. These assays are included as inputs because they provide continuous metrics for the model. The model output is a probability distribution of the EDO1, which is an estimate of the applied human predictive patch test dermal dose in micrograms per centimeter squared, at which there is a 1% chance of inducing sensitization. The geometric mean of that distribution is the most likely estimate. Importantly, the model predicts a human relevant dose. Next slide, please. Okay, so this slide shows the inputs EPA used for the SARA-ICE model, which included in the summary table that was adapted from table 411. In the human health hazard assessment. So table 411 in the hazard assessment. As inputs, EPA used the results from the DPRA, the KDPRA, the HCLAT, the keratinosens, and the LLNA that received a study rating of acceptable for use in quantitative dose response assessment. The model output is a probability distribution, which is shown by the figure below the blue arrow, which is a generalized EDO1 distribution graph output from the model. The 5th, 95th, and geomean of the EDO1 are indicated by the gray bars and highlighted with the bolded black text and arrows. The geomean is a tiny purple bar that I hope you can see. The purpose of this figure is to help visualize the concept of the model, and the actual data outputs from the SARA-ICE model, given these inputs, are on the next slide. Next slide, please. The SARA-ICE model was run using 2 sets of input data, and therefore there are 2 outputs summarized on the 2 rows in the table on this slide. The 2 sets of input data are represented under the first column of model run in the table. The first is phthalic anhydride all data, which includes data from all assays that were considered acceptable for quantitative use. The second run includes that minus data for key events 2 and 3 due to EPA's concern that phthalic anhydride hydrolyzed to ophthalic acid, which is a non-sensitizer, in the cell culture media for these assays, yielding negative results. There's additional concern for interpreting key event 2 assays that rely on cysteine binding, as the DPRA data in fact show that phthalic anhydride preferentially binds to lysine over cysteine. The second column of this table is the geomean of the EDO1 in microgram per centimeter squared, which represents the candidate PODs. The next three columns to the right of that are the 5th, 50th, and 95th percentiles of the EDO1 distribution. The last column is the Sarah-Ice prediction uncertainty ratio, which is abbreviated as SPUR. The SPUR is measured by the ratio of the 50th to the 5th percentile and is a measure of variance in the estimates. Next slide, please. So EPA is proposing the EDO1 of 45 micrograms per centimeter squared as the POD for input into the draft risk evaluation for phthalic anhydride. The POD is based on induction of dermal sensitization. This POD is selected from the output of the model run that excluded key event 2 and key event 3 data. EPA is proposing a total uncertainty factor of 1 based on a UFH for human variability of 1. The POD is based on a human relevant dose, so the UFA is not applicable here. For the UFH, EPA considered the POD to be highly refined and intended to already be protective of 99% of the population from induction of skin sensitization, and therefore the UFH was reduced to 1. Of note, OECD Test Guideline 497 does not provide recommendations on the UF application, and application of UFH represents a chemical-specific proposal for phthalic anhydride. The summary table is adapted from the draft human health hazard assessment, and as you can see, the relevant populations for this POD are workers and consumers. The POD is relevant for acute dermal exposure scenarios. Next slide, please. Okay. This next part of the presentation is relevant to the inhalation hazards of phthalic anhydride and charge questions 14A through 14D. But first, EPA would like to thank its collaborators on this work, including NIHS, NICEDM, ICVAM, and method developers, including InVitroLice. Special acknowledgement is given to Dori Germelek, Emily Renke, and Vic Johnson for their efforts as part of the ICVAM NICEDM project assessing respiratory sensitizers. As part of this project, ICVAM agency partners had nominated 102 substances of interest for evaluation in the GUARD Air respiratory sensitization platform. And of those, 93 substances were successfully evaluated in GUARD Air. One of those was phthalic anhydride. And it was that effort that informed some of the experimental data for this evaluation. EPA is also part of ongoing efforts within the OECD Working Party on Hazard Assessment, the case studies group, to further develop approaches to evaluate respiratory sensitization. Next slide, please. EPA evaluated the weight of scientific evidence and concluded that the most sensitive hazard following inhalation exposure to phthalic anhydride is respiratory sensitization. This is further described in section 4.3.1.2 of the draft human health hazard assessment. This conclusion is consistent with that of the OECD, Health Canada, Australian ICNAS, and the European Union and the ACJH. In contrast, available evidence supports that oxalic acid is not a respiratory sensitizer. Phthalic anhydride is also an irritant, but inhalation studies of other endpoints were not identified. EPA organized available data on respiratory sensitization according to the framework outlined by AOP 39. AOP 39 is also known as the respiratory sensitization AOP. Next slide, please. The figure on this slide shows a simplified version of the AOP that is in the human health hazard assessment. The blue filled boxes designate key events and adverse outcome. Key events 1 through 4 correspond to the induction phase of respiratory sensitization, while the adverse outcome, or an allergic respiratory hypersensitivity response, corresponds to elicitation of the immune reaction following subsequent exposure to the allergen. The respiratory and dermal sensitization AOPs exhibit substantial mechanistic convergence, for example, sharing key event 1. And the time course of respiratory sensitization is considered variable because of this two-phase immunological process where elicitation phase can have a latency phase. Key event 1 in the first blue box is covalent interaction with cellular proteins, which is the same as that of the dermal AOP and can also be measured by the KDPRA and DPRA. Similar to the dermal AOP, key event 1 can then proceed either to key event 2 or directly to key event 3. Key event 2 represents events in respiratory epithelial cells, including activation of inflammatory cytokines and induction of cytoprotective gene pathways. The Allison's assay is one assay that can evaluate key event 2 as well as key event 3 data. The Allison's assay is a 3D co-culture in vitro model representing the alveolar barrier and combines 3 human cell lines. It quantifies inflammatory cytokine markers for key event 2, as well as cell surface markers on dendritic cells relevant for key event 3. Key event 3 represents induction of inflammatory cytokines and activation of dendritic cells. These events are quantified through assays that reflect expression of cell surface markers. In addition to the Allison's assay, the GARD-AIR assay provides data for this key event, which is based on dendritic cell activation, as reflected by transcriptional quantification of genomic predictors of sensitization. Activated dendritic cells migrate to the lymph node to then present antigen to T cells and activate them, which leads to their proliferation. And this reflects key event 4. Key event 4 is quantified by the local lymph node assay. For this, EPA, for the respiratory part, EPA only included LNAs from inhalation studies when organizing data into this AOP framework. The adverse outcome is inflammation upon challenge with an allergen, which occurs in the respiratory tract after subsequent exposure. Next slide, please. This table shows the data EPA identified that were relevant for key events 1, 2, and 3. Key event 4, as well as the adverse outcome, are going to be on the next slide. As you can see for key event 1, there were 2 DPRA and 1 KDPRA, which were the same assays from the dermal AOP for this key event, and all were positive. The Allison's assay provided data for key event 2, which was inconclusive because there are not yet definitive cutoff values for cytokine responses to allow clear identification of sensitizers. The Allison's assay also provided data for key event 3. A positive result was observed in one of the 2 assays, as reflected by increased expression of CD86 and CD54 above threshold values. There was also GARD-AIR data available for the key event 3, thanks to collaboration between the agency and NICEDM. The output of GARD-AIR's transcription-based quantification is a decision value, or a DV, and any value above 1 is positive. Phthalic anhydride yielded a DV of 4.96, which is positive. Next slide, please. Data on the adverse outcome come from 5 available studies of exposed worker populations, as well as 6 available laboratory animal inhalation studies, one of which included a respiratory LNA by Arts et al. In the worker studies, there was consistent evidence of respiratory sensitization reflected by increased prevalence of work-related respiratory symptoms, such as asthma, and increases in serum-specific antibodies against phthalic anhydride. Animal studies consist of 3 guinea pig studies, 2 mouse studies, and 1 rat study. Across these species, consistent evidence of outcomes consistent with respiratory sensitization was observed. Outcomes included changes in lung function and breathing rate in guinea pigs, increases in lymphocyte proliferation in mice, and increases in IgG levels in guinea pigs and rats. Increased lymphocyte proliferation data come from the study by Arts et al., who developed a, quote, respiratory local lymph node assay, quote. In this assay, 2 of the 6 animals in the study had stimulation indices, or SI, above around 3 at an air concentration of 14.2 milligram per cubic meter, which the authors considered positive. EPA considered these data relevant for key event 4. Altogether, the evidence on the previous slide from the NAMS-based assays and the human and animal data discussed on this slide support EPA's preliminary conclusion that phthalic anhydride is a respiratory sensitizer. And so respiratory sensitization was considered for dose response analysis. Next slide, please. In contrast to dermal sensitization, there's no defined approach for assessment of respiratory sensitization yet. In vitro respiratory sensitization assays, oh, sorry, let me get some water really quick. However, EPA is actively participating in ongoing activities related to their development as part of the OECD Working Party Hazard Assessment IATA Case Studies Program. Therefore, these assays were used as part of the weight of evidence described in the Human Health Hazard Assessment, ultimately to support the POD. EPA's approach was to drive 3 candidate PODs based on respiratory sensitization. In the draft Human Health Hazard Assessment, EPA describes these as the proposed POD and the alternative PODs in section 4313. The proposed POD of 0.4 milligram per cubic meter was derived from an 8-hour time-weighted average LOEC from heavily exposed workers in the study by Nielsen et al. In 1988. The 8-hour time-weighted average is derived from a mean 30-minute peak of 6.6 milligram per cubic meter. The first alternative POD of 0.099 milligram per cubic meter phthalic anhydride is an 8-hour time-weight adjusted human equivalent concentration and is based on the guinea pig study by Sarlo et al. In 1994. This is based on increases in IgG in serum collected 18 hours prior to challenge. The IgG antibodies were not specific to phthalic anhydride. The second alternative POD of 0.03 milligram per cubic meter is based on an analog study in rats exposed to trimelytic anhydride by Leach et al. Based on increases in TMA-specific antibodies. The POD also represents the 8-hour time-weighted average adjusted human equivalent concentration. Ultimately, EPA concluded that there was too much uncertainty associated with the use of available animal studies to derive a POD based on respiratory sensitization for phthalic anhydride. This is primarily because there are currently no validated animal models for respiratory sensitization, as well as various species differences in respiratory anatomy and immunological mechanisms that add uncertainty with any extrapolation procedures. And for the analog data, there is additional uncertainty introduced. Next slide, please. EPA is proposing a POD for phthalic anhydride based on an 8-hour time-weighted average of 0.4 milligram per cubic meter based on respiratory sensitization in heavily exposed reactor loaders in the study by Nielsen et al., 1988. The POD is based on increased prevalence of asthma, conjunctivitis, and rhinitis in parallel with increased serum-specific IgG antibodies. This POD is applicable for acute inhalation exposure scenarios for workers and consumers. EPA is proposing a total uncertainty factor of 30 based on a UFH of 10 and a UFL of 3. EPA considered data-derived factors to refine the uncertainty factors, including the toxicokinetic component of the intraspecies uncertainty factor, or UFH-TK, as well as the LOEC to NOEC uncertainty factor, or the UFL. Additional details are described at the end of section 43131 of the Human Health Hazard Assessment. The table below on the slide is adapted from table 420 of the draft Human Health Hazard Assessment to include the strengths and the uncertainties of the study. Overall, there are multiple uncertainties with the Nielsen et al. Study related to its study design and the lack of NOEC. However, the major strengths of the study included that it provided specific air monitoring data for phthalic anhydride in parallel with respiratory outcomes like asthma and the phthalic anhydride specific antibodies. The study also is directly relevant for worker populations in the risk evaluation for phthalic anhydride. Next slide, please. So this figure shows the comparison of existing hazard values with EPA's effective hazard value using the total uncertainty factor of 30 and the proposed POD. EPA calculated the effective hazard value by dividing the POD by 30 to result in the 0.013 milligram per cubic meter you see on the slide. That value is represented by the purple bar, where other hazard values are the gray bars. The x-axis is the hazard value in milligram per cubic meter, and please note the break in the axes. The point of the slide is just to illustrate that existing values span orders of magnitude, and that EPA's proposed value is in the middle of the existing values, including the most recent 2017 value by ACGAH, which was 0.0002 milligram per cubic meter, and the OSHA-PEL from 1971 of 12 milligram per cubic meter, both of which are based on respiratory sensitization. Next slide, please. The proposed POD from Nielsen et al. Is from a study of exposed workers. EPA characterized the variability that is expected based on possible differences in toxicokinetics within a worker population using two different approaches. The first approach characterized human variability driven by physiological and anatomical variability in the respiratory tract. EPA applied the ICRP model, ICRP respiratory tract model to evaluate variability in dose delivered to the tracheobronchial or TB airways that would be expected in a worker population based primarily on morphological differences in the upper airways or the head. According to the ICRP model, there is an approximate 3 times difference in the 95% confidence upper bound compared to the central tendency estimate of particle deposition, which reflects variability. These results were largely independent of factors such as activity level and breathing rate, particle size, and sex. In the second approach, EPA characterized human variability driven by workplace exposure determinants of particle size and activity levels. EPA evaluated regional lung particle deposition via multiple path particle dosimetry modeling based on several factors, including particle size distributions and worker activity levels. Worker activity levels include factors like breathing rate and tidal volume. NPPD simulations indicate that within the tracheobronchial region of the lung, particle deposition or exposure for the most highly exposed individuals vary when looking at individuals that are undergoing a heavy exercise compared to sitting or light exercise. Heavy exercise would be expected during a challenging manual task like loading a reactor. The difference in particle deposition in heavy exercise compared to light exercise or sitting is about 1.5 to 3-fold, respectively. Based on the above rationale, EPA preliminary concludes that a factor of 3 is appropriate to account for human toxicokinetic variability. Next slide, please. An additional consideration by EPA for the inhalation POD relates to the factors that contribute to the magnitude of the critical effect of respiratory sensitization. Respiratory sensitization is generally considered a severe outcome. However, the candidate POD for Nielsen et al. Is based on respiratory sensitization. And this effect is partly reflected by increased prevalence of asthma of about 14% in the highly exposed workers compared to 0% in the low exposure group. Summarized in the table on the slide, EPA considered available data to characterize the magnitude of asthma prevalence relative to general population benchmarks. Observed symptom prevalences for asthma in highly exposed worker groups of 14% are not far from current day population benchmarks in the US of about 8%, according to recent CDC data. Additionally, the Nielsen study was conducted in Sweden in the 60s, and background rates of asthma at that time were around 1.3 to 2.3%. And more current day asthma rates in Sweden are around 9%, which are similar to US benchmarks. EPA concludes that the observed symptom prevalences of asthma in the highly exposed worker population from Nielsen et al. Are similar to general population benchmarks. Next slide, please. EPA's weight of scientific evidence to support the POD comes from strong, coherent, and biologically plausible evidence for respiratory sensitization in workers and animals exposed to phthalic anhydride via inhalation. 4 out of 5 epidemiological studies found consistent evidence of work-related asthma or respiratory symptoms, which in some cases coincided with increased serum levels of specific IgG. 6 animal studies demonstrate evidence consistent with respiratory sensitization, although there is not yet a validated model for respiratory sensitization in animals. Nevertheless, observed effects include changes in lung function and increased breathing rate. In one study, this also corresponded with increased IgG antibody levels specific to phthalic anhydride. Positive results in the NAMS-based assays provide additional coherence across evidence streams. So phthalic anhydride tested positive in 2 DPRA, 1 kDPRA, the GARD-AIR assay, and one of the 2 Allison's assays. EPA's proposed POD is based on the 8-hour time-weighted average based on a 30-minute peak exposure during reactor loading, which was 6.6 milligram per cubic meter. Effects consistent with respiratory sensitization were also observed in the Sarlo et al. Study of guinea pigs at doses as low as 8 hours of a time-weighted average adjusted human equivalent concentration of 0.55 milligram per cubic meter phthalic anhydride, where the 8-hour time-weighted average HEC is 0.099 milligram per cubic meter. The POD proposed by EPA is in line with that of existing assessments. Indeed, the California OEHA and Health Canada had also selected the Nielsen et al. Study from 1998 to calculate for quantitative risk assessment. Next slide, please. Okay, so this concludes the presentation of human health hazard information for phthalic anhydride related to charge questions 11, 12, and 14. Thank you for your attention, and I see Dr. Cobb has turned his camera on, so I'll turn it back over to Dr. Cobb for any questions.
So first of all, I'd like to thank you very much for that very nice presentation. Very informative. And I think the committee probably has some questions for you. I see Dr. Graham's hand is up.
Hello, this is Dr. Cynthia Graham. Yes, it was a very thorough presentation. I commend you for that. I am curious if you looked at the concentration that causes irritation, respiratory irritation, there is some researchers now were believing that irritation is one of the hallmarks of developing respiratory sensitization.
Thank you for your question, Dr. Graham. EPA did consider in its hazard assessment, we do look at irritation. However, the most sensitive hazard is respiratory sensitization. And
my question is the concentration, not that that was the most sensitive outcome, but did you compare the concentration causing respiratory irritation with your POD?
In the current draft, we don't directly make that comparison one-to-one. But it's clear that based on the limited available evidence on the irritation side, which is more limited, that it would be a higher level that you are seeing the irritation effects compared to the much more sensitive effect of respiratory sensitization.
Yes, but you're looking at induction of sensitization, which is normally a higher concentration, will cause the induction, and the elicitation will develop after very low concentrations.
Yeah, in the key study, the Nielsen et al. Study, because of the design of it, the induction elicitation phase are actually obscured. So we're unable to say that, like on the dermal side, we're looking at induction. We're not able to do that for the inhalation side. So it's difficult to answer your question for that reason, I believe.
All right. Thank you for that question and for the response. Dr. Gadia.
Thank you. This is very interesting, and thank you for this great presentation. I have one comment and then a question followed by it. One being that the OELs typically are developed based on systemic effects, and hazards like sensitization, they are communicated via notations on OELs. And here, developing or deriving an OEL based on sensitization seems to be overly conservative to begin with. And then I think from its slide 144 or 145, where the POD was from worker population, and still EPA uses a factor of 10, which seems to be overly conservative again, primarily because the OEL is supposedly for the worker population, so you don't have to account for the geriatrics or the pediatrics. So I would consider reevaluating that.
Yeah, thanks for the question. So this is Anna Lowett, OPPT, Senior Science Advisor. I guess we would just ask you to put those comments in your comments for the report. Those are actually the kinds of things we're looking for in the report and your comments over the next few days of how to take endpoints like this and develop regulatory values for it. So thank you.
Thank you. And thanks for that response, Dr. Lowett. Dr. Strickland?
Hello, I have a comment or no, a question on the skin sensitization part. You had key event 2 and 3 assays that were negative because the phthalic anhydride hydrolyzed in aqueous media to phthalic acid. Can you explain the assays that were positive? There was a USENS assay and a GARD skin assay that were positive.
Hi, Ashley Fabriel, EPA. Thanks, Dr. Strickland, for your question. So I'll start with the USENS assay. We're not we're actually not completely sure why that one was positive. It might be related to the relatively high test concentration. It was about, it was over 1,000 micromolar, I believe. And we're actually not entirely sure if the committee has suggestions that would be well received. But and the GUARD skin assay, that one is transcriptional based rather than based on like protein expression like some of the other assays. And so this isn't published anywhere, but it would be expected that it might be more sensitive, be able to detect a lower level of test substance and therefore elicit the change that the assay is detecting because it's based on transcription, whereas the HCLAT is based on like a signal transduction or a protein expression based thing where you might need more to detect an effect.
Okay, so a tiny bit of phthalic anhydride could have been there and the GUARD skin would have picked it up faster or more than the other assays. Okay.
Yeah, correct.
Thank you.
Thank you for that conversation. Mr. Wright.
Yes. First, thanks for an excellent presentation, and also for all the work that your team did that went into it, which was impressive. I have a couple questions. The first one, I don't mean to put anybody on the spot, but I want to kind of make a point, I guess. Did anyone from EPA actually observe any of these COUs by going into an occupational setting and actually watching how the work was done?
So later on today, we have the exposure part of our presentation. And I think that might be a more appropriate venue for that type of question. I'm a human health hazard assessor. Maybe our SSAs might have additional information to provide now, but that's what I would say.
Excuse me, that's fine. I wasn't sure exactly where I should ask that. I've got two others, but I can wait till that presentation.
Mike, if they fit here, we can talk about them now. If they're directly related to this segment.
One of them is somewhat related to it. And that is, did you consider concurrent exposures to any other sensitizers? For example, isocyanates.
Pepperell EPA, we acknowledge the co-exposure was occurring in all of the epidemiological studies that were considered for the inhalation part. And EPA cites it as a limitation of those studies. But beyond that, we did not. I don't know if anyone else on the team in DC has anything additional to add.
Hi, Anna Lowett, OPPT Senior Science Advisor. I guess I would also maybe defer that one to our exposure assessor later. I just want to remind you that most of our TSCA risk evaluations are done on an individual chemical basis. But we do recognize that some of those epidemiology studies do include co-exposures.
Yeah. Thank you. And the last one really does have to do with the occupational presentation. So I'll wait.
Okay. So, all right. Thank you, Mr. Wright. And let's see, we can go back to Dr. Gadia.
Sorry, I have one more question. This is on slide 140. I think on the SARA ICE model, you made a comment that it is protective of 99% of the population. But the numbers that you presented previously, or typically when you derive these numbers, you want to look at the 95th percentile. Could you comment on why you chose 99% protection with SARA ICE when selecting a POD?
I can, but someone that is better able to do is my colleague, Emily Renke. So give me a second to switch out.
Thank you.
Hi, good afternoon. My name is Good afternoon. My name is Emily Ranke, GDIT contractor supporting Nicedum Arriva. Sorry, lots of buttons. So the Sarah Ice model, the way that it was designed was actually to predict that 1% sensitizing rate in a human patch test eligible population. The reason for that is that the underlying human data actually tends to, I want to say converge, but is most representative around 1% as opposed to that 5 percentile. And so the model was designed to get as close, really in skin sensitization, you're trying to get as close to that no effect skin induction level, and that 1% gets as close as possible without statistical noise that you get below 1%.
So is it still, or is it more conservative? Is it, or, okay.
Yeah, it's more conservative than the 95th percentile would have been, because it's 90, that would be a 5% of the population versus a 1% of the population.
And so I'm just thinking out loud. And this is again, when it comes to sensitization, because you're, I don't know what population sort of number do you have when you derive these, or is it a Bayesian model that is used?
Yeah, this is based on the Bayesian model that is used to.
Okay, thank you.
Thank you.
Yeah, well, this is George Cobb. One quick question before we get to you, Dr. Robles. On the 1% versus the 5%, just so that I'm clear, the 1%, there's less variability across populations. Is that what I'm hearing? But when you get to the 5%, there's more variability across study populations. Is that what I heard you say?
Sorry, up to Emily Ranke, or GDIT contractor supporting Arriva Nicedum. So it's more that the underlying data for the to build the model does better at 1%. There's more underlying data at 1% than there is at 5%.
Okay.
And so that's why it's predicated as that EDO1.
Okay, excellent. Thank you for clarifying that, because that makes a lot more sense to me. So thank you very much. Dr. Robles?
Yes, first, thanks for the presentation. It was very informative. I have one comment and one question. The one comment is regarding the data from the DPRAs, the key event 1. You guys mentioned that phthalic anhydride hydrolyzes into a non-sensitizer, which is supported by that evidence. I think that makes sense, but just to consider that in the DPRAs, the reaction mixture at the end is made in aqueous solution, because the peptides are diluted in phosphate buffer, and then they reacted with the test sample that it might be diluted in another solvent. But just to comment that as well. The question is related to the KDPRA. In some of the slides, I saw that the prediction was positive for dermal sensitization and for respiratory sensitization, but the KDPRA predicts strong sensitizers or weak sensitizer or non-sensitizer. So just wanted to double check, what do you mean by positive?
Hi, Ash Pepperelli, PA. We wanted to check the TSD to be sure, but strong sensitizer. This might come up in the charge question, but would it be something we should update to say to be more than just positive?
Yes, I think that it would be more accurate to say a strong sensitizer as the result instead of positive.
Okay, I definitely look forward to talking about that when we get to the charge. Thank you, Dr. Islas.
Thank you.
Thank you for that comment. And I agree that clarifying what is meant by positive, whether it's weak or strong, is very important. I have just George Cobb. I have a couple of questions. Maybe some of them are interrelated. So if you go to slide 138, and then there's other slides at least one other slide later, but we don't need to go through all of them that are related to this question. So you've got your uncertainty factors there, and it looks like you've got one because you did an animal study and not a human study. And then you've got the question really is, why don't you have human intervariability for metabolism or for sensitivity to account for pest populations? Why don't you have that there? And maybe that's a question during the broader charge questions if you'd rather have it there, but that's something that is concerning to me.
It's a good question. I definitely would want to talk about it during the charge questions, but for now, so the POD is selected from the EDO1, which is the distribution. Basically, it's based on distribution, but we should talk about this more thoroughly when we get to the charge.
Yeah. Okay, and I think you're right there, and it may be in essence a wash, a mathematical or statistical wash.
Yeah, exactly. We can go into more details on that. But the distribution accounts for population variability, and then the estimate is protective of 99% of the population already. We'll talk about it later in the charge, but
Okay.
I hope that pre-answers.
That's all. It's all good. And this is related, but it's on slide 147. I think. Yeah, that last bullet says that what you're dealing with is a factor of 3 that's appropriate for human toxicokinetic variability. I don't think the things you've described up, at least in number 2, is toxicokinetic variability. And I'm not sure number 1 is toxicokinetic variability either. We can talk about that during the charge questions as well, but I think you'll be careful using the word toxicokinetic in that particular context for this slide. It's my only
Looks like
only thought here.
Anna's gone off camera, so I'll turn over to her.
Yeah, Anna Lowett, Science Advisor at BPT. I just want to make sure that we're keeping our routes separate, that for the dermal, we're using the Sarah Ice Bayesian approach, and for the inhalation, we're using the epidemiology study, and they have different approaches to doing the uncertainty factors, and we just need to make sure we're keeping them straight.
Excellent point. Thank you. Okay, perhaps we're done with questions. Thank you for getting us through this, for the presentation and for the question and answer period. It's very much appreciated. So now, make sure I haven't lost my place. Occupational and consumer dermal exposures from Aaron Murray.
Yep. Thank you very much. Hi, everyone. My name is Aaron Murray with US EPA, and I'll be going through background information for charge questions related to dermal exposure of phthalic anhydride. Next slide, please. Looking at the map of risk evaluation documents, information on dermal exposures presented in the consumer and indoor exposure technical support document and the environmental release and occupational exposure technical support document. Aspects of the physical chemical assessment may serve to inform the consumer and occupational dermal exposure assessments. And these dermal exposure assessments go on to inform the human health risk characterization and the draft risk evaluation. Next slide, please. For charge question 13, let's first go over the background of the occupational and consumer dermal exposure assessment of phthalic anhydride. In occupational settings, there may be dermal exposure to the solid form of phthalic anhydride, since the chemical is often manufactured, imported, and sold as a flaked solid or powdered form. Dermal exposure may occur from industrial uses, including manufacture, import, and processing, as well as from downstream uses of the chemical, including laboratory use and fabrication of final products. There are also liquid formulations containing phthalic anhydride that result in dermal exposure from occupational or consumer use. There are several commercial and consumer products that list phthalic anhydride in the safety data sheets. Products such as paints, coatings, adhesives, sealants, hydraulic fluids, and laboratory chemicals. As mentioned in the previous slides, the dermal POD is based on induction of sensitization at the level of 45 micrograms per square centimeter. And therefore, the goal of the dermal exposure assessment is to quantify the amount of phthalic anhydride deposited on the skin surface in terms of mass per area for each occupational and consumer exposure scenario. Next slide, please. For charge question 13A, we will focus only on dermal occupational exposure to the solid form of phthalic anhydride. During manufacture and import, workers may experience dermal exposure from the flaking and bagging process or while handling bags in preparation for shipment. During phthalic anhydride processing, workers may experience dermal exposure from activities such as manually dumping bags or handling the empty bags. During laboratory use, workers may be exposed from transferring phthalic anhydride from a bulk bag into containers for storage or use, or while handling full or empty bags. Lastly, workers may be dermally exposed to dust containing phthalic anhydride from fabrication activities such as cutting or grinding final products with phthalic anhydride content. EPA did not identify any dermal loading data specific to phthalic anhydride. However, EPA did identify 2 studies that quantified dermal loading of solids from similar substances and occupational activities. The first study from Lansink and colleagues measured dermal loading of calcium carbonate during occupational activities, including collection of raw material, handling of empty bags, and manually dumping and mixing. Measurements were collected by workers wearing cotton gloves that covered the hands and forearms. The 2 main limitations of this study are 1, adherence to cotton gloves may be greater than adherence to skin, and 2, the study provides only the total mass deposited on the gloves, but the exact surface area affected was not reported. The second study from Houston and colleagues measured dermal loading of zinc oxide for 2 scenarios: manual dumping and contact with a dusty surface. Measurements were collected using wet wipe samples from palms, backs of hands, and forearms. The 2 main limitations of this study are 1, wipe sampling methodologies may result in underestimation of skin exposure, and 2, the study notes that zinc oxide has low skin adherence, likely due to its high density and tendency to agglomerate. Next slide, please. This table provides an overview of the elements considered in selecting the best available surrogate data for the occupational dermal exposure assessment of phthalic anhydride solids. The table shows a side-by-side comparison of the Lansink and Houston studies in relation to the assessment of phthalic anhydride for various parameters. As mentioned in the previous slide, the Lansink study evaluated the dermal loading of calcium carbonate, whereas the Houston study evaluated the dermal loading of zinc oxide. Calcium carbonate and phthalic anhydride are much lower density materials than zinc oxide. As noted in the Houston study, the material density is an important physical property that, with respect to skin adherence, and the high density of zinc oxide is likely a reason that zinc oxide exhibits low skin adherence. Next, the types of activities evaluated in each study were important consideration for relevance in the phthalic anhydride exposure assessment. There were 4 dermal exposure scenarios among the various occupational conditions of use involving solid phthalic anhydride. Landsync evaluated 3 out of the 4 relevant scenarios and did so in a workplace environment. Houston evaluated 2 out of the 4 relevant scenarios, but did so using an experimental setup. After careful evaluation of both studies, EPA concluded that there is greater scientific evidence to support the use of surrogate dermal loading data from the work of Landsync and colleagues, since the study evaluated a wider range of tasks applicable to occupational uses of phthalic anhydride and used a substance with physical properties that more closely resemble phthalic anhydride. Next slide, please. For charge question 13B, we'll shift focus to dermal exposure from liquid formulations, which is relevant to both occupational and consumer uses. This table shows the various settings, products, exposure scenarios, and applications considered in the risk evaluation. For both occupational and consumer uses, there are several paints, coatings, adhesives, and sealants that contain phthalic anhydride. Some of these products are applied through non-spray methods such as brush, roller, or bead applications, and some of these products are available in aerosol cans intended for spray application. There are also several liquid formulations specific to occupational settings, such as paints, coatings, and epoxy resins that are applied through spray guns. Workers may also experience dermal contact during the use of laboratory mixtures or during hydraulic fluid changeout. Liquid formulations containing phthalic anhydride are non-aqueous materials that are viscous or oily in nature. As stated in the previous slide, EPA did not identify any dermal loading data specific to phthalic anhydride. Rather, surrogate data from the 1992 US EPA liquid retention study were used to estimate dermal loading. In this liquid retention study, investigators conducted experiments using oily liquids to determine how much material will transfer to the skin from 2 distinct scenarios: rag handling and full immersion. Rag handling experiments measured the transfer of oily liquids from saturated rags to the hands of participants, and these data were considered representative of dermal loading from non-spray application scenarios, since contacting a rag is similar to incidental or routine contact of the material on a surface. Full immersion experiments measured the transfer of oily liquids to the hands of participants from full hand immersion in the liquid. And these data were considered representative of dermal loading from spray application scenarios, since both immersion and spray coating may lead to skin surface saturation. In order to verify the applicability of these data to the scenarios in the table above, EPA compared dermal loading data from the liquid retention study to estimates provided in the detailed analysis of available dermal loading data from the Risk of Derm project by Marcourt and colleagues. Next slide, please. This table shows a comparison between dermal loading data from the US EPA liquid retention study and dermal loading data summarized in the Risk of Derm project by Marcourt. For non-spray application scenarios, EPA used rag handling data from the US EPA liquid retention study, resulting in dermal loading values of 1.4 to 2.1 milligrams per centimeter squared. Similarly, Marcourt reports dermal loading values for rolling of recently applied styrene and polyester boat building, and brushing or rolling of relatively viscous liquid products ranging from 1.3 to 2.7 milligrams per centimeter squared and 1.2 to 9 milligrams per centimeter squared. For spray application values, or for spray application scenarios, EPA used immersion data from the US EPA liquid retention study, resulting in dermal loading values of 3.8 to 10.3 milligrams per centimeter squared. Similarly, my court reports dermal loading values for low pressure spray application, spray painting large areas, and spraying marine anti-fouling paint as 4.8 to 14 milligrams per centimeter squared, 3 to 12 milligrams per centimeter squared, and 4.2 to 16.6 milligrams per centimeter squared, respectively. Though dermal loading values may vary among available data based on a variety of factors, the data presented in the US EPA liquid retention study are consistent with available data for the relevant uses considered in the exposure assessments of phthalic anhydride. And next, Laura Karnavik will discuss the dermal exposure sensitivity analysis in consumer uses.
Thank you, Aaron. My name is Laura Karnavik from EPA, and I will be presenting on the dermal sensitivity analysis for consumer exposures specific to charge question 13C. EPA performed a dermal exposure sensitivity analysis to show the impact of varying weight fractions and dermal loading values on dermal exposure risks, also known as MOEs. In the figure shown in this slide, the horizontal axis in light gray shows the range of weight fractions by product type. For example, the weight fraction of phthalic anhydride in adhesives range from 0.1 to 5% by weight. These values were obtained from the product SDSs that were publicly available when the analysis was conducted. The vertical axis in multiple colors shows the range of dermal loading values used in the dermal analysis. For example, in yellow, we have increase in dermal loading values obtained from the US EPA 1992 WIPE experiment for liquid product study, described in detail on the previous slides. The sensitivity analysis matrix shows the MOE values for the specific weight fraction and dermal loading combinations. The pink background and red font cells within the matrix are for the MOEs that are below the dermal benchmark of 1. The consumer dermal exposure sensitivity analysis demonstrates the impact of varying weight fractions and dermal loading values on dermal risk estimates. Next slide, please. This concludes our presentation of phthalic anhydride risk evaluation dermal exposure assessment. Thank you for your attention. I'll turn it back over to Dr. Cubb for any questions from the committee related to charge questions 13A, B, and C.
Thank you for getting that information together for us. And see Dr. Chasen has her hand raised.
Thank you very much for this presentation. I have some sort of general, not specific to your question, if you'll indulge me. This has to do with the assumptions or how the data in the studies are used. For example, Lancek et al., where you have presumably dry powders, and the worker is presumably wearing gloves. So is it assuming that there would be any other protective clothing worn by those kinds of workers doing this in the industry? Do you know?
Aaron Murray, US EPA. And so the Lansing study, the cotton gloves that were worn, they were worn to collect the material, not to protect the worker. So the workers were handling calcium carbonate, wearing cotton gloves, and the cotton gloves were collecting the material. Subsequently, the gloves were used to determine how much calcium carbonate was transferred during these different activities. And so that the gloves weren't necessarily being used for protection, more for collection.
Yeah, I understand. But I mean, would you assume, for example, that that in the real world, people would be wearing cotton coverings themselves?
Well, we wouldn't assume a worker is wearing necessarily cotton coverings, but the purpose of this assessment is to determine how much material can get transferred to the skin for a given contact, right? So a worker is, for instance, dumping a bag into a reactor. We want to know if the worker is not wearing any protection at all, how much can get onto their skin? What type of loading can we expect from that type of activity?
And
from there, we can determine the risk and then determine potentially the risk.
So over
mitigation.
what percentage of their body would you say this would, for these kinds of activities in the industry, assuming they're not wearing a leather apron or something like that? Do you think, I mean, what is the standard approach that you're using when you apply studies like that?
And so in this particular instance, right, phthalic anhydride is a dermal sensitizer. Induction of sensitization is the endpoint. So we're interested in how much mass per area the worker contacts. And so that's what we're quantifying here. How much mass per area is being contacted by the worker. We're not assuming some level of surface area. We're saying how much mass per area gets on the skin, right? So if it's
I'm
1
asking,
milligram
how
per
much
centimeter.
skin are you assuming, essentially?
But that's the thing, that there is no assumption of surface area in this because we're looking at mass per area. So if you have 1 milligram per centimeter squared on the skin, for instance, that's the endpoint that we're looking at. So 1 milligram per centimeter squared could be just on your fingertip, or it could be on your whole hand, but the endpoint is mass per area.
Yeah, I understand, but forget about the sensitization. I'm sort of asking what the process would be for using this kind of a study to look at the amount of material that might be available to the workers in industry. So see, I understand your point, and it's well taken, but I think the question comes up as to what the workers are doing, and assuming this industry is not creating a sort of dust-free space or anything like that, who these workers are and how you would handle that kind of data. Maybe you could.
And so as far as, like the PPE that's generally worn, is that kind of what you're getting at? The PPE that's generally worn, a lot of the safety data sheets will mention, the need to use polylaminate gloves. A lot of the, workers will also be wearing like an apron or protective shoes and footwear. However, as far as for determining exposure, that's not part of the exposure assessment. That would be part of the risk mitigation.
Would you indulge me with two other questions? This is, once again, it's sort of general. In reading this and other places where, quote, occupation tasks are discussed, I kept looking for what happens to the containers. And I was either this or the HHCB where I think the statement was that they were taken off site. But then as far as the discussion went, they kind of stuff that just kind of disappeared. So are people who deal with the disposal of the bags and or other containers considered workers under occupational for these assessments?
Yeah, so a worker would, like I was saying before, perhaps after they've emptied a bag into a reactor, they may, remove that bag, throw it into like some type of bin that is then collected by a disposal company. that then takes that off-site. So once the disposal company collects that material, it's now a different COU. So the worker taking the bag, throwing it into a disposal unit, that's all part of the worker at the processing facility or manufacturing facility.
Right, at that facility, but the chemical keeps going, and I was wondering why the next person who handles that, and somewhere I saw that it's somewhere between 0.5% and 3% of the chemical still remains. So somebody walks away with the bags in a container, that's disposal. And I was wondering how that's dealt with in the risk assessment.
And so those types of materials are generally taken for incineration. And so after the material has been disposed of, it's assumed that it's going to an incineration unit.
With no worker exposure between the time that you put it in the container and then the time it disappears into an incinerator?
So after leaving the facility downstream, it's assumed that, yeah, the next step would be the incineration.
Okay. And then I had one other question. Are any of these kinds of workers, assuming that they're getting some of the powder on their clothes, is there any way to look? Are you considering any trichome residues on the clothes or shoes or hair?
I guess, like, once again, we're looking at dermal sensitization, so mass per area on the skin, right? So, you know, we're looking at how much can get transferred from some type of activity to the skin surface. That could also be the clothing surface. So there's, I guess, we don't specifically look at how much is getting transferred to the clothing. We look at how much could potentially be getting transferred to the high exposure surface areas of, like, the hands and the forearms.
So the risk assessment does not include, certainly not, I couldn't find it anyway in the consumer side, but so the possibility, just like of the chemical leaving the plant, and thanks for your patience, I just wanted to straighten this out. So if the worker leaves the plant and they still have the chemical on their clothes or shoes or whatever, that too is just disappearing. I mean, it's in terms of disappearing in terms of whether or not there's an exposure or risk assessment somewhere in the analysis of hazard or risk, however you want to put it, within. And basically, we're asking who's exposed. I get your point about the per square inch. That's really not my question. I think I'm looking at who's exposed. So, and I think you're saying that that's not addressed in these assessments. Is that correct?
So are you asking if a worker gets phthalic anhydride on their clothing and then they leave and somebody touches their clothing, is that assessed?
Well,
is that
if
the
they go
question?
home and I mean, that would be another assessment, bringing a daily dose of that back into the home. And I didn't see that in, is that correct? Or
Yes, that's correct. There's no take-home exposures considered in this assessment.
Okay, and there's nowhere that I'm missing consideration of the exposure to whoever the company is that's taking the chemical out of the building and disposing of it permanently, correct?
The disposal by the worker at the facility is part of the exposure assessment.
I'm asking you a different question, but I think I got it. Thank you for your presentation, Dr. Murray. I appreciate it. Thank you.
Right. Thanks for that discussion. And Dr. Samuel.
Yes, thank you very much to the EPA for the excellent presentation. And also, I just wanted to applaud the agency's efforts to look a bit more deeply into the loading literature to consider some new data that has not previously been considered. So I'm really happy to see that and congratulate the agency on their assessment here. I just had two quick questions, and I believe they may have been answered by Dr. Chasen's discussion, but just to confirm, with respect to the dermal exposure assessment and the sensitivity analysis specifically, it sounds like number one, the surface area of skin was not considered. I think that was pretty clear from the discussion with Dr. Chasen, but I had the same question for frequency of exposure. Was there any consideration for frequency of exposure in the assessment of dermal exposure, or specifically the sensitivity analysis?
A little bit of arm, a quarter. Hi, this is Kathy Denisio, Senior Science Advisor, OPPT. Can you clarify, are you asking about the consumer or the occupational assessment, or both?
I think it could be both. I'm just interested in, to the extent to which frequency of exposure was considered in either consumer or occupational in the analysis.
Okay. Do you want to go ahead and answer that for occupational, Aaron?
Yeah, I can answer that. Aaron Murray, EPA. And so the endpoint that we're looking at here is an acute endpoint. So 45 micrograms per centimeter squared at the acute level. And so frequency didn't come into the equation when calculating the risk value. So we're looking at what's the potential for acute exposure of phthalic anhydride for these various activities.
Thank you, Dr. Murray. So in other words, it was assumed that a single exposure at a sufficient concentration would then rise to the level of sufficient exposure.
Yes, that's right.
Okay, thank you. Thank you very much. And I had the same question, I guess, for both consumer and occupational.
Right. Yes, Kathy Denisio, Senior Science Advisor. We're just going to clarify that we're not looking at a chronic hazard. So the acute exposure, the one-time exposure is what was considered.
Okay, thank you very much. So single exposure and concentration based only, with no consideration for surface area of the skin for either of the two, either occupational or consumer. Is that, do I have that right?
That's correct.
Yeah, I think that was a question.
Hi, Anna Lewis, OPPT Science Advisor. Just to be precise, we recognize that in sensitization reactions, chemically, a minimum of 2 exposures would be required, and that initial first exposure leads to the second exposure that eventually causes a sensitization. So I wouldn't take the acute single day as literally as maybe some might. We're talking about very short-term events, not chronic or many days repeated. I think deserves some clarification. Thank you.
Understood. Thank you, Dr. Lowett. That's helpful. Thank you so much.
All right, great. Good conversation. Let's go to Dr. Ottinger.
I really appreciate so this Marianne Ottinger, I really appreciate the surrogate studies that you use to look at liquid exposure, and just had a question about when you model for risk, is there any consideration of other chemicals that would co-locate with the phthalic anhydride in the liquid formulations, and would that then be considered in your models of risk?
Aaron Murray, US EPA. And so the dermal loading that we used only considered the dermal loading of phthalic anhydride. We didn't consider the dermal loading of other substances mixed with the phthalic anhydride.
Okay, thank you.
Kathy Denisio, Senior Science Advisor, EPA. I would just reference also Anna Lowett's earlier response about the TSCA risk evaluations focusing typically on a single chemical at a time.
Right. Great. Thank you. And then Dr. Gadia?
Thank you. I do want to build up on the previous discussion in terms of, because you're not accounting for the skin or exposed skin area, do you account for the amount that is absorbed? And then do you account for the differences in skin absorption across different regions of the body?
Aaron Murray, EPA. And so again, the POD is induction of dermal sensitization. So we're considering how much contacts the skin, not how much is necessarily absorbed into the skin. So how much contacts the skin per area. So we have a POD of 45 micrograms per centimeter squared, and that's what we want to compare to. So we have to say, okay, if a worker or a consumer is doing activity XYZ, how much mass per area can we expect them to get onto their hand or their forearm or some body part while doing this activity? Is it going to be a very dense amount of material per area, or is it going to be a relatively dilute or small amount of material per area? And so that's how we're looking at the exposure to the dermal part and then comparing to our POD that's based on sensitization. So the absorption itself doesn't come into play here.
I still fully don't understand what all of this, but when the powder is loosely sitting on anybody's hand or skin, it is unlikely to create sensitization. There has to be some level of absorption for it to interact with the proteins. So that's, and again, how you've not accounted for the area of skin is still puzzling to me, but thank you for your response.
Right. Dr. Lee.
Real quick, sorry to interrupt, Asha Pepperelli, PA.
Please, if you've got clarifications, please.
Quick clarification from the hazard side of things on myself and Emily Renke. So real quick, the reminder that from the hazard perspective, Langerhans cells are capable of sampling from the stratum corneum. Dermal absorption is not therefore required for the sensitization, although it is important for it to permeate a little bit. EPA did not use absorption for the assessment.
Emily Renke, GDIT contractor supporting Nicetatum Arriva. And then just to clarify on the dose per skin area that we're talking about, the model that was used to derive the point of departure is estimating that micrograms per centimeter squared that you are looking at. And so it is, you don't necessarily need to have the entire, exactly how much the exposure is. It's in that 1 centimeter squared, if that much of it, if 45 micrograms is on there, that would be considered a sensitizing dose. You could also look at it alternatively if you're looking at a total of 45 micrograms over a larger surface area, but your average is going to be that 45 micrograms per centimeter squared is causing that sensitization. And so I think that while it is being asked that, you know, what's the exposure on the hands or arms, that is independent of what the point of departure is being used for, which is that how much needs to be on 1 single centimeter squared area of skin to cause a sensitizing reaction. Hopefully that helps.
Yes. Thank you. Dr. Lee.
Okay, this is Dr. Lee, SACC member. So I do have a question regarding to the powder handling worker exposure. So if you have your draft environmental release and occupational exposure assessment document at hand, and maybe you can turn to section 3144. And in table 3-5, you list a number, for example, for high exposure workers, the central tendency number, the loading is 0.253 milligram per centimeter square. And for higher end, the number is 0.57 milligram per centimeter square. So when I look at how these numbers were derived, I paid attention to that you got this number by calculating some numbers from Lansing 1996. And from that report, you had the total dermal loading data, the total dermal exposure data. For median, you have 476 milligram per day. And for 90%, 90th percentile, your number is 1,064 milligram per day. And if you pay attention to the unit is milligram per day. And then later you divide this number by the total surface area of absorption. And you assume this surface area is the hands plus part of the forearms, and the number is 1,855 centimeter square. And if you divide this number together, you would get some numbers with a unit of milligram per centimeter square per day. But when you express this number in table 3-5, and your unit is milligram per centimeter square, which means you miss day from the unit. So I was wondering, number one, whether that means you try some way to drop the unit of a day of D from the total unit, for example, by multiply the number by 1 day. And number two, if that's the case, that means you are assuming the whole surface area, the whole exposure surface area, which means the hands plus the forearm, is loaded or contaminated with the dust 1 day, once per day, and all this dust is thermally absorbed. And I was wondering whether this is your consideration during the derivation of this number.
Yeah, Aaron Murray, EPA. Yeah, thank you for looking into that so thoroughly. And so, as you said, the Lansing study, it reports the total mass deposited onto the gloves for a given activity. So perhaps the workers were dumping bags, and the study, it reports, the number of bags that they were dumping. They were dumping anywhere from 4 to, I believe, 20 bags of material. And so the collection on those gloves would be from that collection of activities. So the dumping of bags led to a certain amount of dermal loading onto the gloves. And so Lansing reports that as mass deposited on the gloves per day.
Right.
Though it's only, a small amount of activities that are leading to that dermal exposure. And so, as you said, the total mass was reported, and also they said they're wearing cotton gloves with a forearm cap that extends up the forearm. And so to estimate, our endpoint, right, to estimate the value we want to compare to the endpoint, we have to estimate how much surface area that material is being deposited throughout the cotton glove.
Right.
And so the assumption is that the surface area of the hand and part of the forearm could be covered during the dumping or bag handling. And that's how we go from the total mass deposited to a mass loading per area.
Yes, in that case, the number from Lansing is mass per day. And if you
Yes.
divide this number by the surface area, which is a centimeter square, and you should end up with milligram per day per centimeter square.
Well,
but now you
yeah.
drop a day from it.
And so I agree. Yeah, Lansing reports milligrams per day, but it could equivalently be milligrams per activity. Lansing's reporting how many milligrams are deposited for a given activity, and they're saying there's 1 activity per day.
Mm-hmm.
And so we're trying to say in our risk evaluation, how much mass is being transferred to the skin for a given activity.
Okay, so that means you assume this activity happens once a day. So this is in explicit.
Yes, so
Okay.
we're trying to get quantification over mass deposited per activity. That's correct.
Okay, thank you so much for the clarification.
Yeah, thank you.
Thank you. Mr. Wright.
Thank you. These are very simple, and they have to do with COUs primarily. But before I ask those, let me ask another simple one. And that is for workers exposed to the powdered form, what's the typical particle size? Or was that measured?
Aaron Murray, EPA. I don't know that off the top of my head, so that's something we'll need to get back to you with.
That's fair. Thank you. In the COUs, there are a lot of assumptions made, and I'm trying to figure out what they're based on. For example, one of the high exposure tasks, maybe the highest exposure task, is reactor loading. That was assumed to take place once a day, or at least once during an 8-hour work shift, and to last for 30 minutes. How did you come up with that kind of assumption?
Yeah, Aaron Murray, US EPA. And so I guess I'm curious where exactly in the risk evaluation that would be. Is this part of the dermal exposure assessment?
I'm not sure where I read that. I should have written it down on my notes, but I did not. It may have been in some of the supporting documentation for table 6.2, which is where some of these questions came from.
So I'm not sure exactly the answer to your question now. That would be something else I would need to get back to you with here.
Okay. Well, in a more general sense, you did, I think in a number of places, describe a particular COU. How did you get those data? Those descriptions?
So how did we define COUs? Like throughout the phthalic anhydride evaluation, how did we identify all the different uses?
Yeah.
And so we identify the different uses by looking at first the CDR data. So the chemical data reporting, manufacturers, processors, importers will submit information to that database about how much they're producing or importing or processing, and what are the downstream uses of the chemical. So it's going into paints and coatings, it's going into plasticizers, etc. So that's one area that we look at for conditions of use. And then we also look at the different products that exist that contain phthalic anhydride and, for instance, the safety data sheets. So safety data sheets will have information about the chemicals within the product. And that is another indication of how the product or how the chemical is used.
But you don't actually look at what a particular worker in a particular COU would do during a typical workday.
And so to get those type of like worker activities specific to a processor or a manufacturer, you had asked a question earlier about actually going to the sites and seeing what they do there. We weren't able to actually go to a site and actually visit a phthalic anhydride processor or producer, but we were able to do, what's called a virtual tour. So we had, a producer walk us through all of the different worker activities, the life cycle of the chemical within their factory. And so we were able to get information like that through at least a virtual tour.
Okay. Thank you. One other one. Were maintenance workers in the category of worker or an occupational non-user?
They're in the category of worker. And so for phthalic anhydride, we actually had several data points from maintenance workers specifically, as well as equipment operators, and also ONUs. And we were able to see the levels of exposure for equipment operators, for maintenance workers, and they were very similar. And we did combine those two into a singular group that we just call workers. And we clearly, in the risk evaluation, described that workers for like a manufacturing setting, a processing setting, do include both equipment operators and maintenance workers.
Good. I'm glad you did that because in some of these past evaluations, EPA has considered maintenance workers to be occupational non-users, and I think that's wrong. I think you did it right. Thank you.
Dr. Chasen's hand again.
Dr. Cobb, if I may, I have one quick communication piece for the committee.
Yes, please.
The walkthrough that Aaron mentioned is on the docket for the submission for Exxon. So if the committee would like that information, it can be provided by Olive this afternoon, as well as additional information on the surface area point. An expert, Dr. Frank Gerberick, was so kind as to provide additional information for the record to clarify the surface area point that many of the committee members were discussing. And we can provide that later this afternoon through ALA. Thank you.
Great, thank you. Dr. Chasen.
Thank you. I just wanted to take a minute to acknowledge that it appears to me that there were sprinkled throughout these different exposure assessments for the chemicals, as well as discussions in the risk assessment, and including the appendices, seem to have things that are real improvements, at least from the perspective of the SACC, things that we had recommended in previous conversations. And I just wanted to say that I appreciated seeing those. Maybe serendipitous, but I'm just going to go ahead and assume that it was because we recommended it. But thank you.
Thank you for that comment. Okay, we are at 4:10 Eastern, and we're just before part 3. Maybe if we can take a quick 10-minute break and come back and finish up the rest of the EPA presentations here this afternoon, and hope to get into public comments. So if we can come back at 20 minutes after the hour. Okay, we're back for the last part of the afternoon session for our SACC review of 5 different chemicals. So if we can move now to our risk evaluations for the HHCB, and I believe Dr. Groza will present this for us.
I think we have the last part of the phthalic anhydrides. The last section.
I apologize. I missed that we hadn't gotten to that. So let's please move to that overview of the phthalic anhydride risk evaluation.
Hi, this is Karen Eisenreich, EPA. We actually did complete that section. Laura did give her.
That's what I thought.
Yeah, right, Laura? I'm not wrong. Correct?
No, there is more.
There is more. Okay.
Always
My
more.
bad. Sorry.
Okay. So let's proceed to the consumer exposure.
Thank you so much. No worries. Hello, everyone. My name is Laura Knavik with EPA, and I will be presenting on the phthalic anhydride consumer inhalation
exposure assessment, specifically on the input selected for the inhalation exposure modeling performed in the consumer exposure model CEM, as presented by charge question 15. Next slide, please. Consumer inhalation exposures from spray paints and sealants were calculated using the consumer exposure model, CEM. Some of the inputs needed for CEM modeling were weight fractions, duration of use, volume of product used during application events, and the environment the product is applied or used in. For each one of the inputs, EPA can either use CEM defaults if those are deemed appropriate, or can investigate product-specific use patterns to obtain product-specific input values, which would lead to more representative exposure concentrations. Next slide, please. Thank you. In the phthalic anhydride consumer assessment, weight fraction values were obtained from product SDSs that were publicly available at the time of publication. For duration of exposure and frequency, EPA reviewed public forums dedicated to do-it-yourself DIY home renovation projects that match the identified products for small and large projects. EPA also used information from product labels and technical data sheets specific to products being evaluated. For example, the selection of 270 minutes as a duration of use for large projects with spray application of the product considered time to prepare the sprayer for use, time to spray 2 coats, which was a recommendation from the product label, and time to empty the sprayer reservoir after use. The mass of product used for the large project was based on product label specifications. The specifications provided a guideline for the amount of product needed to cover a certain surface area. The environment of use was selected based on product label instructions and CEM default inputs. For example, based on product descriptions, a large project was assumed to be completed indoors. As an example of such projects would include refinishing the floor of an interior room of a home, an activity which cannot be moved to an outdoor environment. For the small project spray application, EPA selected the garage as the environment of use because the small and medium-sized items can easily be removed from the indoor environment and spray painted in the garage, which is an environment more appropriate for the type of DIY work. EPA concluded that the inputs used are representative of product use patterns and provide realistic exposures for users and bystanders. Next slide, please. This concludes our presentation of phthalic anhydride consumer inhalation exposure assessment. Thank you for your attention. At this time, we will address questions with regard to charge question 15.
Thank you. And are there questions from the committee? I'm not seeing any, so thanks again, and we can move on to the now the HHCB assessments.
Hi, this is Brian Groza, DPA, and just a minor correction to the agenda. I do not have a PhD. I'm an exposure assessor in the existing chemicals risk assessment division. I'll be presenting the environmental exposure characterization for HHCB and surface water. However, before diving in, I'll provide some necessary background and context to frame today's sequence of HHCB technical presentations. Next slide, please. I want to acknowledge the multidisciplinary team that is responsible for developing the draft HHCB risk evaluation. I'd like to thank all of the authors, contributors, and technical support colleagues for their hard work. Next slide, please. The outline for this portion of our technical presentation is as follows. After a brief introduction on HHCB and relevant background, this presentation will detail charge questions 16 and 17, centered on environmental exposure for the characterization of HHCB surface water concentrations and HHCB bioaccumulation and exposure via fish consumption. Charge question 18 will detail occupational exposure with an emphasis on the iterative tiered approaches for human exposure assessment. After that, consumer exposure will detail the relevant portions of technical information for charge question 19. Finally, human health hazards and related topics will be detailed relating to charge questions 20, 21, 22A, 22B, and 4B. Next slide, please. HHCB is a polycyclic musk used widely in perfumes, cosmetics, shampoos, lotions, detergents, fabric softeners, and commercial or household cleaners. In the US, most HHCB is imported rather than manufactured. EPA first published an HHCB assessment in 2014 following a 2013 draft that was open for public comment and reviewed by an independent external panel. The 2014 assessment identified no environmental or human health risks. In December 2019, HHCB was designated a high priority chemical under TSCA. In August 2020, EPA released the final scope defining conditions of use, exposed populations, and exposure pathways. The present risk evaluation incorporates additional data and more robust analyses compared to the 2014 assessment. Overall, conclusions are generally consistent with prior findings. HHCB is semi-volatile, susceptible to photolysis, and not expected to persist in outdoor air. It has low water solubility, does not hydrolyze, and degrades slowly via aerobic and anaerobic biotic processes under some conditions. HHCB partitions to sediment, bioaccumulates in aquatic biota, and is metabolized to more polar excretable compounds. It has been detected in surface water, sediment, soil, and aquatic tissues across the US, consistent with its fate and transport profile. Exposure pathways evaluated include inhalation for workers and consumers, and ingestion for the general population. Environmental pathways include industrial and down-the-drain releases to surface water that lead to detectable concentrations in surface water, sediment, and fish tissue. The human health hazard assessment characterizes cancer and non-cancer hazards for oral, inhalation, and dermal routes, and derives points of departure, or PODs, as appropriate. The environmental hazard assessment characterizes acute hazards using species sensitivity distributions and develops chronic thresholds for aquatic and terrestrial organisms. The current draft risk evaluation quantitatively assesses exposure using a tiered framework, beginning with screening level methods and advancing to more refined data-informed analyses when warranted by the pathway and population. Accordingly, the draft HHCB risk evaluation includes both screening level and refined assessment approaches. Next slide, please. When applicable and appropriate, EPA uses tiered approaches to conduct risk assessments. A tiered assessment is a stepwise process that begins with conservative screening assumptions and methods and progresses to a more refined data-rich analysis as needed. When conducting a tiered exposure assessment, after each iteration, the question is asked, is the level of detail or degree of confidence sufficient to achieve the purpose of this assessment? If the answer is no, a series of iterations will continue until the answer is in the affirmative, new input data are generated, or the available data, time, and resources are depleted. Lower tiers, that is screening level tiers, are simpler to apply, require fewer inputs, and produce conservative outputs, results that we are confident overestimate real-world exposures. Higher tiers, that is the more refined tiers, require more detailed inputs and yield more realistic site or scenario-specific outputs. Progression through tiers occurs only when supported by available data and continues until concentrations are below levels of concern or a risk management decision can be made. Next slide, please. So now we'll begin the technical presentations related to our HHCB charge questions. As we move through these presentations, the relevant charge question will be displayed in the upper left-hand corner of the slide in the green box. I will be presenting on the environmental exposure characterization for HHCB in surface water to support charge question 16. Next slide, please. This slide outlines today's HHCB presentations by charge and links to the relevant documents. We'll use it as a roadmap throughout the HHCB presentations. To keep it readable, the table lists only the charge and the documents for each presentation. And each slide will display the active charge question in the green box at the upper left for easy reference. The remainder of my presentation focuses on charge question 16 and is supported by the TSD covering physical chemistry, fate and transport, environmental releases, and the environmental exposure assessment. Next slide, please. The draft HHCB risk evaluation contains multiple documents. This document map is meant to orient you to how they relate. The TSD on the physical chemistry, environmental fate and transport, environmental releases, and environmental exposure assessment is relevant to charge question 16. Next slide, please. EPA is seeking feedback for HHCB on surface water concentrations from commercial and consumer down the drain releases. EPA is not seeking feedback on industrial releases because there are limited direct industrial releases of HHCB to surface water. But widespread use of HHCB in common commercial and consumer products such as detergents and cleaners. Therefore, community scale releases from commercial and consumer product use that go down the drain and aggregate at publicly owned treatment works or POTW are a primary focus of this risk evaluation. To assess surface water concentrations due to industrial releases, EPA conducted a site-specific analysis linking each facility that reported industrial releases of HHCB to EPA's Toxics Release Inventory, TRI, to its receiving water body using the National Pollution Discharge Elimination System, or NPDES permit. To assess surface water concentrations due to the commercial and consumer down the drain releases, in the absence of site-specific use and disposal data, EPA developed generic per capita loading rates based on the expected use patterns of relevant products in commercial and consumer settings. The same approach used to link industrial releases to receiving water bodies was then applied for a national POTW database rather than a list of industrial releasers. Next slide, please. For the POTW analysis and the draft HHCB risk evaluation, records were pulled from EPA's 2022 Clean Watersheds Needs Survey, or CWNS, which included the facility name, location, ID, NPDES permit, contributing population, and the level of treatment. Using EPA's ECHO database, each NPDES permit was mapped to its receiving water body by retrieving the corresponding National Hydrography Dataset, or NHD. The version is the NHD plus version 2.1. And we pulled the corresponding reach code, which was selected for its integration with the NPDES program, where each reach code identifies a specific receiving water body. We then obtained reach-specific flow estimations from the NHD Plus version 2.1 database to derive the flow statistics used in this assessment, which are the 7Q10, which is the lowest 7-day average flow with about a 10-year recurrence interval, the 30Q5, which is the lowest 30-day average flow with a 5-year recurrence interval, and the harmonic mean, which is a more central tendency flow that's more conservative than the arithmetic mean. The relevant methods here are detailed in section 4.2 of the draft environmental exposure technical support document. Next slide, please. For each POTW with complete flow and input data, we ranked facilities to estimate the relative order of resulting surface water concentrations. This screening step avoids individually modeling more than 13,000 POTWs to characterize the distribution of outcomes. The approach has been applied previously and consistently preserves the relative ordering, allowing us to model representative percentiles from the full distribution. We calculated an estimated load ratio for each POTW as a function of the contributing population, the average per capita loading, and assumed removal efficiency, and receiving water body flow. And then we sorted this data set by the new calculated variable. From the ranked list, we selected the 50th and 95th percentile POTWs, which we refer to as P50 and P95. For more detailed modeling, to represent the central tendency and high-end scenarios. These POTW scenarios represent where we expect to see the P50 and P95 surface water concentrations resulting from the releases. The histogram illustrates the distribution of estimated load ratios, with the load ratio on the x-axis and the frequency or count of POTWs on the y-axis. The details of this analysis are presented in Appendix F of the Environmental Exposure Technical Support document, and the database used to calculate these values is included as supplemental file number 26. Next slide, please. Loading for these scenarios was estimated by multiplying the average per capita down the drain HHCB load by the contributing population for each POTW, and then modeling the discharge to the receiving water body with the point source calculator, or PSC. Modeled concentrations represent conditions at the outfall, assuming an instantaneous, complete mixing in the water column immediately downstream. We are interested in feedback on the methods to estimate down the drain releases and how they were applied to the POTW database to reflect a national distribution. Next slide, please. We prioritized modeled concentrations for the draft HHCB risk evaluation because available monitoring data may not capture high-end conditions near POTW outfalls. As noted previously, the surface water concentrations resulting from modeled industrial releases were minimal and therefore not the focus of this assessment. This table compares the distribution of 7Q10 modeled receiving water concentrations for combined consumer and commercial down the drain POTW scenarios with monitored concentrations from the water quality portal. Many monitoring stations are not immediately downstream of POTW outfalls. However, some higher observations align with our modeled scenario when site conditions match the modeled assumptions. For example, a larger POTW discharging to a smaller water body during a low flow season. Despite differences in how monitoring sites and modeled scenarios are represented, the distributions are broadly similar. Most surface water concentrations were well below 10 micrograms per liter, with an upper tail exceeding 20 micrograms per liter when multiple high exposure factors coincide. These higher concentrations, while achievable near the outfall, are expected to attenuate downstream due to degradation and dilution. We are interested in feedback on how monitoring data and modeling data were used and how we characterize monitoring data for many different locations and conditions. Next slide, please. Thank you for your attention, and we'll pause here to allow time for any questions.
Thank you. Let's turn it over to the committee. I see Dr. Chason.
Yes, thank you very much for that presentation. I understand what you've done and the calculations. I have just a couple of questions about the general issue between which kinds of products EPA is interested in versus the huge number that are actually regulated under FDA. So if I understand this correctly, part of the down the drain, or from other reading, a great bulk of down the drain residue would be from cosmetics, perfumes, washing clothes, where the clothes had either creams or perfumes on them, et cetera, et cetera. This is a huge array of personal products, creams, all kinds of things like that that are not a part of the COUs. I understand that I'm not taking issue to that. It just seemed, I was surprised when I looked at the, if you can go back to slide 176, maybe I can speak it. So when you compare the central tendency, for example, from the modeled versus monitored data, I was surprised that there wasn't a huge, bigger difference there than we're seeing, because there's so much more of the product coming into the water system, apparently, from the many COUs that are not covered at all by EPA. Have you taken a look at that? Can somebody speak to that a little bit? I'm just wondering whether your modeled efforts, mathematics, may be, too high here or something. So maybe you could speak to that if anybody wants to take a guess on what's going on with this.
Hi, this is Kathy Denisio, Senior Science Advisor, EPA. I'll address part of your question, I think, which is just to, which I think you've acknowledged, to clarify that under the scope of TSCA, we are looking at the exposures due to the TSCA conditions of use. So as you acknowledge, not looking at those which, sorry, I had to pop up on this computer screen. Not looking at those which FDA are under the regulatory purview of FDA. So I'd just like to clarify that. And then, sorry, can you repeat the second part of your question? And then.
Oh no, I'm just acknowledging that. It's just that there's so much of that I was surprised at this comparison between monitoring data, which I would presume had a much bigger component in it for the FDA COUs than for the EPA COUs. So I'm surprised that your modeled combined scenarios are greater than the central tendency. I wouldn't have expected that.
You want to go ahead, Brian, and acknowledge how you compared the monitoring and the modeling?
Yeah, this is Brian Groza with EPA, and that just speaks to some of the conservatism built into our modeling. That we do acknowledge that there would be contributions from other non-TSCA sources here, and we did not have a refined analysis or estimation of what those contributions might be, but we would expect other contributions. And also that our monitoring data set is limited, so that's not necessarily the entire universe of what environmental concentrations could be.
Well, thank you, Dr. Groves. And I went back and looked at that too, searching for, the conservatism, which leads me to another question. Could you opine a little bit on how you got to the assumption of, I think it's 92% removal efficiency, because that didn't look conservative to me. That looked a little liberal. But this, like I said, I'm no engineer for these things. So could you tell me how you figured that out?
Yeah, this is Brian Groza with EPA. I would just point to the section 2 of the environmental exposure and physical, chemical, and fate properties technical support document has the details and the citations for where those numbers came from.
Could you tell me that again, please? Where is it?
That's section 2 of the TSD that starts with physical, chemical, and fate properties and the environmental exposure assessment.
Okay, I'll look at that again. Thank you. And I had and a question related to that. Do you have any idea how representative these cleanup processes systems are in the United States? Is that do you know what percentage and what size community would be able to take a look at that kind of thing? I just don't have much background in that. I was going to look that up, but do you know if that's a standard for like 100% of the United States or something? Do you know?
This is Brian Groza with EPA again. I would again refer to section 2 there, and also to the POTW database, which kind of cites the size of these systems, the level of treatment at each one, and can give you more information about that.
Okay, well, I did look in there. I did not see, there's a lot of information about the sizes, but maybe you could tell me, is that I'm looking to see how representative that 92% reduction is, and kind of what happens if it's less than that, or what happens if you have many communities that would be, and I would expect these would be literally across the United States. What happens if you don't have that? So what I'm looking for generically is that if in fact your model is, even with that, getting numbers that are higher than I would have expected, I'm looking for why. There's something here that's not logical to me, and I'm either missing some really key point, which should be easy to find, because I'm looking at a order of magnitude here, not sort of fuzzes around the edge, and I'm not seeing it. So if you maybe you can think about this, if you do see something like that that might help, I'd appreciate it. Thank you, and thank you again for these good presentations.
Yeah, thanks. This is Brian Groza again with EPA, and we can get back to you with some of those numbers and how representative they are.
Okay, let's move on to Dr. Schlenk.
Yeah, just some quick questions. And I'm sorry, I was looking through the document, and I had a hard time finding some of the raw data, but I was curious on your NPDES permitting monitoring data. Was there any direction to target, you kind of mentioned it in your talk, but was there any direction to target wastewater dominated streams? I mean, for example, Trinity River would be one that there's been quite a bit of work on. I'm wondering, was any of that data, surface water data, used for like a worst case scenario for surface waters?
And Groza with EPA. As far as the POTW database, it kind of includes all available examples, of which there are many, like you described, that are more effluent dominated. Getting into the other monitoring data that were available, the fish tissue study that we kind of highlight in there does focus on that kind of a scenario specifically. Yeah.
Well, I'm just wondering whether or not the 25 micrograms per liter value is from like the Trinity River, or is it from someplace else? I just didn't see, I couldn't find the site specific sort of data in there. And if you have a table for where that is, that'd be great if you could point me to it. But I was just curious if you did, because it seemed to me like the best way to go about this is to go to an effluent dominated river and look for a worst case scenario and see if that fits your model, right? I mean, that would seem like sort of appropriate to me, but I'm just wondering, it seems like you went to POTW and then estimated data for that rather than, and then, I mean, did you try to confirm that with surface water monitoring to see how accurate those were, I guess? Is that, yeah?
Yeah, so to a few of those points, the supplemental file, I believe it's number 26 that was called out in that section, has the list of POTWs there. The naming the 50th and 95th percentile, weren't meant to target a specific location to say this is where this is happening, though they are based on real locations. It was more to describe the distribution of potential.
So you don't have that information, is basically what you're saying in terms of the
that
site.
information is in that supplemental file if you wanted to dig into that further.
The
And
site information.
Right, right.
Yeah. And what file, which file is that?
In the supplemental file number 26.
Okay.
And where we did have monitoring data, we did investigate where those locations were, how they kind of matched up with.
Again, I'm not looking at POTW data though. I'm looking for surface water data.
Okay, I might clarify that. Yeah, these are surface water samples, but located just downstream of a POTW.
Downstream. Okay.
Yeah.
Okay, got it. And then one last question. This is just a general, I don't know, maybe we'll save it for the air monitoring, but I spend a lot of time in cars living in Southern California, and I know there's a lot of fresheners in cars. And I'm wondering whether or not any of that exposure, this is non-occupational, I guess. This would just be exposure, whether that is a condition of use aspect that's evaluated by FDA, or is it something that EPA should be responsible for? Because I didn't see that as a condition of use, and it's very predominant, at least where I live. So I'm not an aerosol guy. I'm just wondering why, if that was excluded for some particular reason, or you just didn't have the data. Maybe, I guess that was probably part of it.
Yeah.
I guess.
This is Brian Groza with EPA. There will be presentation on that later, and it is discussed in the consumer exposure assessment in section 2.2 of the human exposure TSD.
Okay, great. Thanks. I missed that.
We're back to Dr. Chason.
Thank you. I had one other question, which I forgot. Could you briefly explain why there's not another calculation or even sort of a setup for the same kind of idea of looking at it in an initial tiered approach to the surface deposits in an area that did use a mist and a spray from droplets or condensation from the air, because those droplets, as we know, do come down onto the home surface areas. Why it just seemed to me that there would be the same kind of tier for this surface opportunity for exposure, and maybe someone could speak to that, please.
Dr. Chason, is this about the aquatic surface water exposures?
No, this is actually just the idea of the tiered approach for exposure. So if that's inappropriate for the
Okay, that was part of this presentation, so I think maybe I have a similar question, but yeah, somebody from EPA can probably answer that about the tiered approach.
Hi, this is Karen Eisenreich, EPA. Those questions are really related to our consumer analysis, which will be presented on later, and will be a good place to revisit those.
Fine, thank you very much.
Okay, so just a point of clarification, that tiered approach is mentioned in the ecological assessments, and so it's appropriate for both places. But we can address the tiered approach aspects where at any point during this discussions. I did want to circle back to one discussion point that Dr. Slink was having with I believe it's Dr. Groza. I can't remember everybody's name here. But the measured data downstream of POTWs, maybe I misheard that. I understood originally in the presentation that those were likely not downstream or mostly not downstream of POTWs. And then in the discussion with Dr. Slink, I thought I heard the indication that those measurements were downstream of POTWs. So can that get clarified a little bit here, just for my sake, because that's a big point in this assessment.
This is Brian Groza with EPA. So to clarify, a lot of that surface water monitoring data, or the bulk of it, came from the water quality portal, which are submitted from lots of different agencies, can be lots of different conditions. So by looking into the data set, we were able to figure out some that were located downstream of POTW outfalls to kind of correlate them with the modeling assessment that we had done. But that does speak to maybe the difference in the distributions represented in those data sets as well. Some of the questions that we're asking about relating to modeling and monitoring, because those could be collected far away from a POTW.
Right. And so then to kind of as a follow-up, the high end that you're using there for the monitored, is that's a high end of the entire data set, whether it's downstream or not?
That's correct. And that is a monitoring data point that does align well with our modeled scenario, where it's downstream from a POTW, larger size POTW on a smaller stream, low flow conditions. So it's a good alignment with that scenario.
Well, it's a good alignment, but is it the 95th or the 90th centile of the downstream data? The basic question is, if you were to do only downstream of POTWs, would you get a high-end estimate that was higher than the value that you selected, i.e., are there values higher than that in your database?
That 25.5 micrograms per liter is the highest data point in the monitoring.
Okay, and so you're not going to get a higher number by going to a higher centile.
Correct. Yeah.
Okay, so that's very good. Thank you for answering that, because that's a big point in the and that kind of answers my next question: is could you have multiple POTWs discharging into one river reach, where then you've got accumulation because everything's not degrading? And I think you've answered that with your last question. Okay, I think that's it. And from me, and let's see if there's any other questions. I see a EPA commenter, maybe with a follow-up. No, you folks are just getting ready to go next.
This is Karen Eisenreich. We're just ready to move on to the.
Yeah, so let's go to Dr. Berneau to talk about environmental exposures and fish consumption.
Hi, my name is Randy Berneau, and I'm an environmental risk assessor with the EPA. I'll be presenting information about HHCB's bioaccumulation potential. Next slide, please. I'll focus on information relevant to charge question 17A and charge question 17B. Next slide, please. Section 4.3.3 and Appendix G in the TSD on the physical, chemistry, environmental fate and transport, environmental releases, and environmental exposure assessment, and Section 2.4.3 in the risk evaluation are relevant to charge question 17. Next slide, please. HHCB is highly lipophilic with a log KOW of 5.9 and has the potential to bioaccumulate. The highest HHCB concentration reported in a US animal is 2,100 micrograms per kilogram wet weight in a common carp. It has also been measured in other wild fish like bass, bluegill, and catfish, other aquatic organisms like zebra mussels, and predators of aquatic biota like otters, mink, dolphins, sharks, and ducks, indicating trophic transfer. All of these monitoring data are consistent with HHCB bioaccumulation in organisms associated with water. HHCB can enter fish through direct uptake across their gills and through dietary ingestion. To quantify bioaccumulation factors, or BAFs, are field-based metrics that reflect both gill and dietary uptake. Bioconcentration factors, or BCFs, are typically derived from laboratory OECD guideline studies and capture gill-only uptake. Reported BAFs and BCFs for HHCB range from about 261 to more than 60,000, with several values being greater than 1,000, consistent with bioaccumulation in fish and potential trophic transfer in food webs. At the same time, laboratory and field evidence indicates considerable metabolic transformation and elimination in fish with limited biomagnification into upper trophic levels. Next slide, please. EPA applied a tiered exposure assessment approach, starting with protective inputs and refining as needed for decision confidence. For the purpose of a screening assessment, conservative input values were chosen, including BCF equals 1,584, and the highest modeled surface water concentration from the combined commercial and consumer down the drain release scenario that we were just talking about, which was the highest concentration attributable to TSCA conditions of use. The screening assessment resulted in fish tissue concentrations roughly 20 times higher than levels measured in wild fish, where exposure cannot be attributed to TSCA uses. This divergence signaled that the screening assessment was appropriately conservative, but it warranted a closer look at the key processes driving accumulation in fish tissues. Specifically, the screening assessment omitted information about routes of HHCB intake, in-fish metabolism plus elimination, and in-stream factors such as fish behavior, alternative flow regimes, all that would be expected to lead to lower tissue concentrations. Therefore, the assessment was refined to address uncertainty in uptake routes, gill versus diet, using Gobas et al.'s ADME-B tool and EPA's CABAM model. And it was further refined in CABAM to explicitly incorporate log KOW, fish metabolic transformation, and food web structure. These refinements yielded more confidence and more realistic fish tissue concentrations for human and wildlife fish ingestion risk assessments. Next slide, please. To address uncertainty in uptake pathways, EPA implemented parallel refinements using the ADME-B calculator and EPA's CABAM model with conservative decision-oriented inputs. For ADME-B, the highest modeled surface water concentration of 24.5 micrograms per liter was paired with the highest measured fish tissue concentration as a dietary input and incorporated chemical flux data from Schneider et al. 2021, which was an OECD guideline dietary study. Under these conditions, the model apportioned approximately 94% of the HHCB uptake through the gills and about 6% through the diet. EPA then applied CABAM to independently estimate uptake via gills and diet. Inputs included a log KOW of 5.9, bluegill metabolic transformation rates derived from Van Dijk's 1996 OECD laboratory water-only exposure study, and allometric scaling of metabolic rates across trophic levels. In this scenario, CABAM results indicated a somewhat smaller but still dominant gill contribution, around 78% of total uptake. Taken together, these lines of evidence converge on the conclusion that gill uptake is the primary driver of HHCB bioaccumulation in fish, with dietary uptake playing a secondary role under the conditions evaluated. Next slide, please. To refine fish tissue estimates for human and wildlife fish ingestion risk assessments, we used the CABAM model to incorporate metabolism and food web structure. The highest surface water concentration attributed to TSCA conditions of use was used again. As with the screening tier results, these results are conservative and are expected to overestimate real-world fish concentrations, as illustrated by the modeled bluegill values exceeding the highest measured value in wild fish. Unlike the initial screening tier, CBAM explicitly incorporated metabolic transformation and a more realistic food web structure, reducing key uncertainties. Overall, these bioaccumulation refinements increase confidence in the tissue estimates and support decision-making for both human fish ingestion and wildlife fish ingestion assessments. Next slide, please. Thank you, and I'll pause here for any clarifying questions.
Thank you for getting that into the record. That was a nice presentation. Dr. Schlenk.
Yeah, I I had some real trouble when you're saying you're plugging in a metabolism metric into CBAM. I went on to the CBAM handbook and I didn't see a single incidence of a KM or any sort of metabolic capability metric that was at or parameter that's actually used in the model. I did see that ADME had you use a calculation from a non-metabolizable standard or reference compound, which is one question I do have is what was used as the non-metabolizable reference compound for the ADME B, but for CBAM, I didn't see any metabolism component in there. So I'm wondering how you're actually estimating metabolism from CBAM.
Hi, Randy Burnell, EPA. Yeah, Appendix G in the exposure TSD has the details of how I incorporated metabolism from the OECD paper into CBAM, and there's a whole section on metabolic transformation in CBAM. I can get back to you on that.
Yeah, that the OECD paper doesn't have a metabolic rate. It's got an elimination rate, but there's no metabolism in there. It's an elimination rate. I didn't see anything on metabolism.
Randy Burnell, EPA. Again, I will refer you to the Appendix G of the TSD and the details there. They're in that appendix, how we calculated metabolic transformation and elimination. Yep.
Yeah, I looked at that. The second question I would be then is what was your non-metabolizable reference that you compared it to for the ADME? Because I didn't see that either.
Randy Burnell, EPA. I'll have to get back to you on that. I can't recall off the top of my head, but I will get back to you on that.
And I guess I'm wondering, were you aware of the Fernandez et al. Paper that actually looked at in vitro biotransformation that actually showed this as being fairly rapid metabolizing?
Yes. But we used the rates from the OECD study.
Okay, which again is a rate elimination. There wasn't any metabolite identification which I didn't see anyway, right? I just want to confirm.
I will have to get back to you on that, and I look forward to your comments, and I can get more information to you. Yeah.
Okay. Yeah, and again, as far as I know, I'll just hold off on that. But yeah, I just want to make sure. Yeah, I'm just curious how you define something that's that bioaccumulates but is also metabolized. That those two things don't usually go together very well. The other question is, was there any other thought that the fact that this has such a high log KOW that it would actually be bioavailable for aqueous uptake? Usually compounds with that high log KOW partition out into organic carbon and usually drop off into sediment or picked up, by detritivores or things of that nature, not by fish, but.
Randy Burnell, EPA. So there's a lot of evidence of it being present in fish tissue.
I know that.
Yeah, so
I'm talking about your estimate of gill uptake versus dietary. It would seem to me, based upon the chemistry, at least the fate of this compound, that it would be more dietary, as opposed to aqueous.
Randy Bruneau, EPA again. That was specifically why we used the ADME-B calculator, which addresses that particular topic.
But it doesn't, I don't think it incorporates a bioavailability constant, does it? Does it actually have a availability constant of the compound? I think it just looks at log KOW, right?
I will have to get back to you on that. I'm off the top of my head, I don't know.
Okay. I don't think there's an aqueous DOC metric in that in the ADME, but I could be wrong on that. But anyway, all right, thanks.
Thanks for those questions, Dan, and Dr. Slink and Dr. Bruneau for the answers. And just as a point of reference, we would need those answers before we get to these questions, the charge for this bioaccumulation part. So fortunately, that's late in the week, but that'll give you a day or so to get some responses to Dr. Slink's question. Dr. Chasen.
Thank you. Following up on Dr. Schlank's questions and related to that, I tried to sort some of this out, but I've come to a couple sort of very basic questions. Maybe you could opine on this, EPA. The calculations start with bluegill sunfish study, if I'm correct. And I understand that this particular fish is unique in how, for lack of a better word, skinny it is, and is kind of known for not taking on this kind of chemical. So if you had started the calculations with, or if the study had been done with, quote, a fatter fish, you would, those are my terms, that's not what the way they described it in the study, of course, but it seems like it would have been more representative. In fact, in considering, it's not a math error here, it's sort of like a concept problem. Because of the physical characteristics of this chemical, I would expect, in fact, it's even in earthworms, and we know that this is going to go into the bottom, if you will, and we have a lot of food that is both for the environment as well as people down there, everything from fish that live on the surface to crabs and clams and things like that literally dig into the bottom of the rivers during certain seasons, but bivalves that are known, or we look at those for possible ways to clean up the rivers. So maybe you could explain two things. One is, how do you think these studies and the data from the bluegill sunfish are really the appropriate beginning, if you will, of the math? And number two, why are we just looking at free swimming fish instead of a full dietary plate, if you will, of very relevant edible items out of the water? Thank you.
Bruneau, EPA. So the Caban model does provide us with results with more trophic levels, including sediment-dwelling organisms and shellfish. For the the rest of your comment. We really look forward to your written comments and ways that we can improve our model. And so, yeah, we're looking forward to seeing your comments.
Dr. Lee?
Okay, so this is Lee, SACC member. So I do have a question regarding the bioaccumulation factors used in the report. So I noticed that you list both the BCF and the BAF values, and for BCF that is the number around 2000, but you do report BAF values about 39,000 for silver carp and 52,000 for crucian carp and 66,000 for common carp, which is about 20 times or 30 times higher than the BCF used here. But actually, you didn't give the consideration to these high BAF values. And you mentioned that these numbers are snapshot fish and water measurements, and they have unknown exposure concentration durations. I was wondering whether you have ever considered the physiological differences between the fish you consider for BCF and the fish like the common carp for BAF values you consider here. You are muted.
Sorry, we're having technical issues. Okay.
No, I can hear you all right.
Can you hear me? Okay. Randy Burnell, EPA. So we considered all of those species across a range of BAFs. And one of the reasons why we used CBAM was to have a more generalizable set of fish tissue concentrations that didn't rely on one particular species, particularly because of the range of these different accumulation values. Does that answer your question?
Okay, that means you didn't consider the reason contribute to these high BAF values in the literature.
Sorry, can you repeat that? We're having issues in DC.
Oh,
here.
so I mean, that means you didn't explore the reason why these high BAF values are there. And instead, you just use the generic fish and generic food web, and you consider that.
So we, in our broad screening assessment, we did want to have a sort of a general view and did not explore each and every reason why there's differences in BAFs, correct?
Okay, thanks.
Okay, this is George Cobb. I think we're kind of running out of time for some logistic reasons, I think, on the EPA side and some logistic reasons on the committee side. So I'm going to call it a day, but I want to do two things before I do. I want to ask the committee to stay online after this is over. And I'd like to turn it over to Dr. Kamal to close us out for the day.
Thank you, Dr. Cobb. And I also want to thank everyone else who participated in today's meeting, EPA presenters. And we will continue tomorrow, the last section of the HHCB and the public commenters also. Thank you, and the meeting is adjourned.